Applied Physics Lab, and we would like to welcome you to this workshop session. This workshop is the brainchild of a standing committee of the National Academy of Sciences, the Standing Committee on Transformative Science and Technology for the Department of Defense. We're chartered by USD R&E to bring forward a broad set of technologies that the DoD may have interest in for future mission applications. Yvette and I, at a workshop meeting many months ago, brought forward the idea of a workshop on VLEO, technologies, missions, impacts. And we're really pleased to have you all here with us today and to have so many people joining us online as part of this session. I'm excited about this, about the speakers that we have lined up that you'll hear from in a couple of sessions. Yvette will come up in a moment and introduce them. I did just want to say, you know, as someone who has worked in the space technology and the space science domain for for several decades now, VLEO has a ton of potential. VLEO is like what constellations were a couple decades ago. If you think about the mission impact benefits of being able to operate lower and closer to the Earth, whether it's a reconnaissance benefit or the improvements to telecom, which can reduce power or improve transmission, the reduction in launch costs, which you can see with the way SpaceX is flying their Starlink constellation these days. There's a lot of good reasons to fly in VLEO. There's also some very unique challenges, right? It's low enough that the atmosphere matters. It's a regime of the atmosphere that some call the ignorosphere because we know so little about it. Space weather influences this regime, this atmospheric regime, because it's so low in density. Generally speaking, it's a different mixture, a different composition than we're typically used to flying through. So there are some material challenges there. And you're going to hear about all of these things in the workshop and much more in the workshop session today. So our goal, this is like an informal meeting. Our goal is to just talk about the challenges and the benefits of VLEO. Each of the speakers has a slightly different perspective from where they sit, from their expertise. And I think in an integrated sense, we'll get a very good picture of both the challenges and the benefits of operating in this domain. A domain, once again, that I think the United States will be operating in the coming decade in a significant way. With that, I want to bring up Yvette for her opening remarks and then to introduce our first panel. Thank you again for being here.
Thank you, Bobby. Okay, well, welcome. We look forward to a great morning. The first part of the morning was actually the difficult one to organize. Felipe, Ian, Mitch, Mike, we knew you, so we just invited you. That was easy. The government perspective, less so. But thanks to Amanda, Justin, and other people, we got connected to a great set of people that can tell us more about the government perspective. So that's what we are expecting in the first half of this meeting. And then the second half, it's the professors telling us what they've done and what they think that the opportunities are for VLEO. So with that, and without further ado, I'm going to invite our first speaker. So the first speakers, Seth, Mike, and Spence, they each have 15 minutes to talk. And you were told to either bring slides or not bring slides. We don't care so much, but we care about the information that you're going to give us. So the first speaker is Seth Lacey, and he is the Senior Scientist for Space Mobility and Precision Maneuver at our beloved AFRL. So Seth, 15 minutes.
Thank you, Yvette. I'm going to do a little bit of an intro here, and then Dr. Holmes is going to pick up and present the charts. So as way of introduction, we're pretty excited about the opportunities of very low Earth orbit. We think that there's a lot of things on the defense side that we could benefit from VLEO. It's a very uncertain regime, and we're lacking in physics understanding. We're lacking in data to do good modeling. So there's a lot of challenges that we need to work through as we explore this new regime. On the benefit side, being closer is better for all kinds of things. So that's I think everyone kind of sees whether you're thinking about 1 over r squared up to 1 over r to the fourth, or closer is better for lots of activities. On the radiation side, it's a much more benign environment than we experience even in low Earth orbit. You could consider flying, the latest and greatest processors. You could probably fly your cell phone in space and have it last a long time. The radiation environment is very benign. So there's another benefit there of, instead of having to deal with even the radiation environment in low Earth orbit where humans live, we do survive in low Earth orbit for a while. This is even more benign and looks even more like a terrestrial environment. And then back to the beginning, we're very excited about exploring the new domain, and we'd like to, all the help we can get on getting through and learning more and getting more data to support the exploration of this new domain. Dr.
All right, thank you, Dr. Lacey. My name is Dr. Marlon Holmes. I work at AFRL Space Vehicles, Branch Technical Advisor for Small Satellite Portfolio. And I want to talk about the challenge and really why we're here, why we're engaging with industry, why we're engaging with academia, because we need your help. So next slide. So let you sit with this, but the bottom line is every domain is contested. We now know with pretty much good confidence that we can reach out and touch nearly anywhere. And this is outdated information at this point. This is before the Space Force, right? And as a Space Force, it is our purview. Our AOR is anything over 100 kilometers, which includes VLEO. Oh, fancy. Cool. But yeah, let's make it clear that VLEO is important. We need to be there. It's our job to be there. So let's talk about it. How low can you go? And more importantly, how long can you last? How do we have a consistent, persistent presence, similar to GEO, similar to MEO in VLEO? And it's non-trivial. So let's talk about what's been done before. If you're familiar with this is GOCHE, work done out of ESA. Amazing experiment working on mapping the gravitational field across the planet. Operated at a VLEO altitude about 235 for years. Very rich data set, open to the public. Definitely encourage you to check it out. Another program. This is SLAT's super low altitude test satellite, Tsubame from Jackson, Japan. Actually has the record, the lowest Earth observation satellite at 167 kilometers. Only for a week. Interesting fact. That's a little bit of a cheat. At that point, they weren't just using EP, they actually had a reaction control thruster getting up to 1 Newton. We'll talk about that, why that matters. All right, but we have people that are up there doing things. Is it operationalized yet? No, but we're taking pokes. So why not lower? What happens? What we know is as we go from 235 to 135, things get funky, right? The mean free path versus the dimensional length starts to go approach 1. We're getting rarefied flow, and now air starts to act like ping pong balls. Atomic oxygen starts to eat you up. Things get challenging. What does that mean? So looking at these ranges, we have GOCHE at 235, SLATs at 167, and 107.8, that is X-15 experimental aircraft back in 1963. As you can see, not sustained. Rocket motor got up to speed, and it coasted through. What happens in this range? Well, first thing is drag. Looking at the data from GOCHE, 235, you're talking about 20 millinewtons per meter squared, right? Roughly thrust that they need. Okay, not too bad. 167, just at 100 kilometers, we go up to about a Newton plus, right? So we're talking about orders of magnitude. X-15, even more. We're dealing with a fairly almost geometric scale increase in drag, much beyond what we normally see with EP. What else happens? Well, heating. Friction now starts to matter. GOCHE, 160, getting down to X15, it had to have special Inconel plates to deal with the actual heating drag as it went through the atmosphere. But that's not all. Power. The Oche was about a 1.3 kilowatt vehicle. X15 had effectively 130 kilowatts of power going out. So, ladies and gentlemen, this is a challenge. So what does this mean? We are in an unbelievably vicious cycle, whereas you need more and more power, you need more and more solar panels, which means more size, which means more drag, which means more power. This is an inherently linked problem, and we need your help to solve it. And not only that, because we're still not really able to use convective cooling, radiative cooling, where do you put your radiators? You would love to put it to cold space. How much do you have of it? It's a challenge. We need some of the brightest minds to do it. So I would leave you with this. We need your help for coupled models, for test facilities, for better understanding the physics, for materials, for AO resistance and fluence, better understanding rarefied flow. We need your help so that we can not only go into this space, but lead in this space as we should. Thank you for your time.
Well, very quickly to the point. Thank you. So that's good. You can find out the end to question all of the presenters. So our next presenter, so that was the beloved AFRL, and I do mean it, I love AFRL. And the next one, we're going from the Air Force to the Navy. And so it's Mike McDonald, who is an aerospace engineer close to us at NRL, the Naval Research Lab.
All right, folks. So thank you for having me here. I'm Mike McDonald. I'm from the other RL, Naval Research Lab here in Washington, D.C., where I lead a propulsion group where we specialize in the creation and characterization of energetic flows. So if you'll click through me to our first slide. Seth hit this a little bit, but I'll just add a couple pieces of extra flavor for why we want to be in very low Earth orbit. Very low Earth orbit is this liminal zone between the atmosphere and space where you have just enough sparse atmospheric air remaining to be dangerous and to either give you a resource if you want to maybe harvest it for propellant, or to give you some reaction surface as some potential control authority. But that opportunity comes at tremendous cost, which is drag. And that's really the reason that no one is there today. But you have the potential maybe for some future with really sustained ability to maneuver. So otherwise, the propulsion requirements and the fuel requirements in this regime are just so demanding. You get lower, you can enhance your resolution. The same telescope gets twice the resolution when you go half as high. If you think about receivers, and radio signals, you can again get R squared, 2 doublings, or maybe a 6 dB when you think about signal to noise at just a very high level. And finally, it's certainly a nice orbital regime that it cleans itself of debris when we think about things like Kessler syndrome and the idea that spacecraft crashing into one another could lead to a cascade. And you have an easier launch access. But there's not a lot of people there right now, and there's a reason for that. Is it's incredibly hard to stay aloft. So if you'll click once, the thing to take away is, can we fly where no one else can, as Marlon was just asking. So if you'll click once more for me, the first problem is obviously propulsion to stay aloft, and I'm showing a collection of Busick Hall thrusters here, not to endorse Busick, but because they had a convenient picture I could pull with a lot of different thrusters. But we think about operating in very low Earth orbit, the atmosphere comes at you at 8 kilometers per second. You need to at least be making that up with some exhaust velocity for propulsion systems. So chemical is not really going to work for us. It's not going to have the performance. we're going to be stuck looking at electric propulsion. Now, EP traditionally runs on something like xenon or krypton. You can see here, we picked the heaviest atoms on the periodic table to use because it gives us the best thrust to power. And in orbit, we are trying to match that with our drag to power from our solar panels. But recently we've seen folks like Starlink switch over to argon just because it's vastly cheaper. We joke that xenon is about $1 a molecule when we have to use it in the lab. And we have a whole wealth of other propellant options as well. Hall thrusters in this case have run on a number of other propellants, but air in particular. So there is the potential to have EP systems that are going to use the air that is already providing you drag. But again, think about that balance. It's coming in at 8 kilometers per second. You're going to stop it and then re-accelerate it. So you're only going to break even if you spit it out at 8 kilometers per second. If you think about some frontal drag of a bluff body hitting that environment and bouncing it back, now crudely, you should be thinking twice that is what you want to be exiting out the back of your vehicle. So you're going to really need these kind of EP systems to get to that point. And the other thing is that you're usually volumetrically limited because of drag in a low Earth orbit environment. So you may decide that air is not the right thing to use. Maybe use one of these other propellants. But xenon, krypton, argon, those are going to store at maybe 1 gram per cc. You might have much better bang for the buck if you could store something condensable, if you wanted to take the hit and just have a limited lifetime. But as we look at all those things that are condensable, you should think that we don't put spacecraft up there to demonstrate propulsion systems. We put them up there to do things, to look and to listen and to talk. And asking where those condensables go after you fire them out of your thruster and do they end up on the things you cared about on your spacecraft is certainly a validation challenge if we were to go that route. The last thing I'll maybe point out is that when I think about propulsion, this is my background in particular, I think about the Hall thruster as an ink blot that slowly spreads on the parameter space of optimal thruster solutions. So you should, when thinking about other propulsion technologies, regardless of domain, VLEO or elsewhere, I always start by asking, why can't a Hall thruster do this and work back from there? And if I had to answer in this particular case, it's because air is quite challenging you can see the little bright spike of light next to the ring in some of these pictures, which is the cathode, where typically we boil off electrons from a thermionic emitter to neutralize a Hall thruster exhaust. And so air-compatible cathodes are not really currently a thing in our universe. That is a research and development challenge. And that's what pushes us towards still exploring RF-based and other technologies that might give you more electrodeless acceleration. Can you click ahead for me? This is a classic kind of trade space showing performance of propulsion systems. And so if you were to look on here, you would see those Hall thrusters I just showed, a lot of EP systems. These are huge boxes from someone's old paper, but around 100 millinewtons, around a few thousand seconds would be in the middle low end of that blue. But what I want to call your attention to is we talked about 8 kilometers per second a minute ago. So up till now, I've talked about thrusters, but generating the ground test environment is equally challenging. If we ever want to collect the air, if we ever want to measure drag on vehicles, if we want to do ground testing, because let's put it up in space and test it there because it'll be easier, said no one ever. Well, 8 kilometers per second, that's about 800 seconds of specific impulse. So you imagine that horizontal line at 800 seconds, there is not a lot there. Chemical is going to top out at 400 or 500 seconds. Nuclear thermal, if you have a reactor in your pocket ready to go, it still probably isn't great for VLEO because that's a designed re-entry location. And the only time we've ever purposely re-entered nuclear material into the atmosphere, as I know, was Apollo 13 when the astronauts were going to die otherwise. So reactors for VLEO or even RTGs are quite challenging. And electrothermal, that's usually an arc jet or a resistojet. So recall again, primary environmental species is oxygen. So hot refractory heating elements or exposed arcs in an oxidizing atmosphere is non-trivial. So the way we do ground simulation of the VLEO environment today is often via laser detonation. You fire a high power laser into a nozzle feeding oxygen, it thermally will flash dissociate that into O, and you'll expand that out into usually a small materials-based test cell for cross sections and scattering rates and angles. You could do that, but that's a pulsed system usually at a couple hertz. It's somewhat limited in flux, whereas we want to simulate lower and lower altitudes, or even if we just want to do accelerated life testing to simulate a higher altitude faster, those laser detonation sources have some challenges. But it's also not super clear what else you're going to use, because you want to have atomic oxygen, an unstable species, moving at 8 kilometers per second, which is a hyperthermal velocity, which is also only about 5 volts of energy, so tremendously low for electrical acceleration. But even if you do electrical acceleration, you'd love it to be neutral at the end as well. So, stack your miracles accordingly. So let me click once more. Next, I'm just going to point out, people coming from a thruster background are used to thinking about your ground test facility and pumping out your thruster fuel. And that is indeed a problem. Just showing here a chart that as you flow more and more xenon, in this case for bigger and bigger thrusters, for a given vacuum facility, you'll see higher and higher pressures. And there are thresholds where you can't test above a certain pressure. There's going to be too much scattering of your thruster exhaust. Well, the same thing is going to happen if we simulate the low Earth orbit, the very low Earth orbit environment. If we make an orbital wind tunnel, you now have a bunch of process gas that is impeding your ability to simulate the space environment. Remember, space beats us on pumping speed every time. And so if we consider, say, a half-meter diameter beam simulation at 180 kilometers, if we were perfectly efficient, every atom was collimated and shooting in exactly the right way, which we don't even do with thrusters, and we've been working on them a lot longer, that'd be about 20 skims or SCCMs of flow. If we go up to a square meter to do bigger vehicles, it's 4 times bigger, that's 80 skims. If we have some reasonable inefficiency in that acceleration, have to skim off part of the beam, you could be talking about hundreds of SCCM. And yet we still are facing some of the same physics where we'd love to be at or below that 10 to the minus 5 torr range. So you're really looking at facilities where you're in the hundreds of thousands of liters per second of pumping speed for appreciable size simulation of these facilities. Let me click again. I just note, so VLEO wind tunnels will tax our facilities. On the next slide, I'll note that once we solve all the propulsion and ground test problems, when we go into orbit, we have a rather unknown environment. 8 kilometers per second is how fast the atmosphere comes at you. But this is just a plot from the Grace satellite and some others, the cross-track wind speeds that you encounter. For example, going over the poles. So the axes are a little confusing, but you start 0 here as the latitude of the equator, 90 degrees is the North Pole, 180, 270 is the South Pole. And so you see these peaks on the top in the magnitude of wind as you go over the North and South Poles. That can be something like 10% of your directed velocity. Now, again, remember, our platonic ideal, say, for a vehicle is probably a big cigar. It's very it's got some volume, but it's very, aerodynamic. You get some little stubby solar panel wings, and it's got beautiful drag when your angle of attack is 0. But when you all of a sudden get wind from the side, you're not at angle of attack 0 anymore. You have some big, planform area that is going to get hit. And while we try to model this, we don't model it perfectly. So you're going to need some ideally in situ ability to monitor that and know how to maybe keep yourself pointing into that direction where the atmosphere is coming at you. Again, this is challenging. So if we click ahead once more, on the modeling side, this is an NRL MSIS model. So this is kind of the standard in the field if you want a quick plot of what all the densities are going to look like as a function of altitude. Can do full maps of the globe with latitude and longitude as well. But you'll get some set of data that says, at my given altitude, my density is like so. And you will take it, and if you are not a discerning consumer of that data, you might not know that that's maybe plus or minus 30% on any given day. And keep in mind all the margins that are stacking up here. Your power, from your sun state going into your power system to run your thruster to stay aloft. If you're trying to use the air, how much air you're getting, what the solar state is, which could affect these things. 30% is a lot of system margin to try to carry. So these models are very useful, but also somewhat limited. And if we click once more, this is just a beautiful overview chart I picked because it's pretty and it gives you the sense of, wow, it's complicated. And that's, if you take only those two things, that's fine. I'm not a space physicist. I'm not going to go into detail. But the way that people in this field talk about the environment is that today's thermosphere, the neutral environment, drives tomorrow's ionosphere, the charged particle environment. So that is the way the physics works. The way our measurements work is that it's very easy to measure charged particles. I can tell you this is also true in the ground test simulation side, where even if you make 8 kilometer per second oxygen, it's very challenging to know that you did it because they're hard to see. But we measure today's ionosphere, and then we go back a week or two in our models and tune the way the neutral stuff looked then to try to make it match what we see today. And this, so instead of today's thermosphere driving tomorrow's ionosphere, today's ionosphere is what we use to back predict yesterday's thermosphere and then try to make our forecasts. And you'd certainly love to have a forecast that was accurate going out into the future. So, because that's usually when you want to plan things, is for in the future, not last week. So if I'll click once more, these are my last couple slides. I took a picture of the initial proposed Starlink constellation that someone on YouTube helpfully put up into STK. And I just wanted this for a sense of scale. We often say VLEO and we draw a picture of the Earth, then we draw somewhere like way out here, some satellites, but VLEO is really close. Like look at that innermost yellow ring. That's for the 360 kilometer direct to cell part of that network. And we're talking about for VLEO, it's half again closer than that. And then you look at how many of those satellites there are to get good coverage at that altitude. And again, there's an R squared problem. Your field of view shrinks as you get lower. So imagine you need still more when you get lower. So I kind of wanted this to give you a sense of, you can click once more, I think, just to show for scale. That little orange ring I put was my attempt in PowerPoint to make a 200 kilometer orbit. But you have an environment that you don't especially know well, because neutrals are hard to measure, especially from a distance. So you have to sense all these things in orbit. You have very limited field of view to them, say from a ground station. So you may have to go up and then come back down or do some sort of mesh network. Things are going to change fast, and you've got a whole lot of them, which to me suggests that there is some significant missing autonomy piece as well that is letting you try to manipulate and stay in what an aircraft we would call steady level flight, right? But up in space, in this part of space, we also have weather. So navigating to that part of steady level flight is, I think, also going to be a challenge. So in conclusion, I've mentioned a bunch of challenges in VLEO, propulsion, power, ground testing. I didn't talk much about materials except in the context of the cathode, but atomic oxygen is nasty, so it presents other challenges as well. Guidance, navigation, and control, and then this autonomy and sensing and communication, all these things together. If I had to pick some that I think are most challenging to me, some of those feel to me like the ground testing side and this autonomy and sensing side for how you close the loop once you're up there. But again, it's my 2 cents and your mileage may vary. So thank you. That's all I have for you.
Our third speaker for this session is Spence Wise. He is the Senior Vice President for Space Missions at Redwire Space. So Spence.
First, let me say it's very exciting for me to be here with all these smart folks here. I recognize many of you from some of our early work stepping into VLEO here at Redwire, and it's a very impressive group. So I feel like the old adage is always surround yourself with smart people. I think I'm doing a really good job here. So thanks for having me. Again, Spence Wise, Senior Vice President at Redwire Space. Redwire has been on a multi-year adventure into very low Earth orbit, into the very applied and practical engineering of let's go build systems to fly in VLEO. So I think it should have a bit of a unique angle relative to our earlier presenters, which covered the physics and science foundations of VLEO very well. So I won't try to jump into that deeply, but maybe give you a little bit more of the mission perspectives and practical challenges with very low Earth orbit. I did want to start though, because I found this to be an interesting factoid. If I could get audience participation here, just if everybody would raise their hands and then put them down when we get to if you think the answer is right here. So the question I wanted to ask is a quick survey on when the first VLEO mission was. So get your hands up. So when you hear your answer, you can put it down. Who thinks we're going to do VLEO for the first time next year? Okay. All right, couple hands. Who thinks the very first VLEO mission is already underway? Started last year, a couple years before. Yeah. And there is a quiz in this because the AFRL folks gave you one of the answers. Watching Marlon over here. Back in the last decade. Yep. Okay, good. All right. And then let's pick an arbitrarily large number, 50 plus years ago. That was the right answer. So this is it's really interesting to me. You get back to the Cold War era, and this is where VLEO was actually born. We had a scenario in the early 60s where our U-2 reconnaissance airplanes were getting shot down. So the United States took to the challenge and created the first now published programs and a series of programs. But the one that's maybe most notable and longest running was the Corona program by what is today known as the National Reconnaissance Office. What's exciting about this was they flew in very low Earth orbit and they solved it with brute force. They didn't have digital cameras to downlink with. They literally dropped film from space and caught it with airplanes. I mean, there's a whole engineering feat just in that. And then, of course, they had to deal with drag even then. And you could probably guess how they dealt with it the way you would with big rocket thrusters. So they would literally build their satellite into the top half of a rocket and would plow through very low Earth orbit. They would collect their images and eventually deorbit the satellite. As you can imagine, building entire rockets just for the purpose of collecting photographs got to be fairly expensive. So VLEO kind of quietly fell out of popularity. And we knew that the altitudes at which missions were executed moved higher and higher and higher for a variety of reasons. But we're back to talking VLEO again. And part of the survey at the start there was a bit of a trick question by design, because we really are sort of rediscovering VLEO in a sense. We're now approaching it in a way that we have a market and an environment that cares about the economics of how we solve, be it national missions or even commercial missions. Direct to cell was discussed earlier, among other things. So there's a burden on mission architects and designers now that we need to be able to deliver these missions in a cost-effective manner. So we are looking at things like optimized satellite bodies to minimize drag. We're looking at a variety of electric thrusters, and even one of the topics du jour, air breathing systems. So I appreciate you going through the public survey there. It's helpful. Let's see here. So maybe a little bit about myself from background. So I've been in the industry side of things. So I'm not a PhD or a scientist. So just work in industry here for about 20 years. Again, Redwire I mentioned had been into VLEO for a good variety of years. It was actually started back in about 2022 with our European based side of the house for the European Space Agency's SkimSat mission. Our team supporting Thales Alenia Space is the bus prime on that. So in 2023, we looked at how we, Redwire in the United States, could benefit from some of their early work and thoughts and lessons learned, and set out to develop our own very low Earth orbit bus. Because we could too, like everyone here in the room, could start to see that the reemergence of very low Earth orbit was coming, and that we needed to position with architectures and technologies to get there. In 2024, we announced that we were selected as the prime contractor on DARPA's Otter program, which is intended to be an air breathing demonstration flight. Of course, starts with ground testing and then goes to flight. There's a good bit of information on the original sam.gov, but the DARPA program managers are always very happy to discuss the program further. So if you'd like information about that, feel free to reach out and we'll connect you with those folks as well. But that brings us to being a bus developer for very low Earth orbit. So we have a product we call SaberSat that has been optimized for very low Earth orbit. It can be an air breathing system or non-air breathing system. And as Michael mentioned, there are reasons to do air breathing and not air breathing. It does take up swap, as you can imagine, to put an air breathing system into a satellite. And that may not be what you want to do. You may want to focus on mission effects. So what payloads am I going to carry? So again, we offer both versions of that. Most notably, or most recently, we did announce here in 2025, just about last month, that we're undertaking a commercial constellation support to a partner of ours called DeepSat, who is an LA-based company. They're stepping out to start the first constellation scale, very low Earth orbit deployment for a commercial company. They have brought us on to do modeling and simulation. We've heard a little bit about sparse gas modeling, DSMC code. I'm assuming the room's up to date on those sorts of things, but that is something that is one of the Redwire proficiencies and things we spend a lot of time working with. So we're very excited for that partnership. But I wanted to drop back to maybe the foundational why VLEO. This should be kind of the question we all ask every day when we get out of bed. VLEO presents a number of challenges that have already been discussed. So why subject ourselves to that, right? So Michael had mentioned this, but proximity brings a lot of benefit. The inverse square law, tells us that we're going to lose a lot of signal intensity between 2 points if those are far away, right? So getting twice as close has a 6 dB benefit or a 400% increase in signal strength. I think all of us who have worked on a mission where you're trying to squeeze a dB out of an RF system can understand how impactfully 6 dB just from being closer is. So you could almost just put your stack down and say, that's why we do it, right? But there are more reasons. Resiliency. We've all seen, did everybody see the Gravity movie? Was that about 5 years ago? And it still gives me nightmares even thinking about it. But the whole, the Kessler syndrome of losing orbits, congested orbits rather, to debris fields is challenging. You could, in theory, lose low Earth orbit to decades long debris fields. And even if it's not a total loss, you still have to worry about this debris that's transitioning through your orbit. Being in very low Earth orbit, drag that we fight all day is actually working on our side in this sense. It very quickly deorbits any debris in the regime. So it, in a sense, is a self-cleaning orbit. Seth and Marlon also mentioned that the radiation environment is much more benign in very low Earth orbit. And I think Seth and Jeff mentioned bringing the cell phone up to a satellite. And that is absolutely the way Redwire and some of the partners we look at or work with look at very low Earth orbit. So the application of taking cameras that are maybe more closely related to GoPros rather than exquisite glass that gets put into higher orbits now is very attractive. And recall, we started the conversation, it needs to be an economic justification to go to very low Earth orbit. And this is one of the key ones. So bring smaller, less exquisite cameras into lower Earth orbit, or smaller antennas, fewer amplifiers for RF systems, and so forth. A third key piece of very low Earth orbit that's inherent to the orbit is mobility. If we're going to be fighting drag, we obviously have thrusters on board. So we have some ability to, limited abilities to accelerate. Of course, the bigger one is to decelerate by way of braking maneuvers. And we can see some of the early Chinese satellites that are in VLEO exercising these braking maneuvers as well. Even commercial satellites coming down from LEO to VLEO are showing braking maneuvers. And this is just taking advantage of the natural drag to work with you. But this provides the Space Force and others with the sort of dynamic space operations or freedom to operate in the regime, particularly when we consider, again, the addition of air-breathing systems. So you can imagine if you have little regret in thrusting if you are able to collect more air as fuel than you are expending. So this is the prospect and the benefit long-term of air-breathing systems to the Space Force and others. Fourth benefit that we look at when we're talking to mission partners, in particularly, is orbit diversity and spatial diversity. Much like in the way if you try to close one eye and catch a baseball coming at you, you'll probably miss it and get a big welt on your head. So too do a lot of the Earth observation systems benefit from having multiple collection points and more spatially diversified from one another. They create larger baselines. This gives you, again, similar to eyes, better spatial resolution and the ability to track moving objects or objects that are static under you as you move over them. These are all very interesting benefits. Challenges, we've talked a little bit about these already, so I won't beat these too hard. Drag is the obvious one. Atomic oxygen is difficult. It has a wide variety and density, varying both in your position, time of day, and even the space weather. So as Michael was mentioning, the prospect of forecasting space weather becomes important for understanding your drag, but also the long-term exposure you'll have to the constituents at those altitudes. Next major challenge, and this is one that we would certainly welcome help with, is power. One of the bigger challenges with VLEO is getting enough power on board to maintain your thrust. You could have a duty cycle varying by your altitude. As you are higher, this might be some percent, 5-10% duty cycle on your thrusters. But as you get lower and lower, that may approach 50% or even worse, more, leaving very little power for actual mission operations or payloads. So the more power you can get, particularly that creates less drag, is very attractive from an applied perspective. We talked about atomic oxygen as a challenge. I'm, again, glad to see a few faces here in the crowd. We can talk about some of the materials that can be applied. In the simplest form, if you can go to an oxidized aluminum or a anodized aluminum, that's a first step perhaps. But then the folks who do surface interactions and drag modeling would be quick to point out that that's also a very rough surface, which tends to induce more drag. So the prospect of having surface coatings that can reduce drag and protect your materials is very attractive and something that needs to be a focus of industry here. Add a little bit here, more here about the variability of the environment, but I think, again, Michael covered that very well with his topics, so I'll let that go. Maintaining proper attitude, particularly with air breathing systems. I think, again, Michael mentioned this topic. It's important that if you have an air breathing system that you're able to ingest air with that. I mean, that's obvious. But the direction of orbital travel may not be the same as the apparent winds. So having sensors on board which can indicate that for you are helpful, and having the ability to manage your power budgets and your thruster configuration so that you can allow that collection to occur into the apparent wind, and then returning to thrusting as needed is important. These are all things that we manage in a complex multi-physics model. So I think at the end of the day, for those who plan to enter into the very low Earth orbit regime from an applied engineering perspective, connecting all the models necessary to optimize for mission requirements, but also for bus life optimization and operation is very important. And with that, I'll return the time. Thank you.
Okay. Oh.
In the audience, when you're expecting to capture, please use the mic in front of you.
Go ahead.
Okay, now I guess you can hear me. So if we project ourselves 5 years from now, right, and an ABEP is actually working, what hard problem was solved first in each of your opinion? Was it the drag reduction, power limitations, atomic oxygen materials? So what would you think was that problem that was actually solved? Seth?
I don't think it's any individual tech. I think it's the integration problem. So I think we know enough today to be dangerous. Like we can go, I think, build systems today. We are building systems today that can go function and perform in the VLEO environment with the tech we have on hand today. I think there will be regrets for sure, and we will learn a lot. But it's that integration problem where we've never designed spacecraft for this environment. So we've never really thought about, okay, well, I had this thermal challenge and sticking a radiator off to the side is not a great answer. All right, well, I need to think about how I do the radiator. I have a power problem, but I also don't want to have power like solar panels sticking way off to the side and introducing drag. So now I need to think about that. And which then complicates my thermal problem because now I have, anyway. So it's an integration challenge at the first step. Making something that works better and can last longer and have more maneuverability, those will come, and we'll have to solve materials challenges and thermal challenges to make that happen. But I think the first step really was enabled 2 decades ago with Hall thrusters that produced, the first Hall thruster that made 10 millinewtons of thrust. I think that was the big enabling step. It's taken us a little bit of time to recognize that now this regime is open to us. But that's my 2 cents.
I'll add a couple things. For those who didn't catch, I think you said ABEP, but an air breathing electric propulsion system, for those who didn't catch that. Yes, emphatic yes to all of you solved all the other spacecraft problems first to even let you demonstrate it. But on the propulsion side in particular, if you have a system that I'm going to qualify it now, it's working well, it's doing some material drag makeup. It doesn't have to be extravagant. Maybe you pick a conservative altitude to start where it's a little less demanding. But if it's truly fully air breathing, it means that if it's a DC-based electric propulsion system, you solved a air breathing cathode neutralizer problem. If it's a RF-based system, it means that you've hit one of the best performances that I've ever seen on a RF system where the acceleration mechanism is often not quite clear or sometimes just not quite there. And if it's a pulsed system, think quick, MPDs or maybe vacuum arc system, but you maybe still use a little bit of gas, something where you're pulsing out jets. I still think it's, to me, maybe in that case, an electrode and pulsed power, integration kind of problem. But those are the family of challenges I would think you kind of see there. We're close though, I think.
Yeah. So I guess just adding another comment too is just if we're talking about air breathing, right? I mean, the devil's in the details for a lot of these thrusters. So composition. What are you picking up? And then what is actually going out of your thruster, right? And if you're tuning for a very specific composition, we just know based off MSIS or even limited, I guess limited samples we got for atmospheric explorer or whatnot, composition is going to change versus altitude. Composition is going to change in your orbit. How do you tune for that? Right? You're going to probably have to have some kind of reactive control system and some kind of in situ thought process on what composition is. So it's a tough problem.
I think one of the challenges about VLEO is it's not one thing, right? So if you're flying at 400 kilometers for years or 150 kilometers for days, you're not going to have the same design. And so I think we're at the stage where we're trying to figure out what can be done, right? But at some point, there really has to probably be, some effort put into, what's the first mission that we're actually going to do? I put a stake in the sand and say, look, we can do this, whether it's for national security or civil or commercial. And so my question to you is, what do you think is the first mission that's going to be done?
Well, I mean, to be frank, we kind of already have something going on, right? So commercially, Albedo Space just launched recently. Right now, they're at 425. Their ideas are going down to 375, get 10 centimeter imagery. So it's kind of already happening. That is like RF thruster, not RF, EP thruster, I think, doing xenon, right? So we already got a stake in the sand. We'll see how long it is. That is definitely, low lifetime. So we're not talking a ton of persistence, but I think a few years, right? And ideally, I think eventually want to get to some kind of constellation. So we're doing it, right? That is one design point, but that's 375. I would argue you're just now dipping into VLEO. You're just now, things are starting to get interesting. That's very different than 225 and very different than 150 and very different than 100, right? So VLEO-ish. We'll see.
I would. Oh, go ahead, Spence.
I was just gonna join Marlon there. I do believe that one of the Earth observation kind of functions is the obvious one. I mean, building large scale exquisite glass for higher altitudes is costly and frankly prohibitive. So this prospect of getting to smaller form factors that maintain their aerodynamics in very low Earth orbit, but are still able to take advantage of small primary apertures and deliver, exquisite class performance, like Marlon mentioned from Albedo. I think that's going to be where things get initially established. I think what I'm really interested in is where it goes once you bring air breathing into the to the solution, and you push from months and years into a half decade of operation in a very low Earth orbit. Does that change the arithmetic, the economics? So you start looking at new missions from there.
I was just going to note that I think finding market entry is important, but that's going to be like really tailored to every individual person that or any organization that wants to go up there. And it's hard to think of, for me, pinpointing, and that's like kind of making a bet and hoping you got the right winner, right? And that's why so many different commercial folks are trying this. Everyone's making their different bets. But when I'm thinking about what can I invest in, I don't, maybe it's because I'm more of a earlier stage technologist and scientist, right? That I don't put a lot of flight stuff up. But what I think about is what lets you eventually design the mature systems that let you expand your envelope, that let you go lower, let you stay up longer, or do more interesting things. And a lot of that is enabling some sort of learning curve so that whatever that first mission is, you get enough juice out of it that you do the next one better and cheaper and with some higher confidence. And what I often see in spacecraft is, we focus on a payload. There's a payload that's doing a thing, and that's why you put the spacecraft up there. And then at the end, you're like, oh, here's my power budget, and I need some prop. What fits in my power budget? And there's not enough money for that one that really does it. But this one has specs that might do it, and it's cheaper, so I'll pick that one. And you want a science payload on there too to measure the things. There's no money left over for that. And so what I think about most is what are maybe the most sensitive things that you wish you could get from while you're up there? And how do you make focused sensors that get you a particular thing cheaply, but very well? You know, I often hear about mass spectrometers, for example. A mass spectrometer would be great. You get all the information you could want about the local atmospheric composition. But they're also like exquisite little physics packages, right? And they're expensive and they're hard to qualify. And if they got time of flights or MCPs or amplifiers or, you know, risk, cost. It's like, what's the cheapest thing you can make that picks off a piece of that deliverable package where it's just negligent not to put it on every spacecraft? And how do you find those things and distribute them? You know, there's a reason that weather forecasts today at the 10-day level are as good as weather forecasts when I was growing up at like the 2-day level, you know, like the accuracies match, right? It's because there's so much better data driving all of those models. And certainly the models themselves got better too. But, you know, you can take an imperfect model and kick it with good data and get much better. So I think about what can you do to close the data loop to set some nice learning cycle in motion.
Follow up on that a little bit. The trade between modeling of the environment and being able to predict things like day side, night side variation, you know, what do the winds look like? Those are global kinds of problems and challenges. But if you're a spacecraft, maybe you don't care about that. And maybe there's a local sensing challenge. Maybe a mass spec is the only way to go. But, you know, we think about, you know, in the early days of flying, I mean, we didn't have pitot tubes on airplanes when we first started flying airplanes. But now I think every airplane has one. What is the equivalent of a pitot tube, or what does that local sensing environment look like that we're going to include on every VLEO spacecraft? Because it's obviously the right answer. I don't know what that is today, but I think there is something like that that we need to go and figure out for VLEO.
Can you talk about your approach to using private investment to accelerate your efforts?
So we have a few partnerships with industry where both the government industry can bring expertise and resources to the problems. That's great. We also have a dedicated piece of the Small Business Administration for bringing SBIR dollars, Small Business Innovative Research dollars, out to small businesses. And there's a flavor of those that's dedicated for partnering with private money. And so the SBIR office can put in, depending on the flavor of these are TAC FIs and strat FIs. There's a matching, government puts in so much and the private industry will put in a matching amount. So those are pretty effective ways of getting larger dollar investments into areas that can take larger dollar investments. Of course, there are some problems where, you know, throwing infinite money at it's not going to fix it. So if, but there are certainly areas where more money would help. And for areas like that, those are pretty good tools. We also have CRADA's Cooperative Research Agreement and Data Development Agreement, where it's a contract vehicle, but no money changes hands. So both the government and the private partner will bring, you know, equivalent IP to the table, or infrastructure and data, or, you know, some sharing. And there's a bunch of different flavors of those that we can use to partner with private industry.
Yeah, I'll add on there. I think you know, it's an incredible opportunity to have Seth here in AFRL, because everything you just said is real and applied. Like, they are doing it and very effectively. For Redwire's part, we don't develop many of the technologies that come out of the labs that you all work with, or the companies you work with, but we do partner. So for us, we look to a lot of technology partnerships to find the right fit for our mission. And that's a form of attracting the private industry funding. But we also see ourselves, because we are such a strong mod and sim house, particularly in the VLEO domain, to serve as a bit of an incubator and connector for some of these companies who are, saying we're looking to differentiate ourselves in Earth observation, fire detection, or so forth. And we think VLEO might be helpful. And we will actually help walk them through trade studies and optimizations and connect them with industry, both from a technology perspective, but also with the U.S. government in context like Seth and AFRL here.
Yeah, and I think just to add a point, just to be clear, we're actively doing this, right? So through Department of Air Force, particularly places like AFWorks, SpaceWorks, we recently just had a VLEO call, right? For majority of topics, for NavNav, for propulsion, for sensing. We're already selecting applicants. There'll be future topics, so definitely look for those opportunities, right? If you have an idea, if you think you have value to bring, there's a pathway, right? So definitely feel free to connect with us to talk about that, and we can maybe talk about a way forward. But this isn't just talk. Dollars are already being put against this as we speak right now.
This is really fascinating. We are not alone in this race towards the LBOs. Who are our competitions today? And are they ahead of us? Are we behind? Or where are we in this race?
Do you mean that from a national perspective? I'll jump in with at least one recent observation, and this is public. China has been very vocal about jumping into very low Earth orbit. In fact, if I'm not mistaken, they just put up 2 demonstrator satellites, I think, in the last year or so. No, at least one of them has now successfully deorbited, and they're working on kind of their post briefs for those. When I look at it, you can see they're also in their message is that they're going to build 300 satellites to go fly in the regime. That's interesting to me because it's a message that we need to match pace with that, but that's not at all to suggest that the hard work's not being done. I think what's both unique to the United States and maybe a strength of the United States is that we do pull in such industry and private industry into these things. So we will have commercial companies coming to it. You could argue SpaceX has begun moving into VLEO. They're kind of at the top end of it, maybe arguable whether that's low LEO or VLEO. But I mentioned earlier we have a partnership with a commercial company out of LA right now that's moving into very low Earth orbit to deploy capability both for commercial and potentially government applications. So I think to put a pin in it, I think we are seeing near peers invest and make early demonstrator progress that I would sure like to see us catch up and out accelerate.
I think I'll say that we're not in a terrible place. We have capability out in industry and investment coming in there. There's a decent amount of lab capacity across the Department of Defense labs, DOE labs, with infrastructure to come help. I think the VLEO wind tunnel that we've been talking about, that's a pretty hard problem, and it'd be great to push harder on that and get that moving faster. But we're in a pretty good place where we have a lot of potential and some investment to come and help. We're not in the situation where hey, if somebody came in and wanted to move a ton of money into this area, we'd be flat on our heels. We're moving forward, and I think that the same things that we see about the advantages of VLEO are going to become obvious to everyone else. Everyone else can see the same physics and see the same, gosh, it'd be great if I was closer. So I don't think we're unique and we've discovered oh my gosh, 1/r². I think that everyone else sees that too. And maybe we'll be the first to really operationalize it. But it's not going to be just us.
If I just follow up, then just a quick follow up to that. Where is Space Force in all of this?
So from the Air Force Research Laboratory, and we support the Space Force. We have both the Air Force and Space Force as transition customers for the tech that we develop. We are investing in VLEO with partners to go and help push whole systems and component tech forward for this. There is no program office in Space Force. There is no VLEO program office and sitting around somewhere that's going to proliferate an Air Force or Space Force VLEO constellation yet. I tell people that that's fine. That's not how things start. The initial beginnings of a thing are not a program office springs out from from the earth. That's not where they come from. They come from the labs and industry bringing things forward, and that's where we are in this stage. And as that matures, I can imagine that there will be there are several applications that would be done better from VLEO if we can open up the domain for it.
Thanks everyone for your perspectives. I just want to bring elephant in the room here. When we talk about VLEO, and everyone point out about the power requirement, right? So granted, there are challenges in electric propulsion through air breathing, but it probably will be solved. But at the same time, it all will rely on available power. So can you comment on how you see this effort can go in parallel or in concert with developing electric propulsion devices, etc.?
I think you're just asking, how do I get loads more power without so much drag? Is that the question?
And what kind of power sources? Maybe you have to think about something out of box, because that's vicious cycle, maybe not so easy to break.
So let's tackle that like from a high level. I want power. The sun is there. That is a default option. That's the local generation. If I otherwise wanted to generate power locally, I think the other option is, I can't think of one besides nuclear. And that is quite challenging because there's a lot of regulatory issues to get nuclear power up at all. And then VLEO is often a place where you think about going up to because you have a smaller, cheaper satellite. So nuclear reactor is not the first thing that leaps into my skull. Alternately, maybe you can decouple local power. Maybe you can transmit power to your device. That also presents some significant challenges. If you look at RF power transmission, many of these vehicles might be relatively small because we're trying to make them rather aerodynamic. So maybe the amount of collection aperture is going to be limited. Think about optical power transmission. That certainly is amenable to more focused transmission, right? But and it might even be compatible with your photovoltaics. You might get dual band. You might even focus on a laser transmission energy. But in the VLEO environment, you go up from the ground, you're going to pass over within a, say, 30-degree, half angle in maybe 30 seconds. So now you're starting to think about an awful lot of ground stations to put up that power if you're like rapid charging your satellite instead of aiming at the sun. And like a lot. So think about maybe, again, toy model. It's the best you could do. Well, ground tracks go up and down in latitude, right? So I'll play God and paint ground stations along like the Tropic of Cancer and the Tropic of Capricorn, right? Or pick your altitude. Like, you have infinite money. You've just all the time. Now you're getting 2 30-second transmissions per 90-minute orbit. So you got a % duty cycle. Compared to the sun, which I can get at like 80% duty cycle in a sun sink orbit, I'm now looking at like 100 kilowatt versus to a square meter versus just 1 kilowatt per square meter from the sun. So optical transmission is probably hard from the ground. Maybe there's a way to do it from somewhere else and they like higher up, you go high to low. But now I'm talking about a hard problem on the ground because ground stations are expensive to make all those high power things. And now I'm going to put those expensive things onto a bunch of spacecraft and make more expensive spacecraft when my goal was cheaper spacecraft. So all these things kind of make it hard for me to picture the alternative to vanilla solar. So now I'm like, maybe can I do like strawberry solar? Can I do chocolate solar? Can I do like flexible, roll it out solar? Or maybe like you remember Batman Begins when Batman like flicks out his little cape and it's got the memory. I'm like, oh man, why can't I do that with my solar panels? And when I'm, the Earth is like Santa. It's a little bit fatter in the middle. And so when you go in a circular orbit, you're about 10 kilometers different in altitude above the dirt on the poles versus the equator. Maybe when you're a little higher and you got a little bit less drag, you could flick out your solar and collect a whole bunch and then be ready as you're going in to the depths. But that's when I think about how do I get a lot more power, I start to think, A, maybe I do clever things with my solar, or B, maybe I think about consumable fuels that are just heavy. So I get higher thrust to power and I don't need as much power to begin with to do the drag makeup. So that's where maybe that's someday electrospray type things that get very high thrust to power. Maybe that's someday like the heavy solid metal propellants like a bismuth kind of thing. But those are maybe the two angles that come to mind where maybe you could get some margin there.
I think I'll throw in there. I think that we're only going to learn more about how to do the flying of things in VLEO, and it's not going to look like how we fly things in space. In power is a big piece of the problem. Like where when I'm in the portion of my orbit where I get the most power, okay, that's great. Is that the same as the portion of the orbit where I'd like to be propulsing the most? Maybe, maybe not. So how do I think about when I should be propulsing? Maybe it's all the time, but maybe there's some areas where I need to turn the dial up to 11. How do I operate my vehicle in an intelligent way in VLEO? We don't really know the answer to that yet. And a big chunk of that depends on the environment, which of course we do not understand well yet. So what does that drag environment look like, both from a drag that I need to make up with thrust, but also from a constituent perspective? Am I seeing a lot of atomic? Maybe I tuned my thruster or my collection system to operate on oxygen. Great. Maybe I'm dipping lower and I'm getting nitrogen too. Okay, well, do I have another set point or something like that to tune my propulsion system for that? We're going to learn a lot about how you fly in VLEO, and I don't think brute force is going to be the answer. I think there's going to be a lot of finesse in how you fly in VLEO.
Thank you so much for your perspective. Quick question about the VLEO environment. So I have two questions. Number one is, what's your view on the changing of neutral density in the VLEO environment with time, and how do we adapt to that? Do we need to look into artificial intelligence in that case? And the other thing is, let's say, as you mentioned about the radiation environment being benign, what about like protons up there or like neutrinos or neutrons? Do they cause any damage to your spacecrafts? Do you have issues of that? So what's your perspective on that?
So I guess speaking to the first part, I think AI is nice, but I think sometimes it's a little bit of a buzzword, but we tend to throw it at everything. There's some interesting work, right? But I think the problem, right, is it's a system in a plant control problem, right? What's the plant, right? So what are you training your AI model on? If it is on a empirical model with a bunch of fitted constants, and then you try to apply it to physics that you don't understand, and you expect the AI model to get it right, I would think that'd be a little bit challenging, right? So I think if it goes from the approach of actually trying to train it on physics and it's actually recognizing actual signatures, I'm all for it. But I think just trying to AI brute force it when you don't even know what the tuning constants are based on, it could be catching a signature and optimizing for something that's not even real. And then you try to fly based on that, and you're wondering why you're dropping out of the sky. It's not to say it can't be done. There's definitely some people in the literature doing it. We've talked to different professors that are working on it. We've had those engagements. It's just non-trivial because already right now, right, the average model is 30% left or right. You look at the literature, even looking at Goche, which had a gravimeter that was like 10 to the minus 14 meters per second square of accuracy for acceleration. So crazy level accurate. When they try to back that out and turn it to neutral density, the numbers compared to the models can be wildly off, 50% off, 30% off, right? So what's the baseline for your training? And by the way, that's only one flight experiment that flew at one orbital shell and one inclination. We don't even have the data to really even confidently train, right? Because most of the AI problem is data, right? So can we lean on it? Yeah. I don't see it happening in the near term without more set points.
Last question.
So there's I think a very strong science case from either a space science or space weather perspective to make simultaneous neutral plasma measurements below like 300 kilometers. So my question is, has there been any engagement from NASA or any discussion of NASA DoD partnerships or any interest in that quite yet?
We've had a few discussions. I don't think we have any full going partnerships with the civil space side currently that I'm thinking, but we are certainly open to it, and of course we partner with NASA on all kinds of things. So
I can speak more to it a little bit. So I will say that in my current thing as branch technical advisor, reach out to NASA quite a bit to talk about what they do for the state of science. I think right now the bigger issue is when it comes to defense application versus civil application, the need sets are different, right? My need for tactical or operational science is not the same for research science. So we have talks. We've talked about things like, the INMS, flying that out, right? But do you really want to fly this, $10 million instrument that has a very nice filament that would happen to break when it hits AO? Or is it maybe not super rugged? Do you want to fly something like a GUVI, right? Which was massive and huge and give you amazing science, but then limits my payload capability for mission, right? So I think there's conversations that will continue. Right now, it's hard just finding that nice marry point of how do I get the most bang for my buck sciencely, but still get the mission done, right? Because it should be mission first, delivering capability to the warfighter first. So I think finding a place that we meet will happen, but it's going to take some continued conversation.
I would just add that, in our engagements with both the government, civil defense, and then commercial partners, there is an interest to find a way to get sensors there. There are, of course, various offices throughout the U.S. government that are interested in the data, maybe not put $1 billion into a constellation level of interest, but there are certainly commercial companies who are kind of saying, I'm going there now and I've got some swap available. Is there something we can work out? And I think that kind of talks to Marlin's trade space right there. So I think some of those conversations are happening, including the commercial industry. We just have to land it.
I'm just going to add that there was a question earlier about, are we going fast enough? And it was kind of outward facing relative to adversaries. There was a question about private investment. Then there's this question about science. And, I think about this a little bit more, not as, are we going as fast as someone else, but are we going as fast as we could be? If you sat down and decided that you really wanted to make this a priority and from a clean sheet just said, from first principles, what would you then do? I think that, like Spence said, there are a lot of folks who are thinking about going up into this regime now. There are a lot of folks who aren't, but they're going to put spacecraft up that will eventually end their lives going through this regime also, where you could potentially get some data. And there are lots of folks who would love to make sensors and get them into space, and get this kind of data, but that lack the connection to make it happen. So this is ultimately a coordination problem. I think about, how would you set up a marketplace of folks going to an environment where they say, I have a kilogram or 5 extra watts or so many bips of bandwidth that I could spare. And someone else saying, well, I've made a stone soup of all these different, diagnostic pieces, and I'm still trying to find the ride to do that matchmaking. And there's certainly things like that in rideshare right now already. And I had not really thought about it to this point, but I feel like what would that structure look like that let you play matchmaker? Because in a world where we are so data starved, I'm hesitant to, let perishable goods like payload and swap to orbit and people with sensors that might be ready, or even if they're not ready, we could find out precisely the manner in which they weren't ready when they fail, to sacrifice that kind of information.
All right, that's great. Thank you all so much for your talks and for this panel session, and thanks to folks here and online for participating in this part of our workshop. We're going to take a 15-minute break, and then we're going to reconvene with our second session, which is on technical challenges and opportunities for advancement. Please join me in thanking this group of speakers.
How many people have had fun so far? I think it's going great. Thank you for your participation. So to keep up with this great discussion, now we turn to academia. And our first presenter is Felipe Guzman, and he is the Jack Lee Jewell Endowed Chair in Optical Sciences, Professor of Optical Sciences and Physics, University of Arizona. And I have learned a lot from Felipe when it comes to sensing. So I am sure you're going to tell us a lot about sensing. So thank you, Felipe. 15 minutes. I'll give you.
Thank you very much, Yvette, for the introduction, also for the invitation to be here. This is great. So yeah, I will be talking to you about some of the thoughts we've been having in discussions in my group, and also some of the technologies we've been working on over the past few years. Just a very brief introduction of my lab. I direct the Laboratory of Space Systems and Optomechanics at the Hawaiian College of Optical Sciences in Arizona. We focus on optical and optomechanical technologies, mostly for inertial sensing. A lot of the technologies that we do are also related to space missions, related to gravitational physics, such as GRACE, LISA. LISA is gravitational waves. GRACE is for geodesy. Geodesy is also related to a mission that was alluded before, GOCHE. We do work on some quantum technologies and so on, but I will be focusing mostly on optomechanical sensors for inertial sensing, laser systems, intersatellite laser links, and so on. So operationalizing requires sensing and instrumentation. That basically means we need instruments and capabilities to characterize what's the environment going to be. What's, for example, precision orbit determination, where we're going to be flying. How is this orbit and their characteristics changing as the altitude changes over time? Understanding the phenomena that impacts those effects, dynamics, space weather, drag, some atmospheric, solar, and aero-optical effects, and how that impact the performance of whatever mission we're flying, but also the instruments that we're flying in those satellites. So we need highly sensitive instruments, but as it was mentioned before, also very low C-swap, cost, size, weight, and power. That's basically what makes it possible to fly multiple satellites, constellations, giving us the capabilities to make these observations, not just for characterization, but also for operations. A key thing that I've noticed over the years is that there's not a silver bullet here. So we're going to need to focusing on sensor fusion, multi-physics sensing, combining optimally multiple sensing capabilities and physics concepts to achieve the goals of whatever mission. I will be concentrating in these points here: positioning, navigation, and timing. And one example from my group is what we call ODIN, which is an optomechanical distributed instrument for inertial sensing and navigation. So regarding intersatellite laser links, this is something that has already been demonstrated in the GRACE missions. GRACE follow-on is a constellation of 2 spacecraft separated by about 200 kilometers, sharing a bidirectional laser link to conduct nanometer level displacement sensing between those 2 spacecraft. Now, the attitude control requirements for such a mission are extreme. So for many applications, you don't need that level of attitude control. You don't need that level of displacement sensing, but you do need an operational laser link between multiple spacecraft at baselines, that can be varying between tens of kilometers to hundreds of kilometers. And you can do those for sensing, for metrology, or for communications. Now, particularly for communications, having a bidirectional laser link is very interesting because it makes communication not just fast, making use of the bandwidth that the light offers you, but also making the communication very secure. If you don't have a sensor intercepting that laser link, you're not going to be able to collect the information that is being transmitted. So that is very useful. Now, you can also fly, and you also need for positioning, timing, and navigation, very high precision optical clocks. So we are, for example, in our lab testing currently hollow core fibers that are filled with iodine gas such that we can stabilize optical systems, lasers, to transitions of iodine in order to get timing better than parts in 10 to the 12 over thousands of seconds. So that kind of gives you a time reference that you can then transfer through your multiple spacecraft to do PNT effectively. Now, let me move on to optomechanics and inertial sensing in this case. So over the years, we've also been working on optomechanical inertial sensors, accelerometers effectively. And this has been work mostly funded by NASA. We have had from the Earth Science and Technology Office, ESTO, an IIP grant and also an ongoing INVEST grant to develop triaxial systems of linear accelerometers and also full operational gyro-free IMUs. Now, IMUs based on linear accelerometers are very well known. You can find papers that go over decades, but certainly they were over this time period kind of discarded because of the poor performance of the linear accelerometers. At this point, given the sensitivity that we're reaching, it becomes very interesting to look at these assemblies of linear accelerometers for inertial sensing. This is how Odin came up. We proposed this array of linear accelerometers to be flown under the INVEST program of ESTO. It's going to be launched in February 2027. So if you look at the sensitivities that we're striving here, we're looking effectively at 10 to the minus 10, 10 to the minus 11 meters per second squared per hertz at very low frequencies. That's the sensitivities that you need to even do gravitational characterization. For example, the Gauge emission that was mentioned earlier that achieves something of the order of 10 to minus 12. Now, the form factor of these accelerometers is significantly more compact. They're primarily passive because it's effectively just glass ceramics constituting the mechanical resonators. We do have laser systems, monitoring the displacement of the test masses exquisitely. And something that when we were doing this work, realized that it was very interesting is the fact that the combination of these exquisitely performing linear accelerometers gives you much better attitude sensitivity than what the current fiber gyros provide. So here, for example, in purple, you see the sensitivity of the current fiber gyro flying on Grace follow-on as we speak. What we expect to achieve is orders of magnitude better attitude sensitivity in order to do that. So earlier on in the discussion, we alluded a lot to the capabilities of actuators such as thrusters. But we do need systems that are capable of sensing to that level, ideally better. So those thrusters and those actuators can perform as needed. If we don't know what we need to achieve, what's our target, we're not going to be able to accomplish it. So this system was selected under the INVEST program 23. We're going to fly it in 27. Here, this gives you a comparative chart of the performance that we've been able to demonstrate in the lab. This blue trace is what we measure in the lab compared to the target sensitivity we're aiming for to demonstrate in orbit with Odin. These dashed lines here are the accelerometers on board of Grace follow-on. Now, something that I want to mention here is that, for example, accelerometers performing at this level are typically free-flying test masses. They're suspended, and of course, their range of motion is limited because of that particular fact. Now, the way these systems are developed, they're fully monolithic. They're mechanical resonators etched out of a single wafer of material, giving you basically a full physical connection to the frame and capable also of withstanding significantly higher forces. So this type of accelerometer that we have here tested can also withstand acceleration levels all the way up to a G, giving you the sensitivity that you can see here. So that basically translates to sensitivity levels of pico-G, about 10 pico-G over at frequencies above 60 millihertz. So that is exquisite for such a form factor. The way we've been testing this over the past few years is here, and this is kind of giving you an idea of how this technology has been developing and the sensitivities and the phenomena that we can observe with this. We have our little test mass in the vacuum chamber. one of our little optical heads sensing the motion of the test mass. Everything is in a optical breadboard. There's a lot of optomechanics here. All of this has now been replaced by our own made fiber injectors and mechanics. Everything resides in the in the vacuum chamber on top of an optical table. We procured a seismometer to monitor environmental effects, just as a comparison, not as a calibration. And then we just measured. Now we conducted characterizations of the systems, determining we should be able, and we are able to meet this kind of noise floor. But when we go ahead and do a free running measurement, we meet noise levels that are several orders of magnitude higher than what we need to be. We were scratching our heads a little bit for a while, trying to understand this. And what we realized is that we continue to observe this structure here that is called a microseism. This is an actual geophysical effect. We compared then against the data of our seismometer, and they line up almost perfectly, certainly above 100 millihertz. They deviate a little bit towards lower frequencies, mostly because of systematics between the two systems. And what this microseism effect is that, well, our lab is in Tucson, Arizona, about 150 miles away from the coast of the Gulf of California. If you're sitting at the beach, looking at the water, you can see the waves coming and crashing at the beach, recoiling, and coming again, crashing at the beach. And they do that with a periodicity of about 1 to 10 seconds, which is exactly this. So that is kind of the acoustic waves propagating through the landmass all the way to our basement lab in Tucson, moving our little test mass. And it's such a strong signal that is actually dominating the entire spectrum. So this is one of the reasons why we were awarded the INVEST program to actually test the sensitivity of these devices in orbit. Again, regardless of operating under a bias acceleration that is larger. So other important effects that we can measure and what these technologies are useful in low Earth orbit is looking at variations of the gravity field, either temporary and also looking at the static gravity field. Gravity gives us a map that is useful for inertial navigation. If we're looking at operationalizing low Earth orbit and also navigating in GPS-denied environment, we need an idea of what that gravity map looks like at various orbits. That's something that needs to be characterized. That is something that for other purposes, the missions like Goche and Grace have been conducting over the past 2 decades. Other effects that have been mentioned in the workshop earlier in the session was, for example, measuring thermospheric neutral density, characterizing drag, albedo, the Earth energy imbalance. All of that gives you also effectively differential forces that you can characterize a low Earth orbit. And for that, you need inertial sensors with exquisite sensitivity, combined, of course, again, with other effects that you can measure with ancillary instrumentation. Certainly, these type of systems can also be used for characterizing effects of micrometeorites, spacecraft vibrations, and so on. Lastly, I want to just acknowledge the work of my team, and I will be happy to take any questions. Thanks, Yvette.
Yeah, so quick question, right? So can you speak to the thermal stability of accelerometer, right? Because at least from a lot of the studies, the accelerometers are often better measurements of temperature than they are force themselves. So, can you speak to that at all, or have you done any research on how this responds to changes in temperature?
Yeah, no, certainly. I can speak to that, and I have some backup slides. I couldn't mention all what comes into that. So a lot of what the effect of, well, temperature is going to be dominant regardless in any highly sensitive instrument, right? The way we deal with this is that this glass ceramics that we use, this is effectively fused silica. It has a very low CTE, so that gives you some lower sensitivity to temperature effects. Now, what happens is that when you have temperature fluctuations, your displacement sensor is going to be changing. So it's going to be observing displacement that isn't there. It's just apparent because of the temperature changes. So what we do here is we do a dual interferometer approach. where we have a reference system, a reference interferometer, a measurement interferometer, and differentially, that measurement kind of cancels out the effect of temperature. Now, that doesn't take out the thermal expansion of the material itself, but certainly then if you incorporate, and you will likely incorporate also temperature sensors in your spacecraft or in your environment, then you can do computations and correlations to estimate what's that effect. Now, so far, we've done modeling of these effects and also some measurements in the lab, and we've characterized the sensitivity of our systems to temperature to be in the order of 1 picometer per Kelvin. So they're fairly small overall because of this differential measurement.
I heard you mention a G spec at one point, but how hard can I shake something like this before I break it?
Well, so certainly this is going to fly. We're going to launch, so we're going to put this in a shaker to make sure that it survives. It depends on how you want to do that. So look at this mechanical resonator here. What happens is that if you imprint an external force, this test mass is going to wiggle back and forth. If you shake it too hard, the test mass is going to hit the edges. This gap is designed to be such that when the test mass reaches the edge, it corresponds to accelerations of about 1g. Now, certainly during launch, you're going to experience significantly higher accelerations. For that, you're simply just going to have to incorporate launch locks for that test mass, which we certainly have in order to deploy, well, to survive launch. These launch locks can also recage the test masses if needed during flight and release them again. So that's an advantage. They're piezoelectric, so the power consumption is fairly low. Voltage requirements are also fairly low. They're about in 10 volts. So the range of motion is overall not large. For operations in environments like GRACE, where that's the primary focus of this NASA development, we're expecting accelerations in the order of 10 to minus 4 meters per second squared. So the displacement of the test mass is going to be nanometers. But, at lower orbits, that test mass is going to be moving maybe tens of microns, perhaps even a millimeter. And that's still fine because the heterodyne interferometer that we're using can track that over, a range of meters even. So that shouldn't be a problem.
Can you just talk about whether the compute challenges of sensor fusion have actually raised their ugly head in terms of flying these missions?
So yes, so attempts are being made at the moment. For example, perhaps you've heard of the CAL project at NASA, so that the Cold Atom Lab on the ISS. There are some, that's effectively an atom interferometer measuring very high sensitivity accelerations at low frequencies. Now, the problem is that vibrations, particularly vibrations on the ISS, will imprint phase noise on the matter cloud, and on the matter cloud really, and that adds noise. So something we've actually been working with the atom interferometry community is to incorporate systems like this one, where this is part of the optical system of the atom interferometer. So then you have a hybrid system. You have a sensor that can measure high frequency accelerations, high frequency vibrations with very high sensitivity. And then you have the atom interferometer that can focus on the lower end of the spectrum. Now, that is maybe a very specific case on inertial sensing, but let's focus perhaps on navigation. So you want to do GPS denied navigation. You typically would like to go for inertial sensing. For that, you need a very accurate map of what the gravity field looks like in that area. But if you combine that with magnetic sensors, you can sort of roughly tell where north is. Now, that's not very precise because, in cities or in other environments, the magnetic environment is very polluted. So you're not going to get precision out of that. but you're going to get a good idea of where you're going. And then inertial will tell you exactly where you are. If you combine those two, then you achieve that higher performance. Thanks so much.
Our next speaker is Ian Boyd. He is the director of Center for National Security Initiatives, and he is also the H.T. Sears Memorial Professor of Aerospace at our friendly companion UC Boulder. We love UC Boulder. So
That's great to hear. I love it too. Yeah, so thank you to the committee here for this opportunity. I think it's a very important topic. You know, I think we've already heard we're kind of at the nascent stage, even though Corona was done a long time ago, right? We're kind of at this nascent stage of figuring out, you know, what can be done and how to do things in VLEO. And so I was asked to talk mostly about aerodynamics and modeling. And so if we could go to the next slide. This is the one slide to rule them all. I'm just going to talk about this. And I want to assure the government people and actually the Redwire people, if they're still here, this vehicle shape is something we made up ourselves. Okay, so it's some generic, probably not actually a very good design, doesn't matter. It's really just to illustrate a number of points. So, so this is a vehicle flying at about 200 kilometers. And what we're looking at there is the density field of atomic oxygen around the vehicle. It's a little bit hard to see, but on the vehicle surface itself, we're showing pressure. So the pressure would be contributing to figuring out the drag. So in this regime, you use a very specific type of computational model based on Monte Carlo techniques. We use this instead of solving like computational fluid dynamics, conservation equations, because of this parameter lambda. So lambda is many different things in different fields, but here lambda is the mean free path. It's the average distance that an individual molecule or atom travels between collisions. Okay, so up in VLEO, you know, the molecules travel, in this case, hundreds of meters before they experience another collision. And in this simulation, that vehicle, let's say, is 10 meters in length. Okay, and so essentially, there's no, right in this picture, the ambient molecules and atoms are not colliding with each other. If the spacecraft isn't there, they're just, you know, they're just ballistic, or well, actually, they're just sitting there, right? But in the frame of sitting on the vehicle, you know, there are very few collisions going on. And so in that regime, this is what we call a rarefied gas. And it's a super rarefied gas. And so then there is a couple of different techniques have been developed for many, many years based on Monte Carlo methods to analyze these kinds of flows. So we're actually in good shape for doing the aerodynamics of VLEO vehicles. You can see that this is a three-dimensional vehicle, so we can do very complicated configurations. I don't know how well you can see it, but there's an inlet there that has quite a complicated geometry to it. And in this particular simulation here, we haven't modeled a propulsion system, but we absolutely could, right? So we could be gathering, so air breathing, right? Breathing in air through that inlet on the front of the vehicle. There's some kind of internal pipe work to get that gas to a thruster. And we accelerate that gas in some way, whether it's a Hall thruster or some other system out the back, right, to cruise along in VLEO. Okay, so we have a good capability, and by we I mean the community, right? This is an example from one of our codes, but these codes exist. So then, you know, what makes a good simulation, right? It's the information you put into the code. And so there's certainly been some discussion about this already, but you know, arguably the most important physical phenomenon that we have to try and simulate is gas surface interaction. How does an individual oxygen atom interact with the surface of one of these spacecraft? Right? We're interested in that more than anything else, or it's the first thing we're interested in, because atom by atom, molecule by molecule, this is how the drag force is generated. Okay. And so there are models for gas surface interactions, of course. Part of the challenge is, though, that the way different materials respond to different gases, different atoms and molecules, is different, right? And so we need material-specific information. There's a couple of kind of extreme cases of gas surface interaction. So the first one is what's called specular reflection. So specular reflection is like a light ray bouncing off a mirror, right? The incident reflected angles are the same. So an atom comes in, hits the surface, and reflects off. It doesn't undergo any momentum change parallel to the surface. And so you could imagine on any vehicle, but on this one, you'd kind of like the purple surfaces there to be specular, because that means there's not going to be any what we call shear force. There's going to be no drag due to momentum change, sort of parallel to the surface of that part of the vehicle. The other extreme for gas surface interaction is something called diffuse reflection. So in diffuse reflection, an atom comes into the surface and loses all memory of what it was doing beforehand and kind of just plops off the surface. It reflects with a velocity of a few hundred meters per second, probably. And in that process, then there's a lot of momentum change that happens to that atom, and so it transfers that to the vehicle. And so you would like to avoid having diffuse reflection on the purple surfaces. So like a lot of spacecraft designs, it turns out you would want to have different properties of the materials on different parts, different components of the vehicle like this. You'd like some surfaces to be specular. You'd like other surfaces to be diffuse, right? And so that's part of perhaps the design of an efficient VLEO vehicle system. I think the two speakers after me are going to talk much more about propulsion. I don't actually know what they're going to talk about, but they may be talking about air breathing, right? Or they may not. And I asked a question earlier about, VLEO is more than one thing, right? If you only want to be up there, maybe it's a little bit like the Corona example that Spence Wise mentioned. If you only want to be up there, for a little while, a rapid turn, emergency need for something in VLEO, would you take, maybe you would just take your own propellant with you, right? Don't worry about air breathing, right? So it's not, it's not a foregone conclusion that you would want to do air breathing, but you might. Another aspect of things for the propulsion is, okay, you can collect air, but maybe it's not, you don't get it to the right density that you need for or pressure for your particular thruster system. Right. So do you need additional, machinery like pumps and things like that? Maybe, maybe not. And acceleration, right? So I think Mike McDonald said this, but it's so true, right? Which is in air-breathing electric propulsion. If you're sitting on the spacecraft, what air there is coming at you at 8 kilometers per second, and what you're going to do is slow it down to 0 and then re-accelerate it again. Right? That seems to be a really inefficient way of doing things, right? So maybe there's different approaches to the acceleration. There are a lot of, like any spacecraft or complicated system, there are a lot of things to think about here in terms of optimizing the system. I mean, the geometry, the propulsion, the power generation, with solar cells or with some other means. The selection of different materials on different surfaces of the system. And then the concept of operations, right? How you're actually going to run this thing. These would all fit in to optimization. We have the tools to do these kinds of things, but there are a couple of major uncertainties that, again, have been discussed so far this morning. That I want to spend a little bit more time on, right? So I would say, we have great computational simulation capabilities, right? We can do the drag, we can do the propulsion system, we can do everything, right? But what do we not know, right? And there's two key things that we don't know, at least. So one is the atmospheric properties, right? So we've had some discussion about this already this morning. People tend to think of this in terms of space weather, but to me, it's not space weather, right? A lot of people think of space weather as being a rare, cataclysmic event, right? There's a big mass coronal ejection from the sun, and it kills all our satellites and brings down the electric grid, right? Here, it's much more, the challenge is much more like terrestrial weather, right? It's the day-to-day variation in the same spot, right? Today, there's a little bit of rain here, right? Tomorrow, maybe there's not, right? Today, it's 77 degrees. Tomorrow, it's 85 degrees. It's more that, it's the variation, you know, around your orbit on a day-to-day basis that changes over time. Now, if you had a, you know, a mass coronal event, that would also be bad. That would just add to it. But forget that, right? Just knowing what the conditions are is very, very challenging. And we've had a little bit of discussion about models, and models are important. But again, I would say, think about it in terms of terrestrial weather, right? Nobody can model the weather from first principles, right? There's a whole bunch of data goes into the system, and actually what we do is forecast things, right? And push the weather forward to a little, you know, a little bit further in time, and then ingest a lot of data, push it forward in time. That's the ideal for VLEO, right? We are not going to get to that point anytime soon. And so what does that mean? It means there's a tremendous amount of uncertainty, right? The drag is linearly proportional to the density of where you are, right? And so if there's a plus or minus 30% variation in density, and actually it's much worse than that, you know, in a given spot in VLEO, then you have to build that into your system. And, you know, DARPA is doing this otter program. You know, you'll have heard of DARPA hard. This is hard, right? And built on top of the hard is a need for a lot of margin in the design. Because one day you're flying nominal, you know, 2 orbits later, the density just went up by a factor of 2, right? And you have to be able to account for that in the concept of operations and the way you design a vehicle and so on. And, you know, it's not just the density that's varying, it's the chemical composition as well. So if you're air breathing and your thruster relies on a certain mixture of nitrogen and oxygen and maybe some other things, and that changes, you know, how much does that degrade the performance of your propulsion system, right? And so, so I think these are interesting challenges. And I think the near-term solution is, again, has been discussed here, is to have a lot of instrumentation, as much instrumentation as you can. You know, because it's not about measuring, you know, the density at 200 kilometers directly above here, and then now we know what the density is there, right? All we know is the density on the day and the time that it was measured, right? What we actually need to know are the variations. I you know, live in Boulder, work in Boulder, and NOAA has its Space Weather Operational Center in Boulder. So we went to visit them a few months ago, and the lady in charge was saying that, you know, she gets calls in the middle of the night from SpaceX saying, is it okay to launch today? You know, because they had a bad experience. I don't know if you heard about that. And she doesn't know. I mean, she's the expert in the whole country, right? And she is not willing to give them a yes or no, right? It's hard, you know, we're data deprived, and for VLEO vehicle and mission design, what it means, I think, is you have to build in a lot of margin into the design. The other aspect I'll talk about there, material time evolution, right? So I talked about, it would be super nice to have very smooth specular materials kind of on the purple, you know, sides of the cylinder of that vehicle, right? And so people are working on those kinds of materials and coatings and so on, and seeing some very interesting specular-like behavior. You know, one of the key questions, though, is, okay, on day 1 of my mission, it was specular, right? After I've whizzed around the Earth in a pretty challenging environment, you know, do I remain specular, right? Almost certainly not. I mean, if you've ever seen any materials that have come back from LEO, they are, you know, they've been through the works, right? And so again, the degradation of materials over time is not well known. Mike McDonald again talked about facilities, right? So we don't, thank you. We, you know, we're putting together facilities that might be able to get close to exposing materials for the equivalent of a year of flight time in VLEO, right? But we did not have that capacity today. And so, So I guess my bottom line message here is, yes, we have simulation tools. They can be used and exercised to design and optimize VLEO vehicles, but there are some uncertainties that I don't think are going to get drilled down, anytime soon. And so we need to have, a lot of margin in the design. Thank you.
Continuing on, yes, Ian was right that the next speakers are propulsion. And the third speaker is Mitch Walker he is the William R.T. Oakes Junior School Chair at the Daniel Guggenheim School of Aerospace Engineering at our other friendly Department of Aerospace at Georgia Tech. So
good morning still. Great to see everyone, and I've been waiting to give this presentation. There are a lot of great things going on in VLEO, but there are also some things that we do need to talk about. So I'll try to add some interesting things to the conversation that we have not discussed, and of course, I hope you'll ask some great questions during the panel session. So this activity in VLEO is not new, as they opened up with. It's been around for many, many years, but there was kind of a resurgence that started in the 2010 area, and NASA funded something from NIAC that Busick worked on about air breathing. Of course, NASA probably had some ideas about going around Mars, but you could see that some of the problems were going to be the same. In 2018, things really kicked off in the EP world, and that's when ESA came out and said, hey, I show a picture down here, and we've got a Hall thruster, it runs on air, VLEO's here, any day it's going to happen. Now, if you actually dig in and start to dig into that experiment, as these stunts go, there was nitrogen and oxygen involved, and they turned it on and it glowed. But at the same time, the Air Force took notice and began to fund the universities in the US to start doing this work. AFOSR took off on some stuff, AFRL did an award, and most recently, we've seen all the activity at DARPA. The DARPA stuff has been interesting because now you've got a lot of different teams going and stumbling in and documenting and starting to quantify some of the real problems that we thought were interesting, but were not. So Charge Harmony, there are a suite of universities in the US working on a number of different approaches to do this. The Auto Award is clearly working on a number of different EP suppliers to do this as well. And of course, there are some things that have come out as STTRs. In addition, the rest of the world is also working on this. So there are mentions of Japan and China and India. They're all starting to spool up this capability. What has become a lot of fun now is that there's actually a lot of private industrial investment for both historic EP suppliers, Busick, Phase 4, but also some new ones from Viridian and New Orbit all around the world. Most of these folks are either from a government organization and have gone off and spun off a company. So they, for the most part, know what they're doing, and I'm interested to see what will come out in the public literature. Can I get the next slide? Perfect. I did want to spend just a quick second to understand or at least discuss why we're so interested and why is electric propulsion part of this VLEO discussion. Well, my assumption is that if you're going to do VLEO, that you're going to use the propellant that is there that looks something like air. There are versions of this where you would take your favorite propellant with you, be it condensable, whatever. My assumption for this presentation will be that we're going to do something with air. And if that is the case, air, for the most part, has no energy to do any of the acceleration required. So you need to inject some energy in. And EP is a very natural way to take all of the solar power there, stick it in the propellant, and accelerate it. For the most part, we have three basic ways of doing that. I'll quickly talk about them. We have electrothermal, which is a hairdryer technology. There's a group working on an electrothermal air breathing thruster. We have electrostatic, which is Hall thrusters and gridded ion engines. There are many groups that are trying to pour air through these devices in some way. And of course, you have the electromagnetics where we've got MPD thrusters. I know there's a group doing that. And there are groups that are working on RF versions, helicons, and anything else you'd like to pick out in there. They will all work. The question is, what are the challenges? Are you going to get the performance required to do the mission of interest? Right now, the mission of interest is murky. It's murky. And so the requirements are not perfectly set there. And I heard someone talk about that today. But nonetheless, EP will probably be part of the VLEO solution. All right. I wanted to quickly talk about the systems that are involved. The systems that are involved with doing this with electric propulsion. On the top, I show basically the schematic for power. I'll assume that someone sorted out how we get the power. Power processing gets interesting, right? Is it going to be a pulse system? Is it going to be a DC system? Is it going to be an RF system? All that's still on the table. That power processing exists. It has not been developed for the application of air breathing EP. So I think that should be something as we move forward, that should be moving along in the background to keep up with us. On the far right, you see the accelerator, definitely question marks around what we'll do there. But on the bottom is what makes it exciting. Historically, we've had propellant in a tank. We know what it is. We know what it'll be today. We know it'll be tomorrow. We know it'll be a year from now. That will change with air breathing. The mass flow system, there are lots of questions there about how you're going to collect this gas, compress the gas, feed the gas. All that's still on the table. So it's a lot of engineering challenges there. But I was asked to talk about physics challenges, and I was asked to talk about possibly engineering challenges. So I'll try to break these apart. The biggest physics challenge is around ionizing and accelerating the air. And I'm going to talk about from what we know how to do to what we're being asked or want to do. We have spent all of our time ionizing atoms, inert atoms at that. And so it was a big molecule. We understood it very well. And no matter how sloppy or how little we knew about that propellant, we always got a xenon ion or we got a krypton ion. In this new world where we have a bunch of constituents in there that have a lot of different ionization energies and they can dissociate in different energies, we are going into a realm where we'll be ionizing a soup. And we would like to understand what ions are going to come out of that soup. What's interesting also is that these particles are probably going to dissociate before they ionize. So now we're going to have these little atomic species running around. And it's not clear which one we should try to accelerate. Right? We're going to just have a soup of ions. Where should we focus our energies? In addition, we now have oxygen. So while before things were hot and they were moving at high energies, we weren't so worried about the materials. Now this is going to be significant because the oxygen is going to start to chew up our devices. With respect to modeling, our models do incredibly well at predicting the ionization and acceleration of atomic species. They don't have molecules inside. They don't have chemistry inside. For the most part, they don't have dissociated products and all the other physical processes that will go in there. Does the world know how to do this? Yes, but it is not in that knowledge is not naturally in the propulsion community. So we're probably going to need to reach out a little bit, get some of that physics and start to put it in our models. And furthermore, we don't have the data to start to anchor some of those models. So I think that's a separate effort. Mike McDonald already alluded to the fact that the cathode technology is a physics challenge. How do you get electrons from oxygen or a gas that has oxygen in it? Right, that's a very challenging process. And of course, I'm going to completely ignore all the issues with the inlet. I'm going to leave that on the spacecraft design side. The other challenge, and we've experienced in the lab ourselves, is that we are going to get negative ions, the oxygen in particular. And if you go and look on your favorite website or go to social media, you can always find a picture of some new device operating on air. They don't tell you how long that device operated before it turned itself off. We've found that the negative ions will actually run back and start to melt holes into our traditional anodes. And so we're really going to have to think about the materials and the approaches to doing this, because having heavy negative ions going in the wrong direction really starts to mess with the way that we have historically done EP or propulsion. The other thing, and I put these under engineering challenges in that I know what the challenge is. I haven't solved it yet, but there are a lot of ways that you could solve it, but we do need to start making some progress. What is new to EP is that we have a propellant that varies in composition, right? For all those years, and still now, we have 99.9995% pure gases when we start these devices. We know exactly what is in there, and it will be that way for years into the future. And in air breathing EP, this is not the case. While we have a framework for designing propulsion, we don't have the frameworks yet for what to do when the propulsion composition is varying. In addition, we have the reactive species. We don't have the physics in our models and our approaches of what happens when you start to chew up the walls and all these other materials. How do we deal with that? On the plasma side, we have to talk about the ionization and the acceleration of an ever-changing soup of ions. Which ion are you trying to accelerate, and on which day? In addition, a lot of these devices have magnetic fields inside so that we can hold electrons still, but now we're going to have ions moving off at, we're going to effectively be filtering ions as they come out of the device. The plumes are going to be huge. And this brings up issues with spacecraft integration. So we're really going to have to think about what are we trying to accelerate? When are we trying to accelerate it to get what level of performance? I think that's actually a fun exercise. I heard discussions about you're going to do machine learning and do some exotic control system, but what are you trying to optimize on a given day? How do you sense what you're doing? With that said, I heard Justin Koo was mentioning it. We need to be able to somehow sense what we're putting into the engine. And this is not like I'm going to have 50,000 instruments, a couple lasers. This is like, what is a basic set of measurements or things that I can measure as the propellant comes in to know what I should do to the device in terms of magnetic field, in terms of how I'm going to fluctuate my power, in terms of how I'm going to change my frequency of RF so that I can target the species of interest so that I can have some hope that I know what the performance of the device is going to be, or at least try to tweak it up. Another fun one, and I know that we're going to have years of fun trying to sort this out, is lifetime. We have been in a great situation where we pour the same propellant in. You do, your favorite study of sputtering on a given material, and I can tell you with some level of uncertainty how many hours the device will last. This is important because, we build things and we'd like that mission to continue, or at least know when it's going to end. The problem now is that, okay, what's the lifetime? Well, how did you run it last week? Okay, so you got 700 hours left. You ask a week later, well, what'd you do the week before? Okay, now you got 250 hours left. Well, I only ran it for a week. Well, the propellant you had last week was a lot different, so that doesn't count anymore. And so how do we live in a world where we know enough about what just went through the engine to be able to predict how much will be left of the engine, right? This is going to be significant because I think the error bars on that, when you talk about the composition of the gas changing 100%, well, let's say 50% from week to week, could have a significant change on the amount of life or performance that you could expect in that device. This is a very different world for what we get to do with krypton, xenon, argon. Right? How do you do the physics of that? The other fun one, probably definitely in the labs on the university sides, is all of our diagnostics now are built for atoms, right? No matter what you do, you always know it's the molecular weight of the thing that's going to hit your device. Now we're going to live in a world where chemistry will have happened, reactions will have happened, and there might be 6 or 7 things that could be coming at your diagnostic. How do you determine what the diagnostic is actually measuring? I love lasers, but now how many different frequencies of lasers are you going to have in the experiment so that you can begin to sort out what the species are that you're looking at for LIF or any of the others? So this diagnostic world is going to be really fun. We may need to take a slightly different approach to what we're sensing. The last piece is around the facility. I don't know how long you can run an air breathing EP device in a facility before it cuts a hole in the side of the facility. I don't know what the right material is to put on the wall of that facility to protect the facility, but also not mess up the thruster. I think there are some unknowns there. I think there are some investments that need to be made before we break a lot of facilities. And the last piece, of course, is pumping. We will now be working with light gases. They have lower freezing point. There are some other things that are going on. Is the cryo pumping that we've all come to know and love the right pumping capability as we begin to study these devices? I absolutely agree that cryo pumps will pump all these gases. But when you start to have when you have all these other species there, do you want to put a couple different types of pumps on your facility? Like, what's the right approach to doing this? All right. This is a fun slide I was putting it together. Just, trying to be critical of myself. As always, you can always pick up your favorite paper, you can pick up your favorite item, and you can find pictures of thrusters running. What is the actual reality of these thrusters? I would say on the thruster side, I'd give us a TRL of 3, right? You can turn them all on for some amount of time. I wouldn't give them a 4 because you can't exactly predict the performance before you do that. In terms of thruster lifetime, I would give everyone a 1 because I have not seen yet a model that can predict how long they're going to last. In terms of materials, I just put that in red, lots of unknowns. Flow systems, I'm feeling good about the flow system. In terms of cathode lifetime, it's questions, but we do have cathodes that can supply electrons. Quantities, current densities, all still on the table. And of course, power processing. Power processing will be different in an air-breathing world because it's probably going to have to adapt. Those power electronics exist. We probably need to bring more of that knowledge to this community to make sure we can create what we need. All right, so just to kind of wrap it up here in my last minute or so, if I had a roadmap or to decide how am I going to invest to do this, a little time to figure out the right facility, a lot of time to figure out how to model and simulate these plasmas and the propulsion that you are planning to have, a lot of time on diagnostics so you can begin to anchor some of these models in a real way. I would be spending time on power processing and of course the cathodes. And then of course, if everyone is brought up, the materials are going to be an issue. In summary, I think we are fortunate that we have a strong electric propulsion community over the decades that's been invested in, and the tools and the intellectual knowledge to do this are out there. And I think that community is also ready and probably excited to kind of dig into these problems. Thanks.
Session. We're going to wrap up the session with Michael Pater. Michael. And he is the James Clark Professor of Engineering right here, well, at the George Washington University. Thank you so much.
One. Okay, thank you very much. It's not showing on this screen. Okay, great. Thank you. Thanks for invitation and organizing this very interesting workshop and few panels that one that we had and next one that we will have. And thanks, Mitchell, for giving great background into electric propulsion. I will actually dive into maybe some specific aspect of it that I find it of interest and show you some example of some progress that exist in that sense. So there is a lot of kind of interest, as we heard already from this morning, in what we call the air-breathing or fully air-breathing electric propulsion. So in other words, in this case, we will be heavily relying on the air as our propellant. This would have lots of benefits that already were discussed, that will, perhaps allow to lower operational altitude, will reduce maybe cost when it comes to propellant. Will have a lot of penalties on many other aspects, and etc. And there are many examples of concept that were already discussed and developed, tested, and etc. And as Mitchell was kind of illustrating, there are various thrusters that what people try to do is to adapt to kind of new configuration where instead of atomic gas, you're going to use some mixture that comes with air at different altitude will be different mixtures of. And there are some cases where there were some successes. Granted, this can be run. I remember in the last electric propulsion conference, we had a kind of strong argument which of this kind of existing engine would be the probably the winner in this initial at least attempt. But there was attempt in Europe about maybe 10 to 5 years ago, and they actually built system. They scooped the air to increase the density, and they had a great demonstration, except in their demonstration, the drag was larger than thrust, right? So ultimately, this is not what obviously we're looking for, but the claim was that, hey, at least we can show that we can operate and we can produce some thrust, and now we need to work on improvement. So on the other hand, as was already pointed out several times, this is a dilemma, and Ian mentioned this as well. So if we use a scoop that everyone or most people in the community consider, so in other words, you would like to increase the density of air species to make it more appropriate for ionization and etc. You slow down the air, and then you need to accelerate it again. So we asked this question about 10 years ago and tried to find, is there any situation where you can operate without scooping, without slowing down the air, and yet can still produce thrust that will be at least equal, if not larger than drag, right? And we took whole thruster as example. More or less of a standard configuration, say, 10 centimeter in maybe 20 centimeter in diameter. In this theoretical study, we assume, optimal conditions. Say you have full ionization, so all entire neutral air will be actually converted into ions, and then we accelerate, allowing as long ionization channel as necessary. And we found that solution that exists is in that range of between 90 and 110 kilometers. So in other words, in this range, we can produce thrust for that size of thruster / satellite, if you build satellite around this thruster, right, where you can produce enough thrust to sustain it. Now, the penalty will be is a power. So, and just to give you just to illustrate, if it's a whole thruster, say, few hundred volts of voltage, if we take that size of the satellite and convert, the air into the ion, so we end up with about 100 amps of current. So you have 100 amps of the current, 300 volts. So that ends up in 30 kilowatts, right? So that's like at the minimum, right? So that's basically was the outcome of this exercise. But I started to focus on this altitude because of that, reason. So of course, when you fly in that altitude, and this is what basically I'm kind of, borrowing this from Ian's presentation, but the idea would be how you manage the intake, how you manage the mass flow rate that coming into this type of thruster, what kind of property of the surfaces needed, etc. This is the entire world. It's a problem on its own. I'm not going to focus on that. What I would like to discuss a little bit of some kind of interesting concept that, in my lab we discovered that actually kind of triggered this charge harmony program at DARPA. And the idea was that, okay, let's focus on that low altitude around, let's say, 100 kilometers. And, we looked into chemistry, heavily into chemistry, hundreds plus different species, 1,000 different reactions. And if you just boil down to, two main reactions of interest is ionization and the electron attachment, right? So, Mitchell talked about negative ions. So maybe we can make a use of negative ions. So say, here, what we're showing is that dependent on electron energy, right, that we can perhaps manage, we can either ionize if it's high enough, or we can actually produce more of a negative ions. And if you do so perhaps we can alternate between the different polarities and try to extract either positive or negative ions. So this system, even if it's an ion engine, will be naturally neutralized, self-neutralized, right? So again, this is a simulation. This is a perfect world. In this instance, we produce thrust, which is by a factor of 2 to 3 higher than drag, which is great. And also the plume will be neutral because we extract in right exact amount of positive and negative ions. Okay, so now let's talk about challenging if we do so. So first is ionization that we will be discussing a little bit here. The second challenge, or maybe it's not just challenge, maybe it's even opportunity, right? In terms of neutralization. Now, everyone talk about cascades, etc. We'll address this. And then the environment. Again, previous speaker talked about, challenging and changing all the time environment that we need to rely on, right? So let's talk about ionization. Again, it's a kind of busy slide that I borrow from this review article. But the idea, the bottom line is cross-section for ionization is smaller for, air molecules than for what we used to in electric propulsion, say xenon, right? By order of magnitude. So that basically would translate into, let's say, longer ionization channel if we can want to get to the similar ionization fraction. Molecular propellant, it's also a little bit challenging because it's a larger, losses, perhaps, because you have all different processes that not necessarily directly will lead to ionization. Say, will be a lot of excitation that will end up with radiation, etc., not necessarily useful for propulsion. These are lighter components, so then they will have shorter residence time in the channel. So again, will mean that we might have need to have longer channels and etc. That's a penalty from that point of view. Let's talk about environment, right? So already several speakers mentioned about variation in the air composition. This is one of the example that show quite large, variation, maybe by factor of 2 to 3, that will be, challenging when we operate in given thruster that already optimized, or even if it's not optimized for one particular environment, but still, there is a margin, but how far you can go with that. And we're using, again, air as propellant, and therefore we have to address it somehow. So I will just show you some example how this can be, perhaps, addressed in the way that if the thruster would allow, to have somewhat of variability of operational parameter within this margin at acceptable, say, performance, acceptable efficiency and thrust to power ratio, etc. So you can train the, you can build the artificial neural network that will, basically take various, thrust parameters, discharge voltage, maybe frequency, maybe some current, and etc. Based on the input, say based on the measurements that has to be performed in orbit to figure out what would be the right settings for this particular notional thruster that will be able to overcome this variation in input, right? So this is one example of a simulation that I would like to show. So say, we run an 85 kilometer and we would like to change the altitude. This one of the example where this machine learning can be utilized. And, we can see that we can actually adapt quickly in terms of thruster versus drag to this environment. And at some point, we actually will have, obviously, dependent on how fast thruster will be able to react to this changing condition. At some point, we will have drag larger than thrust, and then perhaps we can find a right condition. What I want to point out is here, this is the envelope that we operate in, and what it shows is how discharge frequency will need to change to adjust to these, variations in the input. Let's talk about neutralization and the cassettes. So I'm not going to focus on the cassette in this presentation, but in general, we understand the problem. The problem would be if we are, dealing with chemically reactive gases. We talk about oxygen and maybe not just molecular oxygen, but also atomic oxygen charge. Ions. You would see a lot of poisoning of the cassette. Etching and sputtering and etc. And perhaps plasma cassette can be used. So in other words, perhaps we can create the system where plasma is formed and electrons can be extracted not from cassette, from the solid cassette, but from the plasma environment. That will introduce lots of flexibility. But in terms of neutralization, there is also some interesting opportunity at those low altitude. And let me show you some of this. Presumably, we operate ion engine, right? Yeah. And in ion engine, you extract positive ions. That will build a positive charge outside in the near plume, and therefore it needs to be neutralized, right? So normally what is used is cassette neutralizer that will inject electrons, just enough electrons to to neutralize that amount of ions. Or as we spoke before, maybe we can alternate between negative and positive ion extraction. But if we operate at, say, 100 kilometer altitude, what actually happens is that charge, this positive charge, will actually create strong enough electric field that will start to ionize air around, right? And will create the electron avalanches that will propagate toward this charge, and as a result, will actually compensate this charge. So, so this is some example of a peak simulation in this environment that show at different altitude how this process happening. What primarily we show on here is a diffusion, the electron diffusion that actually directed toward the charge, where charge is formed. But what's interesting to point out is this, process is actually quite effective at, 50 to maybe 120 kilometers. Where you can decrease the charge by many factors. But when we above 150 kilometers, it's not enough air, it's not enough collisional events that you can produce enough of the electrons to compensate, to neutralize. So in this case, we do need to carry cassettes that will be acting as neutralizer. And then we'll come back to addressing this issues with the cassette. So, and just at the end, just allow me to illustrate some implementation that taking into account all of these aspects that I mentioned, some problems, some challenges, some opportunities as well, is, it all was put together as a kind of demo notional thruster. So we call it hypersonic air breathing thruster. In other words, we are not slowing down. We trying to operate at the condition where mass flow rate is high enough, which correspond to between, let's say, 80 to maybe 110 kilometers, just as was predicted in that paper that I show you, utilizing the plasma cassette where we extract electron from the plasma. And this is some kind of map, the experimental data that shows that, for those conditions, we can obtain something like Newton of thrust at, relatively modest frequency of about, 70, maybe 200 hertz. With that, thank you very much. And I guess we will have immediately discussion. Thank you.
I'll have our speakers all come up to the front now.
Presentation.
So yeah, you sit in the second chair, I guess, Ian. And Mitch, you gotta go third. Third. Let's see if you can count.
Yeah,
Okay,
perfect.
perfect. Okay. Thank you all for your presentations. Exceptional. We'll see if there are questions, and Yvette, we'll start with you.
Ian, this question is for you, and it's just a clarification. But the story that you said about the NOAA lady not being able to tell SpaceX the weather the next day, was that the weather in space or was that the weather at the launch pad?
Oh, it was the weather in Leo, in VLEO. Yeah.
In VLEO.
Yeah. Yeah. Exactly. Yeah.
But were they supposed to? I mean,
So-
why would they expect them to know the weather in VLEO?
Well, I guess SpaceX thought that the Space Weather Operational Center would be able to tell them what the weather is in space. And they can, but not with enough confidence to, guarantee anything, right, for SpaceX or anybody else. So to me, it's an illustration of the uncertainty, right? That is the place in the country for the US that's supposed to know the most about the VLEO weather.
Really, this is new to me. I don't work in this field, but very exciting. I see some of the problems you raised related to this atmospheric oxygen and all these gases that are all there. Are there studies going on I see that actually as opportunity to do something unique. Are there researchers going in there to use this, for example, material scientists that can harvest those unique opportunities to create something new? And in designing your probes, your sensors, are you looking into opportunities to maybe have a kind of materials that will take advantage of that to fortify themselves? That's to say, you start with something that needs ionic oxygen, for example, to create another material that then resists corrosion and all the rest that may happen. So are you working with material scientists to look into these other avenues to leverage the environment and make it even better?
Sure, so that's a big question. There are people, of course, looking at the impact of oxygen environments on materials. They tend to be focused on their application and their set of materials. Some of the things that are coming to this application have oxygen atoms or ions at much different energies than before, with a different set of materials that we don't normally interact with. So there's just, the tools exist and the know-how exists, but there needs to be an effort to say, hey, let's quantify this in an area that's going to be of interest and helpful to us. The second part of the question was, do we have, I guess I would say, manufactured materials that are going to react and do something even better? Not that I completely know of.
Yeah, so it's an interesting question. So in other words, not to be reactive, but be more proactive, right? So you meet environment and you try to work, backwards and try to design something that would be optimal for this environment. This is a kind of interesting approach. I don't think it's actually happening in this community yet, but it's probably should be part of the effort.
I'll maybe just add something to that. If you think about the materials on the outside of the space vehicle, just as one example, right? There certainly are people working on, like I was talking about, specular, right? Materials that have positive reflection properties. In much lower in the altitudes, in the field of hypersonics, there are materials that kind of grow a protective oxide layer themselves. And I think this is the kind of thing that you're talking about, right? Where the initial response of the material to the environment ends up being more positive instead of fighting something, right? Find something that helps. Yeah, I'm not aware of anything like that yet for this community. I think it's just, again, we're at the beginning of, trying to understand what the problems are. But always, I think also that the time evolution is important, right? That it's not enough to have good behavior out of your materials for the first couple of weeks and then things degrade, right? So it's also got to be something that sustains its performance.
I had a question for Dr. Walker. So you mentioned kind of the the issue about composition in electric thrusters, right? That we've historically always had this idea of exactly what's going in and what's going to come out. To your knowledge, has there been any work in academia or maybe industry on thrusters that can accommodate varying compositions?
So there has been work on characterizing the performance when you change those compositions. I haven't seen anyone doing active work to understand it in more detail. I think there's a huge opportunity there.
So it's good to have the computational guys sitting at the same table as the experimentalist, right? So traditionally, right, when we talk scramjets, hypersonics, we actually have equations of motion that can go from inlet to exhaust. Now, I wasn't really sure that, I think Mitchell talked about that there isn't a computational space like that right now. And Ian, I wasn't sure if that's what you were advocating as well too. But we kind of understand the equations of motion to combine free molecular space and Maxwell's equations, right? Is there something out there now, or is it something that needs to be developed from academia? Thoughts?
Yeah, so we do have a code like that can do both, kind of the neutral gas dynamics around the vehicle and a plasma-based electric propulsion system. So we could do an end-to-end simulation of the whole thing, although it does depend on the particular aspects of the propulsion system, right? You get into different regimes. If you kind of look at the flow path through the full system, right, out in space, it's really, really free molecular, right? No collisions at all. But then by design, you want to kind of compress the gas and get its density up. So then you start to see a lot more collisions amongst the atoms and molecules. And then you feed that into a thruster. And if it's a Hall thruster, again, it's very close to being in that free molecular regime. There are important collisions like ionization, of course, charge exchange. But you kind of traverse a wide range of regimes. But there are codes that can do all of that. But they're only as good as, the data that we can compare them to and the information that we can put into them.
So now back to the experimentalist. Why is there a reason we could or could not compare the data that you guys are collecting?
I don't know if it's can't do it.
Yeah.
We built diagnostics knowing that we had a singular atomic species to deal with. So all of those diagnostics are very good at doing that. And now where you have a system where you've got singles and double charge of 4 or 5 different types of molecules, those diagnostics are just not built to measure those things. So there needs to be an effort to build the diagnostics to measure those things so that we can anchor a lot of these codes. And that gets more interesting in that now the code is going to have to track more species and do all of our past assumptions still hold.
Yeah, just to add what Ian discussed, obviously there are codes that can handle all of that, starting with neutral flow and ending with ionization and acceleration. It also could be a hybrid kind of codes, dependent on what kind of environment. So perhaps some of this may be fluid, some of that may be particle-based. But what's really important is the data that will feed into this collisional cross sections and all different type of collisions, etc. There is a lot of chemistry going on, so maybe even in a simple kind of configuration, you end up with maybe 100 different species and maybe 1,000, and if not more, reactions that need to be understood well. So we do have some reaction rates based on some assumptions. Maybe some of them are measured, but not all of them. The database is not perfect. And that would be one of the actually challenges to generate the appropriate database for this environment.
I'd like to just add on to that comment that the Space Force has one of its Strategic Space Technology Institutes, SSTIs, that is on power and propulsion, that is run out of the University of Michigan. And they're looking at even more complicated propellants, hydrocarbon and nitrogen compound. And one of the things that we're doing, so we're supporting that project, and we're looking at the chemistry, right? So the chemistry is even more complicated there. And so there's a couple of things. One is to use something called sensitivity analysis. So sensitivity analysis says, tell me what you care about most in this very complicated calculation, and I will rank the processes by their impact on that quantity of interest, right? So for us here, it would probably be thrust, right? So if you have 1,000 different processes that might be involved in a system, sensitivity analysis, a good result is when it says, well, of all these 1,000, it's these 5 that you really have to figure out well, because those are the 5 that most influence the calculation of thrust. So there are ways to reduce the computational complexity. And then secondly, I lead a MURI project. It's hypersonics, but the title of it is something like plasma formation under hypersonic conditions. And so in that project, we are developing through a combination of experiments and modeling, rates and cross sections and so on for some of the processes that would be involved in an air breathing electric propulsion system. So again, it's not going to answer all of the questions here, but there's already, activities underway that at least means we're not starting from scratch.
This is partly a question for Mitch, maybe also for Ian and Michael, but let's envision glorious victory. All the diagnostic dreams come to pass. You can look at this complex stew of species in your thruster, and you know what's there, and you know now what you want to target. What does the turning of the knobs look like at that point where you say, yes, I want to target the O or the N2? Just because I think about when we went just from xenon to krypton, it was not really obvious how to optimize the thruster there. For many years, it seemed to be, let's turn up the voltage and run it higher to hit this tiny molecule harder. So what do you think about when you think about trying to tailor a thruster discharge to a particular species of interest, even assuming you've been granted that knowledge about what's valuable to target?
So for the mission that hasn't been defined, let's talk about that. I think the first thing is, what can you reliably depend on the device to do, right? Because I'm at some point, if I'm going to fly it, I want to be able to tell someone it will do at least this all of the time. And so what set of species will I work with that I can come up with something that I trust and can put some good uncertainty on it? Once we get there, then we can talk about cost and all the, best electronics. But I think I would be aiming for, of all the species that are going to be here, which ones can I reliably depend to create and use to generate thrust or ISP or whatever your variable interest is?
Yeah, maybe to add to this, I actually look at differently a little bit. I don't think it will be one species because you have this cocktail and you know you're limited with your mass flow rate to begin with, right? Because you're in rarefied kind of environment, so you need to actually solve it. It's going to be like a multi-parametric one. So you have to actually have all of this or most of the species that you know combining will get you relevant mass flow rate and try to optimize. So you will need to compromise somewhere. It's not going to be the perfect for one particular component, but maybe the way to look at it is, you know, get and say 90% of the flow, and you know, we able to utilize it. What would be the combination of parameters? It's not going to be optimal for each of them, but maybe optimal for combination.
I think the only thing I'd add to that is, I think somebody mentioned this, right? That if you have lighter species, right? So the molecular weight is going to dictate some of the design. Maybe you need a longer channel, right? So I think you can use the experience that has been gained for Hall thrusters I'm thinking about here, where you've gone from, where the community has gone from xenon to krypton to argon. There's some understanding across that of, you know, design rules of thumb or whatever best practices, you know, to get the best out of propellant as the mass changes, right? And yes, it's complicated here. It's not, you know, we don't know exactly what it is, but I think those kind of general design rules and understanding that the community already has can still be, right, brought to bear on this problem.
I got one for you. So a common theme across your three talks was uncertainty, uncertainty in the environment, uncertainty in the materials response to the environment, uncertainty in even the altitude of which, you know, a VLEO missions we're talking about, uncertainty in the ground test facilities to match flight. There were other uncertainties as well. I guess my question is, given the large number of uncertainties that you all discussed, do you think there is a need for a common reference concept or a, you know, maybe multiple, you know, maybe we need to move VLEO technology forward, maybe we need a 300, I'm making this up in real time, okay? So it could be wrong. A 300-kilometer VLEO reference mission and a 200-kilometer VLEO reference mission that folks could, you know, apply technology advances to or focus their technology interests on. I'm asking, do you think that would be a helpful way to move this domain forward?
Well, I meant to talk about uncertainty quantification in my remarks, right? So certainly one of the things, a role for modeling simulation is to quantify that uncertainty, right? And based on all the, I think when you stack all those uncertainties up, the uncertainty is huge, right? So, okay, so there's that part. You can actually quantify, right, by running a lot of simulations and figuring out, you know, what the uncertainty is. But also, again, going back to that sensitivity analysis, what is it that contributes to the uncertainty, right? Again, if I say, okay, I can calculate the thrust for one of these concepts as 1 Newton plus or minus 50% because of all the uncertainties, right? But these analyses can also tell you where that plus or minus 50% comes from, right? So that you can, it helps to inform what do I need to drill down on through investment of resources and time. My initial, it's a very interesting idea. And my own thought on that is I'm not sure the community is large enough to have multiple reference, right? But I think even one, right? And that also goes back a little bit to my comment about what's the killer mission here, or what's the first mission, right? And yes, it's true that albedo is, you know, 25 kilometers below LEO, and they're operating today. But it would be great to come up with something more exciting, more challenging to kind of rally around. I think it's a great idea.
I want to add to that. Yes, I think it would be a great idea to pick a couple reference missions and let us try to run down and sort out a smaller set of these challenges and uncertainties. As I was thinking about this, I always compare it more to if I'm in a speedboat, like I know how much horsepower I have, I know how I'm going to cross. This is more like sailing, right? From day to day, things change, but if I'm in a certain location, I have some expectations.
Yeah, I think it will be if it's possible at all, great effort if we can create this maybe set of mission, maybe 2 or 3 that will fly at different altitude, maybe same type of satellite, same type of propulsion system and power, etc., and kind of resolve some of this. I don't think this will resolve it totally that some of us, like Mitchell mentioned, day-to-day variations. I don't think this will help with this. We just need to adapt it one way or another. But at least in terms of just a variability in expectation that we have, we don't know how propulsion system would react, how they would behave at these different conditions. We don't know how material will respond. So I guess having 3 missions with the same materials and 3 reference points, that would actually create a lot of kind of data sets that all modelers and experimentalists can work with, and that will kind of open up this space. I think it might be a good idea. Also, I was just thinking it could be actually one mission that maybe can fly through all these different altitudes and collect all this information.
I had one comment.
Question? Yeah. So following up on that discussion, do you think that there's one approach to flying in VLEO that will make sense across the 3 or 4 orders of magnitude difference in density between the high end of VLEO and the low end of VLEO? Or will we end up with, there's a natural approach that looks great at 150, and there's a different natural approach that looks great at 250. That's different, like, where do you think that's gonna, that we're gonna end up there? Thank you.
Yeah, I think just to the last question, I don't think it will be one solution for all this. Although we talk about VLEO as a one, it's not one, right? And there is significant variabilities from 100 to 400. So there will be different thruster solution, different satellite configurations, and different power perhaps that necessary. And I don't think we at the point where we can maybe classify as like a 3 subsets of altitudes of 4 or 10. I don't know that, and maybe some overlaps perhaps. But the way I think it always is not to take a thruster or say existing configuration and try to adapt it to this new environment, new propellant and etc. But maybe go all the way kind of in the reverse. Take the condition and figure out what would be the optimal thruster for those conditions.
So I don't know the answer to that, but I'll talk about what I've seen. So we have already seen with all of our propulsion technologies, they have windows where they work really well, and if you push them outside of that, things fall off rapidly. In an environment like this, where the margins could possibly be a lot smaller, I suspect there will be some clear-cut windows of it makes sense to do this here, and to do this here, and to do this here. I don't know where those cutoffs will be, but I suspect they will exist, especially as you start to bring in other parts of the spacecraft system.
I think the thing I would add to that question is the kind of push and pull of mission and technology, right? If there's mission pull to be able to fly over hundreds of kilometers of VLEO, right? Then these guys will figure out how to do it, right? And at the same time, we're trying to, I think, just trying to get to that first base of saying, hey, here's the simplest part of VLEO that's a little bit lower than 375 kilometers, right? So somewhere more interesting, where we can show, right, as a country or whatever, that we can operate there, right? And then you start to build more margin into the system where it can start to fly around and do dynamic stuff, right? But understanding, is it 100 kilometers up and down, right? Or is it 10 kilometers up and down, or, right? I think that's going to be super important in the second phase of VLEO stuff.
I just have a quick comment, and mostly for you, Mitch, but in the experimental hypersonics community, there has been a lot of investment in absorption spectroscopy, TDLAS. And with that, they're very good at measuring hundreds of species at one time for one shot of a hypersonic tunnel. So I wonder if there is potential in that technology to your propulsion to see all of the species that you're going to see now with air.
So the comments about, hey, there are other fields that have done things like this. I absolutely agree that we should go over there and leverage all they figured out how to do, be it on the hypersonics aerodynamics side or be it on combustion technology as well. The densities are a lot lower. The signal to noise ratios are going to be a lot different. But yes, and the species are different. But yes, we should absolutely go harvest all of that knowledge and the intellectual know-how to do that.
Okay, so I enjoyed the discussion on sensitivity, and a big challenge both for hypersonics and space is the fact that we can test all we want on the ground, but that's not the operational environment. The sensitivities may be different in an operational environment. So this is a question for the academics. Given that flight data tends to be something we hold on to pretty tightly, what does academia have to do to be to get access to some of the things that we need to do the sensitivity analysis in the operational regime, rather than simply in a chamber?
Yeah, I'll take that question. So we have a good example of that that's been funded by FRL. So the university had a couple of CubeSats that had done a NASA mission, and they were powered down and were just winding their way slowly to re-enter. And so in this project, we've reactivated them, and we're operating them through VLEO. And so every so often changing the configuration. So there's a low drag, configuration, and you can turn it on its side, right? And suddenly it's a high drag configuration, and it pretty much instantly drops, And so I think this is one example, right, in which the universities can generate operational data. I don't think it's sensitive, it's maybe cooey, but it's definitely not classified, right? So it's, and lots of people have CubeSats and things, right? And so you could actually, we should start thinking about, this was kind of, well, we have these things up there, why don't we do something useful with them, right? So the next step is let's design some CubeSat things that bring some, useful information into this community. And universities like ours have, launched and operated plenty of CubeSats. It's a good paradigm for the universities and academia.
Yeah, I just to add to this, I think it's a great example, and perhaps this can be improved even because there are many university missions that will be coming, and you can even add to that maybe some material interaction aspects, perhaps different CubeSats may be designed with different materials, and this can be very, very valuable data.
Okay. Thank you. So we're gonna wrap up this the technical part of this session, and so please join me in thanking our speakers. And so we're going to move to a wrap-up discussion over the next 15 or 20 minutes that Yvette and I will run from up front, so I don't have to keep spinning around.
Yeah.
Let's just take a few minutes to summarize. And if anybody has next steps, thoughts, we can come to. I took
Yeah,
pages of that.
I see that. Thank you. And just so everyone's aware, this is, I mentioned at the outset, this is more of an informal workshop. It's being recorded. We make the recording available to the sponsor as a matter of record. There is no formal National Academy report, so there is no committee that writes a big report with findings and recommendations. So, the major recommendations that you folks that we've been talking about, frankly, today, summary points that we've been talking about today about the state of technology, the need to invest in this area, those kinds of topics, we should make sure to wrap those up here and now. So I'll start with Yvette.
I'll start from the back, the very last. I think that from my own experience working with academia and the Air Force and people that are going to use this for the DoD purposes, I think the idea of having a mission that is hopefully distribution A, but if not CUI, where the universities can work and get their hands dirty on something that is actually orbiting and deploying control algorithms, flipping the article around, I think is a big, big, big bang for the buck that the Space Force can invest. So I think it became apparent to me, at least, that there are many ideas, many technologies floating around in the minds of people, and to challenge the academic community and the 6.2 community to put those thoughts together into a platform that is not classified, I think would yield a lot of fruits.
Could I make a comment on that? So we have great examples of that, and you know them, right? Bolt 1, Bolt 2, which was distro A, boundary layer tests that occurred, right? That was funded by AFOSR. And then there's maybe the next level, which is like the test bed for the hypersonics, multi-B, right? So you really need kind of a space-based VLEO test bed, which would be beneficial to the community at large. So.
Can you say a little bit more? Can you say a little bit more about that? A space-based VLEO.
Right. So you could go really far with expensive, right? Or what you could do is you could launch something and design to a ballistic coefficient, which just lets it drift down, but collecting data, whether that's material data, you could potentially put like a thruster on it to test various thrusters at the same time, and provide those swap for the community, right? Just like they do in MACH-TB. So which is a hypersonic launch periodically. I don't know how frequently it is, maybe every quarter or something, that academia industry could come in and actually test, seeker materials, new GNC type concepts and things like that. So that would be the kind of the thought. And Bolt was very specific towards boundary layer, transition for the community to understand. And that particular one was open to the public for their models, to anchor the models to what was actually measured in flight.
I'll just add one comment to this. Was a surprise to me, which is our launch systems don't deliver things to VLEO, right? So you usually end up higher, right? And then you have to fly down. So it's not, there's some challenges there, I think, because then you have to really operate, you know, these small CubeSats before you even get to the point where, you know, you want to collect data. So just, I'm sure it can be overcome, but it's not as straightforward as just delivering them.
But
I'll highlight that we, within the Air Force Research Laboratory, we have a principal investigator who's the scientist in charge of an overall flight experiment. Dr. Holmes is the principal investigator for Otter. We also have a guest investigator program where we can bring in folks from industry and academia to come in and perform additional experiments, on the on-orbit vehicle. And we've been doing this for decades, and we've had some pretty good successes with some of those partnerships with academia and industry. So if folks want to, reach out and get involved in that, we're definitely open for that.
Yeah, and I guess just to kind of comment on that as well. So yeah, if you have any questions about it or you want to talk more, feel free to tag with me. We can make something happen. But I think, yeah, I mean, realizing that it's non-trivial, right? It's not quite, maybe like an aircraft or something else where you're going to have the designated regime you're working in. There is going to be a non-negligible part of your mission, at least in the current paradigm of, bandwagon SpaceX can be delivered to 550. Getting to where you actually want to start your mission is going to take time, and you got to design for it. So that makes optimizing and uncertainty even larger. So that's one thing. And I think another point to kind of put in there is something that I've been kind of tracking. A lot of measurement systems have assumptions about composition built into it based off a signal, right? They're assuming a certain atomic mass that comes in. They're assuming a certain kind of signature that comes out. They're assuming a certain bandwidth, right? So realizing that if you don't have in situ ground truth of what you're actually measuring, you're inherently going to be off, right? So there definitely needs to be some work onto that part of how do we either account for that variability or measure in situ to know that the blip that I'm thinking I'm going to get, if this was O, or the blip I'm thinking I'm going to get if this is nitrogen, could be different if there is O plus or N plus, or hey, you have high solar weather and now you have a helium plume that comes up and now everything's off. Right, because even today we haven't talked about the fact of the sun rules all. So if CME hits, everything's kind of blown out of the water, right? So just want to I think put those points as well of either composition resilient or composition adaptive measurement is also relevant as well.
Hey, so there's been a lot of discussion about nailing down uncertainties, right? Uncertainties in requirements, uncertainties in phenomena, and sort of trying to nail down the design space. But we shouldn't neglect sort of the benefits of digging into those uncertainties and rolling around in them and looking for sort of surprising phenomena. There were some things that were mentioned about understanding the fundamentals of what happens when you vary fuel composition and understanding the sort of fundamentals of the phenomena of O2 material interaction in this regime and how it's different than others. So there's a lot of broad-based knowledge gaps that there can be some fundamental work in to get that kind of understanding as a foundation for later developments.
Thank you. See, Michael?
As we are discussing, I was just thinking about let's say the first mission would be to kind of reduce risk and maybe to mitigate some uncertainty. Perhaps it has to be somewhat of a hybrid. So say short mission where you can have, say the thruster device operating on kind of normal propellant, and you're going to have some window where it will be operating as purely air breathing. So this might increase kind of success of such, but yet we can gather some useful information on kind of in real time.
I think too that because this is new and academia, yeah, of course they can leverage whatever has been done that is related, but the VLEO mission, it's rather new. I think it's an opportunity for the funding agencies present to rewrite history and make sure that academia is funded with the right support and urgency so that in a few years versus decades, they can produce whatever the operators need. And obviously it can be done, but in the things that we work have been around for a long time, including hypersonics, where a lot of wonderful research for academia was not really directed, which is okay. But in this case, with China putting up satellites now, it might just be a unique opportunity in our careers to make sure that we work together from the beginning and get results quicker.
Go.
So we were talking about design reference missions and what could you do entirely at distro A. I was kind of struck from two sides. First, I work at NRL, which is best described as a funding sink and not a funding source. So keep that always at the forefront of your mind. But as we talked about setting up a distro A reference mission for everyone to design on, I thought that there are benefits to workforce development on that. But I also wondered, whose workforce? Am I setting up an open training data set that, I put all the tools up to let some other country design a way to have a system that works in this space, and I subsidize someone else's development? And so I wondered in my head, how do I actually scope this properly to get the benefit that I want without that cost? And from what we've talked about today, a lot of the challenge, the secret sauce, the issue with flying in this environment is the integration. It's the coupled interfaces of all these different subsystems that have to work together. And that's key to sustained flight. But I wonder if we might not want to think about a design reference mission that is just something that is very heavy. So it has a long ballistic coefficient where it'll stay up passively for a while. And it's more of a test bed environment where you are designing tools to collect data or to validate a subcomponent technology. And you can build your workforce expertise in all of those different subcomponents, but on a, say, bus design, a functional spacecraft that is not designed to do anything but be a slow boat down to the Pacific Ocean. And there may be a way to do that with a form of ballast mass that is heavy but dispersal. Think like tungsten powder or something. When you're done, you all of a sudden eject and you come down quickly. But there's probably ways to get months of lifetime going through a VLEO environment there with something that's heavy with just a low cross section, and try out some of these things. So that is a spur of the moment thought on how you might thread that needle.
It's a good thought. Thank you for sharing. Yeah. Okay. Anybody else? Sorry, go ahead.
So I guess just one other comment, and I kind of just want to put out to the community for just awareness or things to think about. We hear a lot of people talk about how VLEO, the radiation environment, is more benign. I think in most cases we can assume it is. However, in the case in which you're in probably a fairly polar orbit, and now you're going through the poles where everything is getting funneled in, can we really say that? We also say spacecraft charging is an issue, right? Because plasma densities are so high. But yet again, if you're in a highly polar orbit, can you really say that? And so I think, yet again, there's definitely work to be done in the community to check the assumptions that we assume that just because we lower everything's fine, right? The South Atlantic anomaly is still there. At some point, it's going to knee off, but that is altitude dependent. So yet again, depending on where you're at, it could be good, it could be bad. But I know we always thought the benefits of VLEO and all these things, and I think they are, but I do think there's a lot more altitude dependence than we think. And there definitely merits some work in academia or in government to kind of really figure out what those benefits are. Now, what space they'll live in, that's not my job, but something to think about.
Okay. Well, thank you for everyone for your participation here today. Thank you also for sharing, your technical insights, programmatic insights, and these summary thoughts over the last 15, 20 minutes or so. I'm certainly not an expert in this field, but I'm someone who's quite passionate about it and interested in it. And I found the conversation to be very intellectually stimulating, spot on in terms of mission application. And I can see a real future for what we're talking about here. So anyway, I appreciate on behalf of Yvette, and you want to say something? Go ahead.
You just wanna.
Go ahead.
I want to commend every speaker
Yes.
because 90% of the times you give directions to the speakers and they probably don't even look at it. But in this case, the directions that we gave you were followed by every speaker, which made the conversations, I think, much more efficient.
Yeah. So I agree. The speakers were outstanding. And everyone who participated today, we really appreciate your participation and engagement. So thank you all very much. That concludes our workshop. We do have lunch for those of you that are here in person today. Thank you.
Workshop of the day. This workshop is for the Transformative Science and Technology for the Department of Defense, and we're focused on non-linguistic artificial intelligence models. I want to give you some context to our committee first before Laura is going to introduce our session. The National Academies Standing Committee on the Transformative Science and Technology for the Department of Defense is sponsoring a series of workshops that are potentially covering potentially transformative new technologies that have the ability to transform science and technology broadly, and particularly for topics of relevancy for the Department of Defense. For this session, for this workshop, we're focused on alternative approaches or broadly encompassing AI that's outside of large language models. Large language models have gotten a lot of publicity. We're focused here in this workshop on AI that's rapidly evolving in areas of model selection, in areas of model design, and specifically in areas that are outside of large language models, including areas like diffusion modeling, embodied AI for physical systems, and non-tokenizable data that's driving the advances in AI. Those includes things like using learning from images, from signals, and from multidimensional sensors. This session will examine other areas of relevancy to AI and non-linguistic AI, including data sparsity and the role of simulated and synthetic data sets. This workshop also will explore areas of collaboration between academia, industry, and the Department of Defense that can accelerate innovation. I want to share one disclaimer or one overview of our goals for this workshop. This is a public, off-the-record workshop session that is part of an ongoing series that highlights emerging trends in science and technology that can transform how the Department of Defense focuses and approaches research and engineering, and it is also aimed at a non-specific or non-expert audience. The online proceedings and brief will feature video highlights and summarize insights from the discussion. So everything that's discussed here will be on record, and there won't be a summary, a report beyond this from our committee. I'd like to now transfer the podium to Laura Monera, who's going to present our introduction to the session. Thank you, Laura.
Okay. Hi, everybody. My name is Laura McNamara. I'm at Sandia National Laboratories. And when Bill Dally is the third person from NVIDIA who is coordinating this session with us. He wasn't able to make it today. But I want to talk a bit about why it is that we decided to focus on artificial intelligence and machine learning outside of LLMs. Next slide. Can I do mine? Okay, so who remembers November 29th, 2022? Yeah, because what happened the next day? ChatGPT drops. And from that point onward, we have this large language models, ChatGPT, now Grok, there are a bunch of others. It was really easy for me to go and pull up all kinds of headlines and screenshot them and put them into a slide, because language models, as several of us during lunch were talking about, have kind of entered the conversation and sucked a lot of the discursive air out of the room. I work in synthetic aperture radar, which is an RF remote sensing imaging radar. And what I can tell you is that there's a lot of interesting challenges in the domain that I work in, radio frequency remote sensing, that really aren't properly addressed through large language models. And so that was my personal interest in helping organize this workshop. And so what we've done is pull together people who are working outside the domain of LLMs to talk about their work, to talk about the challenges, and to talk about the possibilities and impact of non-LLM machine learning and artificial intelligence. So, this is one of my favorite ones. Let me go back. I didn't know ChatGPT 5 had an overworked secretary energy, but I haven't used it. So there you go. Anyway, so going ahead, the first section is going to have Carrie Priebe, Mindy Wang, and Michael Gerard talking about kind of setting the frame beyond large language models. And then the second, we're going to be talking about types of data and the challenges of managing data, and then also evaluating the performance of non-LLM models for different domains. I'll just close by saying this is a huge area. Large language models are only one class of AI. There's a whole lot of other stuff going on. And of course, we can only skim the surface here. But I hope for those of you who are online and in the room who are maybe getting more familiar with these technologies, that this sparks some interest and curiosity in what's going on outside the headlines. So, And with that, we will turn it over to our panelists.
Thank you, Laura. So our next speaker is Carrie Preeb from Johns Hopkins University. And I want to just preface this by saying I've had the pleasure to start working with Carrie this year on using his expertise to understand large language models for applications to emergency care. So Carrie, please go ahead.
Thank you, Amina. Thank you, Amina. And thank you, Laura. Okay, so I'm here to talk about something I'm going to call performance guarantees. And the work is with DARPA. DARPA has a new program called Artificial Intelligence Quantified. And my funding also comes from the Office of Naval Research and the Air Force and Microsoft Research, as well as intelligence agency that cares quite a bit about today's festivities. So what I'm going to say really comes out of my What I'm going to say really comes out of the DARPA program, and so Pat Shafto is the program manager. But the idea is any of these Gen AIs, if you ask it a question, if you ask it to do something, it does something. If you ask it again to do something, it does something that may or may not be the same, may or may not even be similar. If you ask it slightly differently to do something, will it be similar to what it did when you ask it the other way? I don't know. The idea is, can we provide mathematical or statistical guarantees about the performance? And Pat says math is required for that. And I said, okay, well, I'm interested. Math is also required to run my machine. Is there a different button I can just push? There we go. Okay, anyway, it's kind of working, it's kind of not. And by the way, I asked Gabby if I could authorize you to ask questions while I'm talking, and she said I could, so please feel free to interrupt if you want. I think that mathematical statistics is what I do, doesn't drive the world. It's driven by real applications, and that tells me what to do. I could do symbol manipulation in a vacuum, but prefer to have an interesting problem. And I think that understanding math stat for Gen AI is the problem of my time. I've been sort of spending my entire career trying to get here. So this slide is really for three purposes. The first is to say that Proust is famously boring. So whatever I have to say should not be so bad in comparison. The second is to poke a little bit of fun of myself, because I'm what I like to call myself a dinosaur statistician working in AI. So it was statistics, then it was machine learning, then it was data science, now it's artificial intelligence, but really it's statistics. Okay, and the third is, as Laura said, on November 30th, 2022, ChatGPT came out. Well, one of my former students is head of special projects at Microsoft Research. We were working together, still are, have been for decades. And he told me about 6 months earlier that something big was going to happen and that industry is going to do a bunch of stuff that academia is not going to be able to compete with. But there's one thing that they can't do, that they won't do, and it fits perfectly with dinosaur statistics for AI. So thanks for that. So what I'm going to talk today a little bit, I want to get just 1 point across, and I have 1 point's worth of time to do it, about this performance guarantees. So we all agree that critical DoD applications exist for which we need quantifiable confidence in the performance. Okay? And people say, I can't believe they're trusting the Gen AI to do this. And then the next person says, of course they are. It's cheap and fun and cool. And so, but they don't have any guarantee. And so let's talk about what that might even be. And so I will present a story, and then hopefully spirited discussion will ensue, or at least I'll get more comments. So I want to talk about these dots. And this is all I have to say is these dots. So there's two panels here, two different conditions, the left and the right. So let's just talk about, I don't know if I can point, let's just talk about, say, the left panel. There's 50 dots. Each dot represents a generative AI model doing the same task, if you will. And one of the directions I was giving was to talk about comparing AI models for defense applications. And these dots allow us to actually say things that we want the leaders to understand about comparing AI models. So each dot is a model, and under some condition that I'll describe a little bit in a moment, how close two dots are, or how tells me how similar they behave under this particular condition. So the left one is the relevant one. There's two types of models. I'll describe a little bit in a moment, but one half of them is privy to sensitive information during the training, and the other half, the black ones, are not privy. And so we see in one condition, we can actually tell which ones were privy. In this other condition, they're mixed up. We can't tell. But the point is, we've got these dots. They come from somewhere. Each dot represents an Gen AI model, and we can prove something about them. I've been working on dots for a long time, and I had a neuroscientist, after working together for 2 decades with science and nature papers, say, Kerry, nobody knows what your dots are. So let's see if we can tell you what the dots are. So I'm not going to go into this in nearly the detail you have here, but there's a point. So I have a collection of Gen AI models. These can be diffusion maps. These are, I'll tell you in a moment, what kinds of models we can talk about, but it's a very general deal. I have a collection of queries or tasks that I've asked them, and I can do IID replicates. That's a fundamental important point for Gen AI models that I can't do with a human. Because with a human, who knows what happens if I ask the same thing a second time? I certainly don't get an independent and identically distributed replicate of the performance. But I can do that with Gen AI, both conceptually and in practice. So I get a bunch of random variables, which is each model's response to each query on a bunch of different replicates. And those are IID according to some distribution in high dimensional space. So any model, and there have been machine learning models where I can say this prior to November 30th, 2022, but many of the Gen AI models, or all of them that I know about, can be considered in this scenario. So once I have the concept of data like that, I can ask myself, what would it mean to talk about performance guarantees? And so that's what I want to do. So obviously you're not going to read the slide. Maybe you'll read the paper. But I can take the responses for the various models to the various tasks, and I can ask about a dissimilarity between the performance. So if it's producing an image, I can say, are these images close or far? If it's a large language model, I can say, is the paragraph similar or not? No matter what the task is, I need to be able to talk about a dissimilarity, a distance function between the responses of the Gen AI. And once I have that, I can proceed as follows. Well, I can plug those into a matrix with whatever that distance was, and that's an n by n matrix. There are n models under consideration. Remember, we're asking about comparing models. I'm not talking about how good does a particular model perform. That's a question, a different question, but it's a harder question. I'm asking about how similar or different do two models perform. That turns out to be something that we can talk about concretely. I can talk about it concretely. You can read the newspaper on your cell phone. So it turns out that since I'm talking about IID replicates, there's a law of large numbers, and I can say that the entries of this matrix are actually converging to something, this capital delta. Now that's important to me because now I'm going to do some linear algebra, and I'm going to get the collection of n models represented in low-dimensional Euclidean space. And I'm going to call those these psi hats. And the reason that I care about this law of large numbers, the whole point behind our being able to do this, is that I can also think about these psis, which are the low-dimensional representation of this true but unobservable delta. So these psis are real, and I'm a statistician, and I don't like to put a hat on anything unless it's an estimate of something. And so these psi hats, I think of as estimating these psis. It's the low-dimensional representation of the collection of n Gen AI models. Okay? So now let's go back to this story again for the second of 3 times, in case you're counting down. I have 50 models, 25 black ones with no sensitive data in the training, 25 red ones with some amount of sensitive data in the training. The shading of the red tells you how much. And I play this game that I just described. So I ask them to generate a collection of images with different prompts. And then I have a dissimilarity matrix on those images. And I do this linear algebra, and I get these 50 dots. If the queries generate images of the following sort, are related to the sensitiveness of the data, that is the difference in the models, then I see the separation. If the images that I've asked them to describe are unrelated to whether it's seen sensitive data or not sensitive data, then there's no difference between these, as there shouldn't be. Okay? So these dots are the psi hats. This is where D is 2. I've done a 2-dimensional representation just for fun. I've got 50 points in R2 in both of these 2 different categories. And we see that it's capturing, it's allowing us to say something like, I can compare AI models for whatever application I have. And 2 AI models will be similar or not, depending on the defense application, depending on the task that I'm playing. Okay? Okay, so now close your eyes for just a moment. And I'm going to go through 3 slides real quick. This is the first one, not so bad. So here's what I conjecture. And now we have since proved it, as you'll see in a moment. But the idea is, how close are the psi hats to the psis? That is, how close are these dots to some true thing about the model? Something true about the AI model, the Gen AI model, which is way too complicated to prove how it's going to perform. But I might be able to prove something about comparing how it's going to perform. How close are they? And if I can prove that in some norm, because this is an n by d matrix and that's an n by d matrix, even though I can't observe this, the one that I do observe by just querying models is close, smaller than or equal to, this is called a concentration inequality in probability and statistics. If I can prove that this is close, then I'm going to say that those dots that I see are near something true about the model, something unobservable but true about the model, which is what statistics likes to talk about. And so a bunch of nice papers on this. You're not supposed to see this slide or the next one, but the kinds of things we can talk about are how close the pairwise similarity between the 2 estimated models is compared to the truth, or more like the concentration inequality that I just described. Now, I say you're not supposed to understand this slide. Why would I put it up there? Because I think it's instructive. So this is saying that my dots that I observe are close to something true in comparing these models. Well, this right-hand side is pretty complicated, but it's got N, the number of models. It's got M, the number of queries or tasks I've asked. It's got D, the dimension that I want to look into. And it's got R, hopefully R, the number of IID replicates I ask each of these models to do. Because when I ask it to do the same thing twice, I get two different responses. Slightly different, very different, I don't know. So the four things that should be bounding how close I am to the truth are in this right-hand side. Okay, but I think I understand your question.
Yes, sorry. So for the infimum, so that I might be thinking about this a little wrong, but if I were to imagine them as like sets, it's almost like, you know, a measure of how close they are to intersecting, right? As opposed to, again, that's like my analogy.
Deal. There's a non-identifiability, we call it in statistics. That is, the eigen transformation is orthogonally invariant. I can rotate things if I want. So this infimum here is over orthogonal transformations, because even though the psi hats won't be close to the psi because of the rotation, there is a rotation that will get them close. And if all I'm in, that's a helpful question. If all I'm interested in is comparing the dots, then the orthogonal transformation doesn't matter. The non-identifiability in the linear algebra does hurt us for many things we could want to do, but it is irrelevant when I'm talking about comparing AI models, which Amina asked me to do. And now here, there is no infimum, but there's a pretend infimum because I've got the W star here. So I say I've already found the minimum that optimization. So it's two different ways to present it, but your question was right. So the idea is I've got these dots, and now I know that the dots are guaranteed to be close to something true. And so I can't see the true thing, but if these two black dots are both quantifiably close to their true eyes, then I know that the true side eyes must be close to each other because I have a bound on how close to the true, so a simple triangle inequality. So this linear algebra that I've just described actually allows me to say not these two observed dots are close to one another, but that the true size associated with those two models are close to one another. And this allows us to talk about orthogonality between the hat being at, in this case, the query sets, and the difference in the models. So I can talk about how comparing models quantitatively. And so I want to talk about, I guess, this one. This is a Microsoft research one. This is diffusion models that they had. And they have a bunch of diffusion models, just like we talked about before. And they want to know, well, they have a method for comparing them, a very expensive method for comparing them. And so each model, two models are compared on each query, and which one is better, one or two. And the ones are the questions for which model one produced a better image are in the ones, the questions for which model two produced a better image are in the twos, and the other ones are unevaluated. But with our story of dots, we can now see that we might not believe that too. So there was somebody evaluated that too, that point, and said that model two was better. But if there's a continuity in the behavior of these models, which if there isn't, we should cancel the meeting. the workshop. But if there's a continuity in the behavior of these models, then either something strange is going on in this representation, or that too was mislabeled. Turns out they went back and reevaluated, and in fact, it's one. That is, it's just the sort of thing that you might want to do when you're comparing these models, except we have a principled theory. Now, my beloved, both my intelligence community masters and my Microsoft masters, they think that these theorems are useful only insofar as it might convince them to run A/B tests or to find out whether it really works in practice. But the principled approach does, in fact, help convince them to do that. So that's the story. I have other stories kind of like that, but my time is up and your patience is up. And so I hope that we have something to say. Thank you.
Thank you, Kerry. Are there a quick few questions from the audience?
Yes, sir.
Was the this is very essentially
Point. So the entire story, that's with any comparison, right? That is if I take a distance function between images, and the question is whether they have misshapen cats or good cats, then if my symbol doesn't have any, just how much blue green is in the image, then everything that I said is true. And the theorem is true. It's just that all of the true sides will be right on top of each other because the distance function isn't linear. All of the sides will be close to one another. That could mean two different things. That could mean the models are very similar. Or it could mean the models are different in ways you even care desperately about, but you did a dumb thing when you did the linear algebra. And sort of the orthogonal versus the whatever the other informative set that I had in that other slide were similar. So there's two things that have that same property. It's like tomography that we're doing, right? We're querying the system. If those queries don't have anything to do with what you care about, then whether they're closer, and if the distance function, even if the queries are what you want, but the distance function isn't what you want, then that's essential. So you're exactly right, sir, and it's essential. The point, though, is that I can also look for some of these models at the white box setting. I can see the weights inside the model. Turns out that's not very useful because that's pretty complicated. And how that turns into a model response is pretty complicated. So I think I'm turning these machine learning people back in on themselves, right? They thump the statisticians because their thing is way too hard for me to understand, for me to do the math on. But it turns out that the actual models that they produce, those billions, trillions of parameters, capture the entire difference between the two models, which is extraordinarily opaque. The information is in there. It's extraordinarily opaque because two models are very different and very different. And by doing this tomography, by doing this query, we can say, are they similar or different with respect to the particular defense application or the particular application that we care about? And so whether they're similar or different, if you ask them about sports, is a different question. And it's certainly relevant to the mathematics. Yes.
Perry, could you speak a little bit about your continual multidimensional scaling? Are you continually scaling by different means to reduce the data set's dimensions and testing out the dependency on that in terms of how close and how similar all the models are? Or could you share a little bit?
So my introducing a God's gift to multiple, but it turns out that the probability statistics and linear algebra that we want to do is beyond what was in the literature, because we need to have this sort of law of large numbers limit result. And so the continuous multidimensional scaling paper that Michael wrote, put my name on it, but let's be honest. Michael wrote, describes how you can adapt the classical multidimensional scaling, very, very 70 years old and very common linear algebra, to a scenario where you're going to be able to say, in the where you're going to be able to get this concentration inequality, you're going to be able to say that the psi hats are quantifiably close to their individual size. And so it's a proof. From that perspective, maybe you don't care. The actual optimization algorithm has to be adapted in order to make it work. So it's not just off the shelf multidimensional scaling in order to make this work, although that gives you sort of the same pictures, but not the same principle.
This is really very exciting.
Better than Proust, anyway.
Exactly,
Yeah.
somewhat like that. I was, these days, especially in academia, we are faced with challenges of many people using these AI models to do things. So your idea of comparing models come to hand. We take different models to compare to find out if somebody's cheating, somebody's using AI, and so forth. But then there may be misalignment in those too, because they may be doing different things. How then do we retrieve or validate the models that we are trying to figure out in these cases?
Right. So I think the answer but the question is, so the DOD sometimes performance guarantees are non. I'd like to think, right? You'd like to think that when we accuse the student of plagiarism because our AI model said it, but nobody ever did the exact same thing in front of us. Because it is it will say, if you ask it, was Ray Fisher a great thing? It says yes. You ask it 1,000 times, it says yes, 98%. Not 100%. It's a random variable. So if you ask, is it plagiarism one time, and it says yes, that might be a low probability event. So my two collaborators, the intelligence community and Microsoft, is very different. Okay, but Microsoft research admits, at least in private, that they should do the query a bunch of times to get some sort of idea about the distribution, but they can't afford it. The intelligence community is going to require that, but of course, our theorem, and I didn't tell you this, kind of suggests you need to do quite a few IID replicates, and so there's an issue. And so the question we're doing right now is, if you have a given budget, how much confidence can you get? And now, I mean, my whole idea is being in like operations research rather than statistics, and there is a boss. Statistics is done in this circle, but it's for a boss. If the boss says, here's my question, I want to make sure that we only accuse someone of plagiarism 5% of the time when they're innocent, or whatever your trade-off is. I can run through this calculation, and it's actually real, and I can say, you're going to need this many IID samples, this budget, computational budget, to get this amount of power, the probability that you actually catch someone when they are cheating, satisfying the type 1 error condition. And if that costs too much, it's the boss's decision. Either change what I require or be willing to pay more. I mean, that's how the game is played. And the admiral or the general or the senator, somebody, my job, our job, perhaps, is to tell them what they can have. And mathematically, in these both LLMs and the non-linguistic ones, if we're asking, is it working? That's a hard question. If we're asking, is it different than this previous model? That's an easier question, and we can do that. Perfect question, sir.
Thank you, Carrie. We'll have a follow-up panel after the next speaker, Mending.
And they give you this.
Hello.
Hello, can you hear me?
So our next speaker is Mengting. She's an associate professor at Wang and an associate professor in the Department of Electrical and Computer Engineering and at the Center of Statistics and Machine Learning at Princeton University. She has a great breadth of research that covers large language models to reinforcement learning to generative AI across non-linguistic and large language models, specifically with applications to bio and mathematical problems of interest. So I'm going to just open it up for Mengting, and we'll make sure you have your slides up.
Hello, can you hear me?
We can hear you well.
Okay,
But
awesome.
the screen
Can
is
you see
not
my screen?
not quite yet.
I'm sharing my screen. Let me do it again.
It'll be up in 1 second.
Okay, here we go. Okay. Can you see it?
Yes, you're good.
Okay, awesome. Hello, everyone. So I'm a faculty member from Princeton AI Lab, and specifically, I'm going to talk about like a research center I co-founded last year, specifically on AI for accelerating invention. So we're talking about like how to use AI for like solving problems in like physics, chemistry, engineering, electrical engineering, and so on. Okay. So I myself, I work on like both language models, linguistic AI and non-linguistic AI. So this is the slides for the non-linguistic part. Okay. So when we talk about generative AI, so actually like we can talk about like how do we control and steer dynamics of large language models. But there's another very important class of models, which is, I would say, a parallel pillar to LLMs today. Okay. Diffusion models. Okay, so diffusion models are basically the backbone for image generation, for generating like virtual characters, for generating videos, and so on. Okay, so diffusion models also allow generating novel protein structures that can be binded to any user prompted target. Okay, so I would say the core idea for diffusion models to work is that, say that I want to generate an image, I'm gonna start with a white noise image. Okay, so I'm gonna start with this white noise on the left, and then the diffusion model is gonna guide the transformation from white noise to a random sample or a random image. Okay, step by step. Okay, so that's how diffusion models work on a very high level. So this is what people call generative AI, right? But actually, so to really understand why diffusion models is a paradigm shift, let's actually take a step back into the past. Okay, so actually the word generative AI came as a byproduct, okay, as a byproduct of very classical models. Okay, so the first time people realized that models can be generative when they work on VAEs, variational autoencoders. So the primary objective for VAE is to basically, I would say, map data into a lower dimensional embedding and then decode it back. Okay, so the primary purpose is to do data compression from higher dimension to lower dimensions. Okay, so that was discovered, that was like invented like more than like a decade ago. However, as a byproduct, so researchers realized that, hey, actually the decoder part of VAE is fun to play with, right? So if they can if they get rid of the encoder and only work with the decoder, so they can inject any random noisy low dimensional vector as input to the decoder. And then decoder is actually going to output an image that looks real. So that was the first time when researchers realized that, hey, I can use AI to generate. Okay. So the second example was the pretty well-known generative adversarial networks, GANs. Okay. So again, GANs were not invented for generation. GANs were invented for classification, for discrimination. However, in order to be able to improve the accuracy of a classifier, people try to cover the classifier with a generator. Okay, so the generator try to generate something fake that looks real. So the discriminator or the classifier can be trained to tell the subtle difference between the generated image and the real image. Okay, so the goal was to really to do discriminative analysis. But again, the generator turns out to be more powerful and more interesting to play with. Okay, because people actually use generator alone to generate new images. Okay, so you can tell that so generative models actually came as a byproduct from other machine learning tasks. And now when we talk about generative AI, usually we think about this a class of models that can start with noise and then map noise to data. But however, VAEs and GANs have a very fundamental limitation. Okay, so the limitation is for both the decoder in VAE and the generator in GANs. We're actually expecting a single neural network to map noise to data. So we know that the noise distribution is extremely different from the data distribution. And trying to train one single model to do that job is actually very hard. So training stability and generalizability, they're also like they're upper bounded. So VAEs and GANs couldn't go too far. Okay, now diffusion models. So diffusion models is not about a single neural network to map noise to data. Diffusion model is about a controlled process. So here the goal is to learn a state transition controlled process that can map the noise distribution to the data distribution. Okay, and the UNet or whatever neural network underlying the diffusion model works as a controller that is gonna map the image in every single state transition. And the transition function may different depending on the time step in the diffusion process. So that's also why people call it a diffusion model, because fundamentally we're trying to learn a controller to figure out a nice diffusion process that can translate between random noise and images or proteins or videos or virtual characters. Okay, so the paradigm shift is we're no longer relying on a single neural network. We have reframed the problem of generative AI to be a controlled process, and the goal is to learn the controller. Okay, so how does it work? So the problem of mapping noise to data is very hard, right? But however, if we look at the reversal, is that we actually have a very easy process. So that is so-called the forward process in a diffusion model. So what if we start with a random sample in my data set, and then we add Gaussian noise step by step. And we know that this is for sure gonna diffuse the initial image into white noise. So one can actually write down an OU process, a stochastic differential equation for the forward process. Okay, and now the question becomes that, hey, I have a stochastic diffusion process. I even can write down its SDE. Now can we reverse it? So diffusion models is actually grounded on very fundamental probability analysis. Okay, so one can actually derive the reversal of the forward process, which is the backward process, and it is the process we want. Okay, we really want this controlled stochastic process that maps noise into data. And one can characterize the drift function in the backward process. Okay, which is the blue part. This blue part here is so-called the score function. Okay, so the magic here is that in order to fit the score function or to train a neural network to learn this score function, one can actually take samples from the forward process. Okay. And that's basically how diffusion models are trained. Diffusion models are trained by simulating the forward process, taking random samples from the data set, adding noise. So we're simulating the forward SDE. And then one can draw samples from the forward SDE to train a neural network to match the drift function in the backward process. And eventually, the backward process is how we use to generate new samples, new images, or new protein structures. Okay, I hope this makes sense. So the mathematical theory of diffusion model is beautiful. Okay, so so this very elegant model actually works very well together with deep neural network. Okay. So I want to just give you a hint on how amazing this process is. Okay, so fundamentally, when we learn diffusion models, we're trying to learn this particular stochastic differential equation, where the score function is approximated by a neural network trained based on samples of the forward process. Okay. But however, if you actually think about the problem, so we're expecting this SDE fitted from data to map random noise onto very structured data. In other words, we're expecting a stochastic differential equation, okay, that gives me a random walk or a diffusion process that will always converge to a structured data manifold. So this is actually highly non-trivial. So one of the foundational work from my group like 2 years ago is that we actually established the statistical theory. We showed that diffusion models, through the way they are trained, can always map high-dimensional random noise and have the stochastic diffusion process converge to the underlying data manifold. And the statistical efficiency of the training and the computation scales with the intrinsic dimension of the data manifold rather than the ambient dimension. So fundamentally, diffusion models are automatically adaptive to the latent dimension of the latent data structure. So that's the foundational mathematics of diffusion models and why they work so well. And it's actually kind of like pretty non-intuitive to mathematically show why this is true. Okay. So now let's assume that we are all happy that diffusion models magically can learn this backward SDE, and that SDE is always going to guide my diffusion process to converge very soon, very quickly to the data manifold. Okay, so now we can use diffusion models to do more powerful things. Okay, so diffusion models not only can be used to sample new images, we can also use diffusion models for optimization. Okay, so traditionally, when we think about optimization, we want to say that, hey, I'm giving an objective function f of x, and I'm trying to maximize f of x. Okay, but however, if we reword the problem as a generative AI problem, we can say that, hey, what if my problem is to sample from the conditional distribution of x such that f of x reaches the optimal value. So in this way, we can turn any optimization problem into a generative AI problem, and we can use diffusion models and its variant to solve this problem. Okay. Let's see how does it work. So if we can turn every optimization problem into a diffusion model problem, the nice thing is that we are no longer bounded by the high-dimensional non-convex structure of the original optimization problem. The nice thing is that generative models are very good at leveraging the underlying latent structure of the data we want to generate. Okay, so again, there are a lot of very interesting mathematics here. So the first SDE is the transition law of a typical diffusion process. Okay, and if we want to generate from a conditional distribution, so one can try to approximate a conditional score function. Okay, but however, even nicer trick is that, hey, what if we work with the original unconditioned SDE, okay, which is known to be able to generate from the marginal data distribution. And what if we add an additional controller, an additional, which is called guidance function in the generation process? Okay. And turns out that one can actually modify any pre-trained diffusion model by adding this G function to allow it to optimize any objective function. Okay. Okay. So adding a guidance to steer the dynamics of diffusion process is again non-trivial because we care about eventually generating a sample from the latent space. If we add, for example, just stochastic descent or gradient directly, we would jeopardize all the nice properties of a pre-trained diffusion model. Okay. Okay. And turns out this is possible. So in this paper from 2024, we were able to show that one can do adaptive fine-tuning of diffusion models together with this additional guidance in the generation process. And one can show that this approach can iteratively guide a pre-trained diffusion process to optimize any objective. So specifically, what does this mean? It means that, hey, maybe you give me a pre-trained protein diffusion models that can sample from the space of all proteins. But now we want to generate a protein that would bind to a specific target. Or maybe I want to generate a protein structure with some user-specified metric, right? So those are going to be my new objective function. Then we can adapt the pre-trained protein model to generate what we specifically want by adding this self-play guidance. So to make sure that now we're no longer sampling from the space of all proteins, but we're sampling from the space of proteins that satisfy what we are asking for. Okay. Okay, so to give you another concrete example, so in my group, so we worked a lot on RNA language models and generation. So we had a paper on pre-training language models to decode translated regions of mRNA, and we used that to generate novel mRNA vaccines that were later therapeutically validated. So it used to be just a language model, but we had a recent work in which we build on top of this simple language model, and we add a diffusion layer so that we can generate latent embeddings of RNAs via diffusion models for much substantially enhanced diversity. And more importantly, diffusion models let us control the generation process. So we can generate an RNA sequence to maximize any user-specified reward function. Okay. So that is how one can actually combine diffusion models with language models to generate novel designs. Okay. Another example is in collaboration with my colleague Kaushik Sagupta at Princeton Electrical Engineering. So our goal is to train diffusion models to generate novel designs for RFIC. Okay, so typically people design RFIC by running a lot of simulations and using like genetic algorithms to evolve the design. So we want to disrupt this paradigm. So we want to be able to do inverse design on the fly, meaning that if you give me the target parameters, the S profiles, we want to immediately generate a novel design of the chip. Okay. And again, it turns out that it's possible. So we were able to train a prototype diffusion model to enable the EM structure design for any targeted frequency parameters. And so what used to take minutes or even like hours, now we can do it in a single generation process, which only takes a few seconds. And one can also tell that the generated EM structure, actually, they might look similar to what humans have designed, but they actually have a lot of like subtle differences and a lot of subtle details that are actually not very human interpretable. Okay, so we showed our designs to like other experts in the field, and they were all surprised that those non-obvious designs can actually work, but they do actually work. So this paper recently got the Best Paper Award at the IEEE Microwave Society, and also we were proud to be one of the 3 awardees of the U.S. inaugural proposal call from Netcast. Okay, so going forward, I think the idea of using diffusion models to generate any kind of structured data and then further to use guidance to steer the generation process for further optimization, I think this is like a very generic set of methodologies, and people are actively using this methodology for chip design, for generating crystal structures, discovering new materials. People also use diffusion models to train robotic control policies. And this is a very rich and beautiful methodology. Yeah. And so going forward, in Princeton AI for Accelerating Invention, so we strongly believe that AI is going to basically change every aspect of engineering. And we're encouraging collaborations to use AI to improve simulation, because simulation is fundamentally about solving differential equations. We hope to use AI to improve fabrication, to improve control, and to also to accelerate design. So thank you very much.
We have questions in the room. And
I guess I was curious about your thoughts on, I saw you mentioned like inventory planning and facility allocation, like how would this go up against, traditional like mathematical programming options? Because I guess, I don't know a lot about semiconductor examples, but I'm assuming it was, not generating stuff that didn't make sense, right? There must have been like some sort of, were there constraints programmed into it, or was it?
That's a very good question. So there are actually a lot of papers on using diffusion to solve optimization, combinatorial optimization, inventory planning, and so on. So the idea is that if there is a big enough data set with problem instances and solutions, then diffusion models can be trained on top of the data set to try to learn some underlying, I would say, underlying manifold structure of the data. And that can be further combined with a mathematical solver. And this usually can, I would say, improve the overall efficiency by quite a bit. And in order to impose constraints are also imposed by adding this additional guidance, which I talk about. So guidance can be just this additional control to make sure that we have a secondary objective function to meet. For example, the reward can be, for example, the square loss for violating the constraints. And so this is actually a rich field, and many optimizers are working on this.
Yeah, I have a question about creativity in general, right? So it seems to me that what you're talking about here is some, guided creativity, right? I think one of the most, intriguing potential for AI is to be as creative as we are as humans, right? So what is your thoughts and what are your comments towards, whether your approach can lead us towards creative AI?
Okay, so I think creativity that's like the holy grail for humans and AI. So I think also I'm not sure whether there is a consensus on the definition of creativity. So I think if we specifically talk about diffusion models, the level of creativity inside diffusion model is really about diversity in the latent data manifold. So, and that is that is what we can state mathematically about creativity specific to diffusion models. But there are definitely limitations. So we also have papers showing that diffusion models sometimes they really just do combinations of data. For example, one can train diffusion models on Japanese characters, and then diffusion models are gonna output a bunch of, I would say, like non-human characters that look Japanese, but they are not meaningful. Okay, if you understand what I mean. So there are definitely limits in terms of what's the underlying logic and what's the underlying structure that can be actually captured by diffusion models. They may be creating something which are really a recombination of parts that are already there. So I do think there's a limit. But that being said, I think like improving the model capacity, improving the data richness, that will always improve the overall, I would say, level of creativity of models. But if you ask me personally, I still personally strongly believe that, I mean, human creativity is not it's not something that can be, I would say, reinvented by AI machines. And there's definitely still a pretty big gap today.
I appreciate that. Thanks.
Thank you. That's a very good question.
It's a beautiful talk. There's one question.
Yeah, it's very great, interesting your work. I'm just thinking that the application of VR model, the diffusion model, being used for the task like the land cover classification. What is the benefit for that, or the yield estimation? Because I'm come from USDA, so our interest is to provide a good estimate to the community, so that the farmer or industrial or government officer, they can use this information doing a right decision.
Okay, that's a very good question. So, I think so. First, diffusion models are not specific for estimation. So the primary goal of diffusion models is to do generation. But however, one very important way diffusion models or other generative models can help estimation is that those models can be used to generate synthetic data. And by generating synthetic data, we mean that, hey, maybe you have like a small data set with, I don't know, like 1,000 data points, and there are some underlying structures, right? Then diffusion models can capture that underlying structure and then generate, I would say, another like, 10,000 or like 100K data points that follow the same underlying distribution. So that's one, I would say, like that's one typical way for diffusion models to help analytics and estimation.
Yeah, for us, because we rely on the satellite imagery, so that the data point could be like a billion points.
Okay, so you have a very like non-trivial data set already. Cool.
Yeah.
And I have to say another way to think about like data generation is like for example, if we're thinking about, hey, I have this data set and I don't have any other prior knowledge, right? Then from an information theoretical perspective, we cannot generate synthetic data to improve estimation, because that's because any computation is eventually a function based on this standalone data set, right? So no matter what we do, we cannot improve that. But however, diffusion models can help if we're talking about that, hey, we have a big prior, maybe we have a big data set already, like for example, the data set of all protein structures, of all genomes, right? And then maybe we talk about, hey, protein structures from a new species, okay? And we want to do some estimation for this new species, okay? And now diffusion models can really came to help, because diffusion models can learn the underlying structure of the prior distribution and can help synthetic data generation for the new species. And that can help the estimation problem if you want to extend the prior knowledge from all your data to a new domain or a new type of measurement, or I don't know, just a new problem that is related to the original distribution, but also different in important ways.
Thank you. A really beautiful talk. We have one last question, then we're going to go on to the next speaker. What are the current approaches right now to estimate a priori the data needs of an optimization problem that's defined through a diffusion model? If there are.
That's a very, very good question. So actually, I don't think there is. I don't think there is because the complexity of optimization, I mean, depends on so many things, right? So in the traditional, because I used to be a traditional optimizer. Traditionally, we talk about like Lipschitz continuity, which is a dimension-free capture. But however, like in practice, for every problem, especially combinatorial problems, we always have so the complexity could be exponentially hard. But however, I think how diffusion models works in practice, even for some combinatorial hard problem, is that even though the problem is fundamentally hard, meaning that there's a lower bound or there's a worst case example, but however, practical instances almost always have something underlying, have something latent. And diffusion models help by extracting that kind of latent structure. Diffusion models won't help if we're talking about, I mean, the hardest instance in the problem class. So I would say that what people do today is mostly trial and error.
Thank you very much. Great talk.
Okay. Thank you very much. I look forward to like more discussions.
Thank you so much. All right, I'd like to, we're going to switch screens here. I'd like to introduce our next speaker. This is Michael Gerard from the Pacific Northwest National Laboratory. Michael holds a doctorate in theoretical physics from the University of California, Berkeley. Spent time working in, I think it was UCSF, is that right? In medical imaging and decision support. Moved to PNNL, where he currently is the portfolio manager for PNNL's US SOCOM, also works with the Department of State and the Department of Defense in AIML, and is going to be talking today about radio frequency signal analysis, which is a topic near and dear to my heart. So without further ado.
Awesome. Thank you, everybody. So yes, thank you for the intro, Laura. I hope this scratches the itch. When I was thinking about what this talk would be and what I wanted to get across, I was initially going to pack in a bunch of really awesome AI and RF research and cutting edge things and what everyone is doing. And it felt like that could always be short-circuited by the first question just saying, yeah, well, we'll just use large language models for that now. So I feel like the first thing I had to do was convince you that you couldn't use large language models for signal types like RF and domains like RF. I'm sure there are others. I don't want to say this is not excluding any others. I'm just saying that I'm going to make the case that there are modalities and signals and data types that you can't use large language models for yet, maybe someday. So hopefully by the end of this, you will be convinced. Let me see if I do my interpretive dance for the clicker. There we go. Thank you. So yeah, as Laura said, my background is in physics. Don't hold that against me. My brain is certainly classical now. I don't remember any of it. But I was recently converted and now got a master's degree in electrical engineering, which some of you may find more legit. We could argue about it. While at PNNL, I do several things. I have a lot of hats. But the team I lead in our S&T side of the house is our AI communications and signal exploitation team. We focus a lot on taking AI methods, these new tools that have been around for several years, 4 years, 5 years, depending on when you say AI started, and then traditional DSP, RF, electrical engineering concepts that have been around. Someone just looked it up for me. I used to make the joke that I wasn't sure if the Titanic had a radio, but they looked it up. It does, or it did, rather. It might still be on there. But you get this very weird buddy cop movie where you have AI and RF coming together to try to do interesting things. So bulleted list up front. I know that's not what it stands for. I'm an innovator. There's like a few second delay. Here we go. Okay, so I claim the main takeaways from this talk should be tokenizing RF is very hard compared to other text, speech, images, categorical data types that we typically are using and just dumping into our Claudes and Groks and ChatGPTs and things. RF is different in other modalities that fundamentally affect how they interact with AI models and what types of AI models we need to interact with these data types, which I'll hopefully convince you of.
And the last click, RF is huge. The original thing said RF/EM. So the physicist in me wanted to say, cool, I'll take EM and then I get optics and RF, I get microwave stuff. I probably get some high energy physics stuff in there too. But we'll just leave it to RF. Anyways, it's huge not only in the modality, but also in the use cases, in the timescales. When we start talking about how digital information is actually transmitted around, we have to start talking OSI layers and things, and that spans a lot of it. So it is huge, and it's not like a one-stop shop for, let's just put this into, Gemini and it will figure it out for us. So how do we integrate new advancements into AI? This is what I guess I'm trying to think of next. How do we take these cool new AI tools and apply them to modalities that are not easily tokenizable? I'm going to use RF as my exemplar. And then how does that answer change when we start applying it to national security, right? The drivers for commercial applications of this are just much different than defense. So hopefully we'll have a discussion. I'm looking forward to it, how these things change. And again, I'm a nerd, so that's where the end users and the experts within, DoD and the IC need to tell us what the mission drivers are, what the limits are, what are they trying to accomplish, and then we can just say, yep, here's the tools. Like, you're going to have to make the decisions. So why is RF hard to tokenize? This is very meta and philosophical. So apologies if we get out our pipes and nice leather chairs and just sit around. So language has a discrete meaning. We have fundamentally found and come up with very good ways of separating the message from how it got to us, right? So a sentence means what the sentence means. I can't take an analog dial and get an infinite number of sentences that all have the same meaning. There's a finite number of ways we can just combine words together to have more or less the same meaning. But RF is inherently analog. It's a continuum of parameters. The states, the channel, the noise, everything about how RF gets from typing a text message to the other cell phone receiving the text message is all included in what we mean by this, RF modality. So just as an example, I grabbed this image off someone on the internet was talking about their Lamy Nice pen was dripping ink everywhere. But I can read that. It says Lamy Safari White, right? Hopefully it doesn't keep blobbing like this, but it is. Frowny face. Thought this color would look good for Christmas. Notice that I didn't care about these 3 sets of horizontal and vertical lines. I didn't care about blobs. I didn't care about the fact there was some blue text in the upper left. I didn't care about that it was on graph paper. There are some other squiggles in there. In RF, that would all be a part of what you mean by this collect. My click is intermediate. There we go. Go ahead and tokenize that for me, please. Because now you have to include all the blobs, all the wiggles and the squiggles. Because what I secretly did when I saw the 3 vertical lines there, I don't have to read those because those aren't human text. That's not meant for me to be, to understand. I don't have to read that. But a priori in this spectrogram here, and even there's a bunch of pre-processing that's gone on to even make this into an image, I don't know what I should pay attention to and what I should not pay attention to because the RF spectrum just is that hideous. And I might have to do quite a lot of computation to even figure out, should I look at this signal or not? Is that intended for me or not? Do I need to pay attention to it or not? So how do we tokenize this might be very, very difficult. This is again, a pictorial, take your favorite, speech or image or text. There are very easy, straightforward ways of converting that into a tokenizable data type, tokenizing it and putting it into your favorite model. The click is like right angle. Is someone else clicking for me? I appreciate you. Oh, thank you. Nice job. So again, here is this. It's actually quite difficult to find raw RF signals to put in here without going and doing a wideband collect because literally no one looks at the raw RF data, but it looks hideous. I'll give you a hint. There are 6 signals of interest in there. What a preprocessor for a pre-tokenizer would look like is a bunch of blocks that you may or may not have to run. Like I don't know what has to go on in here. And in fact, I'll just should I point? Okay, sweet. Go ahead. What goes on in here? Some might you just have to run and get the null result. This is a thing I don't have to pay attention to, but I had to run it anyway. Some of these, as a friend of mine who lived in Boston for a while, might say this is a wicked hard problem that might be impossible to do. Some are computationally incredibly expensive. Some can be sequential or have to be sequential and some can be parallelized, and some can be enabled or enhanced by AI. Some just can't. So one of these might be a Fourier transform. Don't train an AI model to do a Fourier transform. It already exists. It's called a Fourier transform, right? So that's why I think this is just so hard to get at. And each one of these little blocks could be a very difficult problem that someone and some people have to get together and solve over many, many years. Okay, so it's not tokenizable. That's great. I'll just use a model I cloned off the shelf off Hugging Face, and that's fine because someone's already done that research for me as well. It's not exactly that easy. So here's a lot of Mike's thoughts on why AI plus RF is hard. Sensors and sample rates. I'll just quickly get some of these thoughts out on paper. Again, I'd love someone to push back, but wideband SDRs and RF systems on chips can generate billions of numbers a second and dump them on you. And AI is just not ready for that kind of throughput, right? Compared to where, a medical like imaging center where I used to work at in radiology, doing MRIs and CTs and X-rays, those can be large, but they can take minutes or hours to collect. NLP in speech is limited by just how fast people can type on a keyboard or how fast you can speak, whereas the new advent of software-defined radios can generate terabytes of data in not very much time. So that is one way in which modern AI is not quite ready for RF. The features and the noise effects that go on in RF, right? Things like fading, things like Doppler, that clock drift, phase offsets, right? Things like this that are just inherent to how it propagates. There's also there's not a great analog in computer vision, but signals can be below the noise floor. If we went back a few slides and there was that hideous RF collect, well, there were 6 signals of interest that I knew about, but there was actually 2 other ones that were just below the noise floor, and I would have no way of knowing unless I had some other operator knowledge I could go and find it. Also, that's very important is that we have to learn what a cat looks like because we don't know what cats look like a priori when we're training computer vision models. But we know what the features are in RF because a human designed them and put them in and then transmitted those features. So we know already what the features of an RF signal are, or at least someone does. Maybe we don't. But someone had to design it that way so that it could be useful. So there's another big difference in the structure that we're putting into RF signals as opposed to learn what cats and dogs look like is just harder because the model doesn't know, or there's no easy way to convert into ones and zeros what this cat looks like. The depth of research, the physical, first principles that underline a lot of RF and electrical engineering. So things like Shannon's limit, the radar equation, right? Nyquist frequencies. You can analytically calculate array factors, match filters can be optimal, right? There aren't as many decades or 100-year-olds or hundreds of year-olds foundational principles that stop some, task from being impossible or very easy. Luckily, there are people that are working, like a previous speakers are working on these kinds of limits and statements we can make about models, but those are maybe months old at this point, years old, not the hundreds of years old potentially that we have for some of these bounds. Obviously, these aren't hundreds, but even decades. When it comes to, I didn't know what to call this one, classes and data types, what can you learn? When it comes to things like, I have a pointer, digital modulation schemes, some classes are wholly contained within other schemes, and that's just by design. There's no way to disambiguate those given some different ways that you could collect on it. There are spurious emissions that become part of your intended emanation to be an unintended emanation that can be collected on and potentially used either against you or can make your own collection bad. Something that is another interesting one is device fingerprinting, where if I want to classify a specific radio and say, oh, this is serial number 5. If that has a defective or somewhat unique antenna and I switch that out for a different antenna, maybe I can't find serial number device or serial number 5 anymore. I can find that antenna when they plug onto a different radio. Now, is that classify? Does that count? Do I want to track where the antenna is? Maybe that's good enough, but that's definitely not fingerprinting that device. And how I do that without being able to get a hold of this antenna might be very difficult. Another one is that this is actually a confusion matrix that I made. that trying to classify different forward error correction codes. There is a nice little corollary to Shannon's limit that if you're sending data rates or you're sending data at the maximum rate through a channel, it will look random. And if two different error correcting codes are at that limit, they will both look random, and thus you cannot classify them because they are statistically random. There is no way to classify these two forward error correction codes apart when they are operating at Shannon's limit. So that just inherently puts a stop on, no, well, you can't ever do this problem with AI. No one could ever do this with any calculation because these two things are statistically guaranteed to be random. So you can't tell them apart. And then lastly, again, as I mentioned earlier, just the breadth of how wide RFEM is. It's multi-scale. Things have to happen they can happen on the seconds, minutes, hours, and it's non-real time. They can be near real time, or they can be real time, literally happening in nanoseconds in analog on the device. They're multi-OSI layer. They're working on different levels of how we communicate. And then just the multi-application. Shout out to Sandia has a public little clip here of SAR, where they can use radar, electronic warfare, communications. There's a wide array of things that RF can do. And so makes it very difficult to have a one-stop shop, silver bullet for every RF application. So how can we apply this to national security? I had a couple other slides in here that I was going to put together, but honestly, I kept coming back to size, weight, and power. This is the biggest driver in my mind. That is like why you can't use large language models currently for some defense applications. And that's just because a server rack, you can't ask the boots on the ground soldier just to slap a server rack on their back and walk around with it. They already have enough stuff to carry. That's a lot of batteries, I'll tell you. It's a lot of other pieces of equipment that are crucial, and now you want them to carry around these 16 GPUs because you have to be able to ask a large language model how to do something. It's very unlikely that will happen. As we're pushing towards smaller UXSs, right? So how are we going to get some of these developments onto small platforms? And then again, shout out to NASA, a great picture on their website. NASA could have the coolest large language model possible that would classify some really cool terrestrial something. Well, but getting it to run on a satellite might be very difficult in an already swap constrained platform. So I think this may tee up the push to, we need to find ways to make AI solutions smaller, more lightweight, make them able to run on edge compute. There's a whole slide that I had worked up that was just how we can get AI to run on FPGAs. That felt like a little bit too in the weeds, but maybe a follow-on discussion. But we need to be able to take existing platforms, existing pieces of compute, existing programs of record, and get these cool AI models and all the solutions that we have to run on them, as opposed to the next platform that we field has to have the 32 PCIe card slots because we have to slam a bunch of GPUs in it to get it to do what it needs to do. So that might be, how do we integrate AI in existing RF systems? Again, placeholder for all this cool, awesome AI research combining RF. If you click forward one, I asked a large language model to give me a summary of some cool AI and RF research that was being done. This is a small slice of it. Each of these pointed to some papers or that was a title to a part of a report that had a bunch of papers in it. There's a ton of really cool and really state-of-the-art combinations of AI research, and not just AI research in the vacuum of we started from a blank AI model and trained it to do something. A lot of these, and most, near 100%, are combinations of very well engineered, very well understood DSP concepts and principles, and applying AI in, I think, very intelligent ways, ways that are designed for the modality, designed for the application, that aren't. I was talking to another attendee earlier. As a physicist, I can make fun of us. We always want to do things from scratch because if someone else has already done it, it's boring and they didn't do it the way I want to do it. So I'm going to start over. But you can't do that when it comes to RF because it's been around for 100 years and you're 100 years behind. So you have to start where the field is, right? You have to start where 5G is, start where SAR and incredibly well-engineered radars and digital communications are now, and find ways that AI can, enable those to be better, enable those to have wider margins for error, enable those to know when to change parameters, know when to twist knobs, so a human doesn't have to do it, right? But I think the only way that we're gonna, I guess my takeaway, there you go. The only way that we're gonna have real meaningful breakthroughs, I think, for Department of Defense, I see for US government at large, is we have to be able to take these new RF engineering and DSP principles and then inform, domain-aware AI. And that really comes down to EEs that know AI stuff and AI researchers that know EE stuff. And, as much as maybe I like to think because I'm zoomed in, there's a lot of crosstalk, and I get to talk to some amazing engineers. There, I don't think is as much crossover and overlap and cross-pollination as there needs to be moving forward. So that might be it for me on time. I'd happily take any questions, comments, concerns. I was hoping to have more questions asked of me than me saying stuff. Oh, yes, well, thank you. Okay, yeah.
Okay, I'll ask a question. So, one aspect of what you talked about, this continuous signal, if you will, that comes from RF, it reminds me a lot of speech as well, right? I mean, speech is basically a continuous signal. There might be multiple speakers in a room and so on and so forth. But yet we are able to do it there, right? So other than the fact that, RF is operating at gigahertz, speech is operating at kilohertz, put that aside. But from the kind of the fundamental, construction of the signal, right? Couldn't you still apply the same kind of ideas there?
Interesting. A colleague of mine raised the same question, and I thought, oh yeah, it's fine. I'll answer that when I get there. Great question. I would say that in general, we have two very different ways of doing these two things, right? So if everyone in this room was trying to talk right now, I could not understand what you were saying. I would say, hey, everybody be quiet, right? The cocktail party problem is hard. And in general, when you're talking to ChatGPT and asking it to do stuff, if there's a bunch of people talking around you, it won't understand what you're saying. It'll get things wrong. We usually tend to use speech to text and things like that in very clean environments. Also, speech tends to be, at least, for a given language, tends to be very structured. There's only so many words that I can end this sentence with, right? I mean, like, I can't just suddenly start saying stuff that doesn't make any sense given what I said before. Whereas, right, if we could see RF, it would be an amazing kaleidoscope of, stuff, right? That actually everyone is talking all the time in RF, right? And that's okay because they can cooperate together through, again, a ton of really interesting, novel engineering ways of allowing this to happen. But the spectrum is just so much denser that if everyone was talking all the time and there were natural, like the bird sounded human and the squeaky chair sounded like human speech and everything around us sounded like human speech, I would be up here also talking about why human speech is hard to tokenize, but just in the ways that we tend to use human speech, at least to interact with AI, it tends to be a much cleaner channel, much easier to do. So I think in principle, yes, you are correct. Speech would be way harder if it had to compete in the same type of environments that RF has to compete in. So I guess that'd be my answer.
Has there been headway on embedding functions that try to attempt to tokenize RF, and what are they?
The ones that I have heard of have been on the back of like cocktail napkins, as they we should make an RF tokenizer. Yeah, we should do that. How you would actually go about doing it. So I mean, people have done narrow ones. There are things like pulse descriptor words and other ways of taking narrow parts of RF phenomena and making them into kind of categorical, lower dimensional representations, but those still have floating point numbers in them, right? So how you take a phenomenon that's inherently analog that has, right, I can change one number from 900 to 800. I know that's a completely different thing that I would want to tokenize, but how you tokenize floating point numbers is still unclear to me. I think ultimately it will be a combination of some existing methods that people have done that we've used for many years to maybe start filtering, right? You maybe have to classify first or spectrum segment first, do some high level coarse grain there is probably a role in here for some kind of large language model agentic thing to start figuring out what I should do next, given all these just traditional RF engineering inputs. What should I do next? And then do some AI classification and then get the results from that and then show that to a human, and the human decides, like, this is what I care about now. And the agent goes off and does something else with all this different data. So I think making a RF tokenizer from scratch is probably very difficult. I think that we're not starting from zero. There's a lot of work that's already been done just, by humans figuring out how we can talk about RF things that isn't just, I have to show you a picture, that we can start to semantically talk about how RF operates. It just needs to be a lot more general and fill in the gaps potentially. Maybe that's where something like AI would come in.
So one of the things I've thought in this domain, and I think, Michael, you already touched on it, is that given the complexity of the RF environment, this may be one of those domains where pure automation isn't what we're aiming for, but what we're aiming for is human assist. So this is an example where technology and humans working together can partner to decipher what's happening in a spectrum congested or congested spectrum.
Yeah, 100%. Especially, with respect to defense and other applications. Certainly, you want a human in the loop who is, very well said. I shouldn't try to restate what you just said, but yes, because RF operates so quickly, because things happen so fast, and because the environments are so dense, that it's likely that the human end user is looking at something potentially much more important, right? They don't have time to take off their gloves and dial the knobs on the radio. They need the radio to do what it needs to do, and potentially just offer up hey, I've got two different coasts for you. Which one would you like? Here are the pros and here are the cons, and the person picks one. So I think something like that, where yes, there's maybe some low level automation, which a lot of our equipment already does, right? Like the pilot of the plane doesn't have to tell the radar how to do what it does. It automatically does things and shows a dot. So I think in the same way, we might need some automation on top of that, or excuse me, some automation that enhances that and distills all this dense RF data plus other context for a human just to look at and say, yes, I want this one, or this helps me achieve what I want to achieve right now. As opposed to, again, a person having to, the 18 Echo is already busy enough, right? The Como, guy in a soft team, they already have enough stuff to do. They don't need another tool to help them operate the radio. They need less tools. They need the radio needs to be more autonomous. But that's where, maybe this wasn't where the question was leading, but I think engaging with the end user and engaging with, like, hey, this is going to make you take your gloves off because the button's tiny. Do you want this? Yes or no? Or would you ever use this? Someone might say, no, I would never use that. Okay, well then don't make that thing, right? Ultimately, we're supposed to, reduce friction, make a warfighter have a decision faster, distill data down into useful stuff quicker, enable a mission they couldn't do previously. So I think engaging with end users is obviously, I haven't mentioned it in this brief, but it certainly is crucially important, just because you need to solve a problem that someone cares about. Let's figure out what the nail is before we make a hammer. Let's not build a hammer, then show up and just say, hey, everybody, I hope you have a lot of nails because we have a sweet hammer.
We're running out. Thank you very much. We are running a little bit late, so we're going to have the panelists come up for a very brief panel discussion.
At 3 o'clock.
Okay. Sorry, we'll have a break now. Then we'll have the panelists come back at the very end. Thanks. Thanks the speaker again, all the Michael and all the speakers.
Oh, I can.
No, I think
I think it was last week. I've got them too. All right, we're reconvening. I'd like to introduce our next speaker, Dr. Uttam K. Majumdar, who is currently at the National Geospatial Intelligence Agency. He holds a doctorate in electrical engineering from Purdue University and is the author of the book Deep Learning for Radar and Communications Automated Target Recognition. These days, he works in the same field that I work in, imaging radar, and having authored a book on this topic, I thought he'd be a good person to talk to us about some of these things. So let you go.
Okay, thank you, Laura. Hello, good afternoon, everyone. So my name is Uttam Majumdar. I go by Tom. So yeah, I think actually previous author kind of set the stage for RF discussion. So here, I was like about 20 years at Air Force Research Lab. So basically, I work on RF radio frequency automated target recognition. Otherwise, AI, mostly we know that, okay, object recognition or computer vision. But in radar or synthetic aperture radar, mostly we are interested to see object of interest or target of interest. So that's there's a long history for Air Force to work on the radio frequency domain, in particular for the imaging radar and how to recognize the object or target of interest from here. So then, as things evolved, by 2012, DARPA, they're saying that, okay, well, we did object recognition from SAR or imaging radar, in a different way. It's called template-based approach, meaning that you put a template of an object of interest and try to match and recognize what type of this is, T-72 tank or something else. So then that's brings to DARPA into, okay, how we can bring deep learning or modern AI for recognition. So then 2014, DARPA Strategic Technology Office, there ran a program called TRACE, which I was heavily involved in, to apply deep learning or AI for military object recognition. Then 2018 or 19, there is a program called RFMLS, RIF Mills from DARPA MTO. So over there, it was the goal was more of how to recognize a signal, RF signal. So as you know, like a previous speaker mentioned, so RF signal, span from, all the way to the seabed to the space. So from basic communication signal, like your cell phone recognition or signal recognition from the cell phone, ADS-B signal, which is like the aircraft signal recognition. Then of course, like IoT, Internet of Things, signal recognition. So in a nutshell, RF, when we talk about RF, we think of both from imaging side and then also the communication side. And within the imaging, there is military imaging, and then there is medical imaging. So medical imaging, like, from MRI, or think of like an X-ray, which was actually one of my area in my, in my PhD research. So the how to recognize like a tumor versus a non-tumor kind of with a vision or computer vision approach. So that brings to me that, okay, when I was in AFR also, there was a need that, hey, we know lots of image recognition for SAR or radio frequency, but we don't have any book. So that's actually kind of helped me writing these books. This book came out to 2020, Deep Learning for Radar and Communication ATR. So as you can see, like when I think of RF, so I knew that it will be confusing what RF we are talking about. So as I was very specific for radar and communication ATR. So that's actually the book that has comprehensive discussion on classifying RF object and all of the problems dealing with that. And then we found that, okay, well, RF for communication is also really complicated. It has so much things. So we actually have another book. It's called Essential Principle of Signal Collection and Signal Collection. So that actually focus on more RF signal classification. So I think previous author mentioned lots of issue with that. Actually, that book capture more of the communication signals issue and AI, and this is more of the imaging radar and AI. So now I'm going to the main topic is adversarial ML for radar literature. Actually, as you know, it's very hard to do public release and things like that. So that's why we have to be like soft. What do we mean by adversarial machine learning and things like that? So basically, it brings to that, we got AI. Yes, AI can recognize the things, and previous presenters showed that the images could be corrupted or manipulated or could be doing something like diffusion model, like you can like a noise induced new imagery. So they actually cause like AI not performing as we expect. So that's actually the term people try to use, like adversarial AI. So it's a very important topic of interest, like so basically our adversarial attack and things like that. So duty relevance here is like is very important. So hopefully like the audience here will see that what's the importance to tackle like the adversarial issues with the AI. And next slide, please. So here's like I try to put those things I presented like these things with a IEEE distinguished lecture series. So here I try to say that, okay, well, there are some misnomer, like people have bad understanding of what is AI should do and why it should not. So now for AI, when it works and why it doesn't work. So I try to frame that, okay, AI works because when we have sufficient statistics. I think the first author mentioned like a couple of times the sufficient statistics. So basically, we try to say that, okay, any mathematical solution or engineering problem, do we have a closed form solution or not? So that's the fundamental issues that, so as we adopt AI, we are not answering that questions. Is our data describes like the, as the closed form solution? So the answer is in many cases, no. So data is a probabilistic space, and you can manipulate the data or add the data, we add Gaussian noise. Many ways you can manipulate the same image or same data, so many ways. So therefore, we do not have a closed form solution by the AI. We are getting a solution, not the solution. So that's what I try to bring, the closed form solution and the convex function. So next slide, please. So now, when you say closed form solution, I think I don't have to say that, okay, what is closed form solution? So we know one solution that kind of gives us the answer that we are looking for. But if we do not have any closed form solution, we are not supposed to get the solution. We'll get different solutions. So the question is, sometimes we get good results, sometimes we get bad results. It depends on, is the data we use for training, is it good or bad? So the basic theory is like AI will never give us the solution, and we have to live with a solution. And so the question is, how good is the solution? Whether we can live with this data or not. So, but the conclusion is that we don't have a closed form solution for AI solution. Yeah, next slide, please. So yes, again, like it goes from the fact that the convex and non-convex. So many of those AI that optimize, they are non-convex function. So when you deal with non-convex function, you never should expect that you get a closed form solution. So therefore, that's the fundamental limitation for AI. Yeah, next slide, please. So again, deep neural networks, these are like, also built on like a non-closed form, solution. So therefore, only thing we can hope that we can get near closed form solution. So the near closed form solution, even though it's like not a quasi kind of, bad term, like, it's not a good term, but what we say that near closed form, that are you getting consistent accuracy, consistent results? So that's what we mean by near closed form. So the near closed form come from that, okay, hey, if I have an operating environment, operating conditions, if I take this data for training, and if I match the test data with the same operating conditions, then we can expect to get a good results. So that's what I think we mean by near closed form solution, and we can guarantee for consistent results. And also sometimes people say, okay, does adding more samples achieve better accuracy? I think it depends. So the data has to be really genuine. That's a diverse data set, not like the millions of samples that I can have from the same location, same geometry for an RF sensing point of view. It will not add you extra information. So anything we are thinking like adding data, it has to really diversify the data that gives me more information. Next slide, please. So yeah, so that goes to the fact that, okay, how can we tie like, maximal likelihood estimation? So here an AI for classification, we can say maximal likelihood classification. So it depends on, we have a class 1 through n. So how can I get the best classification? So it depends on, like, again, if I have a theta as a salient features, so my training data should capture all of the salient feature. So the meaning that, like, like as I mentioned, like I should not have like thousands of samples from same geometry and I'm getting the same features. It's not giving me extra information. But if I turn around like a 360 degree or, azimuth and 0 to 90 degree of elevation, so I diversify my geometry and I can get better, samples. And so maybe I'm good with 500 samples will be good enough. Like, for example, we try to do an experiment, like say T72 tank with a SAR. So I collected 18,000 samples of data. So I'm getting 99% accuracy. Now the same samples, I found that, okay, well, what are the redundant data? So we tried to take out all of this redundant data, and we found that only 500 samples are good enough. 500 versus 18,000, which is like, 36 times more or something like that, more data. So sometimes people have bad things that, oh, more data is good. Actually, no, it should be sufficient statistics, and then it captures the salient features, and then these are diversified. So that's actually the solution. So more data, I think it's a bad term. Like, we have more data that has diversification and good, good information into it. Next slide, please. So again, like the main takeaway is that, we have to, when you do the AI-based classification, we have to have salient features, information to the data. So that I think our classification will be good, and there is no excuse for that. So the main takeaway here is that, AI ML is not just a magic box that you give the data and as an input and you expect that you'll get good results. What data we input, we should know that. Otherwise, like, it's like it doesn't make sense. Next slide, please. So now one thing happened with like the military object recognition is that we have like an actual target and then also surrounding background information. These are also bad. So then that brings to the maximum likelihood estimation and also, the map, maximum a posteriori information. So basically what it says that I have the actual target information or image, area information. And then if I add the imaging scene information, like a prior information, okay, where I'm looking for the object, is it to the open field or into a, urban area or somewhere under the trees hiding? So if we add those information, so basically what it says that, okay, if I have target information and I know the prior information of what area I'm imaging, it will reduce the false alarm and you get really good results. So again, these are kind of tied, like, as intuitively, like how digital communication work, like maximum likelihood estimation or maximum a posteriori estimator. So these are exactly the same thing works for AI as well. Next slide, please. So like here is what I mean, like, sufficient data for object classification. So as you can see, if you have an object here in space, in RF domain, so it should capture the whole space, because when you sense like a different angle and geometry from satellite or from from airborne platform, I can see if I capture only limited, geometry, I can see only the back of the car or a vehicle or front of the car. So theoretically, if I make a complete, a robust model for no matter how it should work, it should capture all 360-degree and all elevation as much possible. So that's the one condition. But other condition could be that, okay, no, often we do not have the capability to see the object from all 360-degree. So we have only limited, azimuth and elevation or limited, graze angle for the target of interest. So then what should we do? So we say, okay, fine. You make the model state the constraint that this data has been collected to this geometry, this azimuth elevation angle or this, radar frequency, so that your model has been developed based on your known information or metadata information that And then when you test, you should match those, testing data information like operating condition, geometry, or collection geometry. Do they match? Then you can be guaranteed that, okay, hey, yes, I trust my results because it's matched the same geometry. Otherwise, these results doesn't you'll see that AI doesn't give us good results. Yeah, next slide, please. So the conclusion is deep learning based classification relies on robust and reliable model development. So the sufficient amount of samples should be masked, that capture the salient features. And we should not accept simplistic statement, okay, more samples always better for AI ML, but actually we need to get it. So hopefully I think that also brings to the issue that, okay, well, how do you get more data? So now that actually brings to the synthetic data generation, in RF domain, you can use XPatch or other tool to make up the gap that if you need more data or synthetic data, you can generate. So the basic conclusion is we should know what is our limitation for model development and where it should work. Otherwise, we just cannot randomly say that, okay, I make model is 99% accurate. It doesn't make sense at all. Yeah, next slide, please. So now, next slide. So these are more of a if you apply this technique to the SAR image classification, what can you do? So this paper was actually more advanced and more a comprehensive paper that you'll see that in literature people are referring, so that how we can do the adversarial AI kind of sense, what kind of tools we have to mitigate those this problem. Yeah, next slide, please. So here, one of the problem with the SAR or RF, based object recognition for DoD application is we do not have lots of data. So the only few data available is called MSTAR data. So that's actually available through Air Force Research Lab. And there is also another data set called CVDOME, Civilian Vehicle Data Dome data. So these are kind of used for some of the results. So I'll try to show some of those results from using this data set. Next slide, please. So again, when you say adversarial things, or we mentioned a diffusion model, how do you add noise? So yeah, Gaussian noise, like the previous author says, yeah, these are good, but these are more homogeneous. So these data, what happens is that you can predict that, okay, hey, if I add this number of noise, what kind of classification accuracy degradation happen? However, most of the adversarial attack, that people say that these noise are called heterogeneous. So meaning that this noise doesn't have any continuity. So they are kind of different places. They can be in a different way. So one of them is a simple one is called fast gradient sign method, FGSM. So you can add noise to your imagery, that method. So there is also another called PGD, a projected gradient method. Then there is other random noise, and there are no many Newton fools. There are so many other ways to add those. So the problem is these are heterogeneous noise. So you're developing a model, based on this data set, your model has to see it. Otherwise, these are not as easy, the Gaussian noise. Gaussian noise problems can be solved easily, but adding those noise, you need really very advanced model development. Yeah, next slide, please. Yeah, so next slide, please. Maybe next. Yeah, I'll quickly go through. So here are some example, how, let me see if okay, you can see that if you random noise, so epsilon, these are actually different level of noise intensity and how the targets looks like. So, and these are FGSM and these are PGD. So the things I'm trying to show here is that like radar imagery or RF imagery, like it's compared to electro-optical imagery or video imagery, is that but visually we cannot see the difference. Like, here, like, this same object, like a tank, looks like, oh, these are like, these all four of them looks like same. These all looks like same. But actually, like, the AI fail. Like, if you train the model with, let's say, for example, this object, but if you test with that one, it will totally misclassify. It will not know that. So here is like a challenge with RF, that like if you're an analyst, visually you'll see the two images look like same, but AI really fail badly. So that's one of the area of a challenge. Next slide, please. Maybe I'll skip that one. Yeah. So again, like, we try to do like how the adversarial attack happens to different model. So the basic conclusion is that, like, if you have a complex model like ResNet 18 or VLEO V8, like those type of model, if the models are really built on like a lots of complexity with a large number of parameters, they actually survive better on adversarial attack, or like when data has lots of noise and things like that. But like a simple model, like if you like a 2-3 layers models, yeah, those doesn't do good. Yeah, next slide, please. So here again, like these are like synthetic aperture radar data set. Like as I mentioned, like these are like how, how some of the military objects looks like, and then these are like the civilian vehicle, like how they look like in SAR. So as you can see, like an RF imagery is not like a one-to-one exact visually. They look like the electro-optical imagery. So the AI, while it helps us, but little bit of perturbation, like a noise, like perturbation, does really bad thing, like a bad classification accuracy. Next slide, please. So yeah, so here is like some of the things, like, we try to show here is that, like, when you have, like, ACON, CONV-B, ResNet 18, BGG11, and ShuffleNet, so across like a different, like a model. So we said, okay, if adversarial perturbation happen, if I do not do anything, which model do good? So the basic conclusion is like ResNet 18, like the green line, they actually perform good, even if you do not do any good adversarial training or not. But even if you try to develop like a model with adversarial things built in, but like the ResNet 18 is a good. So the basic conclusion is anything we try with AI model, like, for image classification, ResNet 18 is a good model to pick. Next slide, please. So yeah, here is like also like, some of those noises are really bad. So even though we can try to use like, like a adversarial training, but sometimes they do not like really do as good. And like, so for example, like here, epsilon, training epsilon means that here we added more and more complex noise. But like as I said, I think what we found that like that ResNet 18 do better than any other model. Next slide, please. Maybe I'll skip that one. So now, like, other things come out, like, say, if you have like, some, like previous author mentioned, like an RF environment, they interact with so many other signals as well. So what kind of signals can do good or bad? So we try to analyze, okay, if you have like, radar signature with a horizontal polarization or HH, so now if you would like put like the phase error, like say, you can measure that the error could be like, could be intentional or unintentional. So if we add the phase error like as a cubic, quadratic, and sinusoidal wideband, so we found that, like, some of those kinds of error could be very detrimental, and they give you really bad results. Your model doesn't work. So in particular, like wideband and these kinds of noise, like really cause a big problem. Next slide, please. So like as I mentioned, like, like here, this kind of shows that so two things from here, like, again, we tested different types of noise, but we found that ResNet 18 does better, even though it doesn't capture all of the good results. And also, like a wideband noise are very hard to mitigate. So basically, conclusion here is that, dealing with RF signal classification or object classification, it's a huge challenge problem. That's the bottom line. Next slide, please. So conclusion, like, we have to deal with like an adversarial training based on what kind of data, what kind of noise we have. And then if we use like a better model like ResNet 18, that tends to do good results than anything else. So I think with that, maybe I'm out of my time, and I can take some questions if you have any questions. So this is like kind of a really like I give you an overview of how the problems in RF domain arising, but we have like more complex situations like to deal with this RF signal and RF based object recognition. So but again, it's a challenging area that to work with. Yeah, that's all. Yeah, I have. Thank you.
Are there questions from the audience? Please,
Sure, yeah. Yes. And thank you very much for this nice talk. So you say more data is not necessary?
Yeah, more data, like say, again, these are like, if you talk with a kindergarten student versus like high school and college. So when people say more data, so more data could be at some point redundant. So let's give an example. If I like to represent this object, then we get four samples, north, south, east, west, because I can see back, front, left, right better. So now you can say, okay, what about I can take 1 million samples? So in that sense, 1 million sample could be too much. So that's why you don't need it. But also another way to answer that question is, like say, if I adding my 1 million samples, is it adding me, it's redundant information. Is it adding any extra information? No. So I'll rather say that if all my samples are from bottom side, I'll diversify other side. So if you have diversified, more data could be good. But at some point, like say, if you think of information theoretical point of view, or laws of large number that someone mentioned, you are already saturated. So what do you do with the more data? So that's why it's like, as a mathematician, you have to be precise, like, more data for what? Like, is it giving me more information? So yeah, if you, like I say, I have a 95, I put my 97% classification accuracy with 18,000 samples all around for a target of interest. But I found that I need only 500 because I skip some of the angles, because as like say 1, 2, 3, 4 degrees of azimuth, they give me the same information. So I skip 1, then 5, 10. So in that way, like, and I take only 500 samples carefully. And so that's what we mean by sufficient statistics. Like, how do you know that what samples are important? So if you have no way to know which one is good or bad, fine, you add it. So because those things will add to the computational complexity, the training time, and all of those things will be giving you. So there are like, significant reason like why you shouldn't be doing that. So actually, like, there are technique called active learning. So they actually can give you that, okay, hey, if you any inputs, new samples come in, you can examine, is it giving me new information, or I already have this information. So you can omit those information. Yeah, I think did I answer your question?
You did. It's just, how do you know that when you start? I mean, how do you predict the sample size that's necessary? We tend to use more and diverse patient population, for example, to get that. But we find that if you look at the ROC, for example, it's always much better.
No, so I think the question goes to, okay, not too less, not too much. So that's what I mean, like to go to the things. Yeah. So then, like say, yeah. So you can like say, so medical diagnostic or medical information, like, yeah, like more samples, more. So again, it has to be like populations of the people's age, then race, and then different circumstance. So those are like diversified information. But if we know that I'm taking this sample for this target from this azimuth and elevation, so I already got it. Like 5 is good enough. But if I take 100, I'm not adding any extra information. That's what I mean. Yeah. Sure. Yeah.
Ralph?
You use the word in your talk that will show up in my presentation. And I just wanted to get a context of what you mean. You said salient information.
Yeah.
What do you mean by that?
The salient features means that let's say T72 and T62 a target, like say, for example. So assuming that T72 has 7 wheels and T62 has 6 wheels. So salient information is that, okay, hey, these two objects look like exactly same. Only difference is that one has one extra wheel. So now if you measure T62 or T72 doesn't capture the extra wheel, so you are missing the salient features. Like, that's what's the most critical information. Or one object may have a antenna erected. So that was salient information. So if you did not capture, that means that's wrong. Actually, some of the adversarial things came out. People try to say that adversarial things comes mostly like when two targets look alike. Like say panda and gibbon. That's one good example. People try to say that. So they look like the same. Like say, or you could think of a twin. Like so, our human eye, we can say, okay, who is what, right? So the machine should mistake the same thing because I'm getting the same face, same structures, right? So that's what I think the salient features.
And do you have a mechanism for measuring that saliency? For
Salient feature,
determining
like
that degree?
Mechanism could be that, okay, you measure data. The measured data is very, very important. Like, so when you do the measured data,
Measured data is?
so measured data is actually, let's say, when you say, let's say radar literature. So like say measured data means that, okay, if I know that my operating conditions, I'll be collecting this area or this geometry. So my actual radar data, like real data, should be from that particular angle that capture those salient features. So yeah, so measure means actual operational data that you would like to see. It could be synthetic data too, you can do it. So meaning that you actually have representation. You cannot just make it like say, hey, a tank has a barrel. So you cannot have a tank without barrel. It has to be there, and that's a salient features, and it has to be in your collected data, like operational data or synthetic data. It should show that this is what it is. Or another way of saying that, like say, hey, I may say that I have only one hand, right? So if you do not see my other hand, and you think that, oh, I should have two hands, that will not work. So I'm missing one of my salient feature, right? So that's what it is.
Thank you.
Okay, thank you.
It's my pleasure to introduce our next speaker, who is Ralph Etienne Cummins. He's the Julian Smith Professor of Electrical Engineering at Johns Hopkins University, and he also was a founding director of the Institute for Neuromorphic Engineering. Please go ahead.
Let's see, does that work? Yes. So I'll be driving. Only reason being that I got some weird videos that may need to be intervened with. So thank you so much for having me. Thank you so much for inviting me. It's great to hear all these great talks and meet lovely colleagues. So I'm going to be talking about sparsity and the importance of sparsity in artificial intelligence and how we get there. Why do I think it's important and so on. This is my lab. I study all kinds of weird things, sometimes animals with multiple eyes. But anyway, this is a plot that is essentially showing the cost of the various models that are currently run by the various companies around the country, right? Actually around the world. And we see that it takes a lot of money to run the LLMs that are out there today. In fact, we don't quite know exactly how DeepSeek got their numbers so low, right? A lot of people say, well, there might be some subsidies that's going on there that's not being accounted for. But nonetheless, the total numbers are ridiculous. And the reason that is the case is because at the end of the day, this is kind of a typical flow of information that happens in a transformer. You are talking about a lot of teraops that needs to happen, and you need to do a lot of matrix multiplications, right? That is really what kills you. And all these, even though there are, parts that are being labeled as attention, and and there's that paper that we were just talking about with Carrie Laurent called "Attention is All You Need." In the end, it's not real attention that they're using there, right? It's basically just a max operation that is going in there. But there are ways maybe that you can manipulate the, excuse me, let me see whether this works. You can manipulate this matrix, that comes in as part of the attention in order to make it a little bit more realistic in terms of what actually attention means. And I hope that as I walk through my talk, you'll get an idea of what I mean by attention, what I mean by saliency, which is, the term that was used in the previous talk. So what is it that we can learn from biology to give us a sense of, of what are the various ways that potentially we can improve AI in the way that is currently implemented? Now, I must confess that I'm a hardware guy, right? I come from the perspective of embedded AI, right? I'm not talking necessarily about what goes into the cloud and goes into these big server farms, right? I'm talking about what can I do locally? What can I do under severe resource limitations, right? Low power. We heard about swap, from Michael's talk, those kinds of things, right? Size, weight, and power, right? How can we take advantage of that and so on, right? So this is a plot generated by Gerd Kamberg's former Hopkins colleagues, who's now at University of California, San Diego, where he basically says that ultimately, this is where humans live on this machine complexity versus task complexity plot, right? We do about 10 to the 15 synaptic operations per second. What is meant by a synaptic operation is essentially a signal that comes in that gets multiplied by a weight and then gets summed by a cell, right? And we do this only with 15 watts of power, right? I mean, it's ridiculously small, right? If you take the kind of the path of where we're going on in terms of deep search or deep learning, I mean, this is just, blowing, things out of the water. And that's why, we talk about increasing the accuracy of some of these GLNs by 5% will cost us like 10 to the 5 times the power that we are doing right now, right? I mean, it's ridiculous in terms of what is going on. So the need to compress power is important. So neuromorphic engineering is a term that you might have heard, bounced around, but it's been around since the late 80s, early 90s, right? And it came, yeah.
Yeah, quick questions. Have you worked with IBM True North processor?
Yes, I know, and I know all the guys who designed it. One of them actually was a former student who's now at IBM, Andrew Cassidy. But yeah, so that's that, and I'll get to that a little bit in terms of what it means to be a neural processor, right? So the whole point is that, with neuromorphic engineering is that we learn from all the different scales of the brain in order to come up with engineered systems, typically in the form of circuits, which is kind of the angle that I come from. I'm an electrical engineer by training. I'm kind of schizophrenic. I'm also a computational neuroscientist, and so on. So I live at basically on this green curve that we're trying to get towards, right? And the way to get there is if you look at the brain, you see that, in terms of activities in the brain at any one point during any type of computation is like less than 2% of the neurons are active at any one point, right? Again, this is ballpark figures, but it gives you a sense of what's going on there. And in terms of connection sparsity, cells even locally only get about 5% of the synapses to be active at any one point, right? And if you start to go globally, like kind of more longer distance, that number collapses by another factor of 10. So, everything in terms of, what is that you're computing and with what you're computing is essentially very, very sparse. Okay, so that may be a means for us to think about what we can take advantage of. So actually, I should take one step back and say this. So there's two salient aspects of this plot. One is the fact that neuromorphics, if you will, or the human brain takes advantage of collective analog computation. And then there's this notion of sparsity. Those are the two pieces that we're going to come back and speak to. So in the mid-90s, Chris Tomaso, who is one of the pioneers of circuit design, essentially came up with this notion that says, look, at the end of the day, the world is analog, right? Every signal that's coming in is coming in, in analog form. But computation, as we do today, is digital, right? So there has to be this analog shell that you have to wrap this, your digital signal processing into. So it means that ultimately, in this blue circle that I've drawn there, you have to have all your data converters, that basically takes analog signals coming in, converts it into some form of digital representation that then can be processed by either your CPU, GPU, FPGA, whatever you want to throw at it, right? And then once your decision is made, you have to communicate back to the world, right? And that again comes back in forms of, an analog representation. And it could be the form of a classification, a command, or an action that needs to happen. Well, I take it one step further and say, actually, the world has a sparsity shell that sits around it, right? And what I mean by that is that at the end of the day, the way that data is coming in at your sensors is episodic. Yes, I know that we talked about, RF just now, and we see, that signal may be continuous, right? But it still bursts. There are bursts that comes. Ultimately, if I'm able to do the feature separations that you see in speech, that's why I asked a question about speech, right? You can essentially find the domain in which those signals are sparse, right? And then you can sample at those sparse domains, and you end up again with a sparse representation. And this is the whole field of compressive sampling that comes into play, and the statistics of that comes into play. But once you pass the sparsity shell and then you jump inside, now you have the ability to ultimately go inside and compute in the domain or in the representation or in the code that you think is appropriate for what you're trying to do, right? You could do things, of course, in spiking neural nets, analog neural nets. You can think about edge ML, edge machine learning as whatever the processes that's responsible for implementing those. And you think about sparse recovery and all those kinds of things, and optimization that we heard previously talked about. And then once decisions are made, again, going back out, you still need to actuate in a sparse way, right? So given that you have this sparsity shell, then the question is, what can we do about it, and how can we represent signals in those ways? So for that, I'm going to give you a couple of examples of what is the kind of the state of the art now, and what do we do with these types of things. So in the end, then the flow of processing with this motivation is going to be essentially this spatial temporal sparsity representation that's going to try to mimic what you see in the dendrites, the synapses, and the axons, as well as the networks, in nervous system. What it means is that you basically have multiple pathways for signal to flow before you get to the decision making, right? You start off with maybe something where the weights of the network are sparse, right? So how do you get there? Or the signals coming in are sparse, the data, the input, right? And that's where the saliency information gets very important, as well as temporally distributed. Now, the modalities of the signals themselves as well can be within themselves label lines, right? Can be sparse in those representations. So that's kind of the flow of what we'll be getting to. So let's start with temporal sparsity, because that's one that is more kind of visual, and you can see what's going on, right? So, these are work of a couple of students of mine who are now, one is at Northrop Grumman, one is at Meta, doing very good stuff. But here is the kind of the idea behind what goes on. So in the 90s, Toby Delbruck and Carver Mead, you might know, is kind of the father of neuromorphic engineering. They were interested in modeling what goes on in the eye, right? They basically noticed that your eye you can walk outside in the brightest sunlight and see, and immediately walk inside in the darkest room, and within short time adapt, and you can see again. Your CCD cameras, before recently, your CMOS cameras couldn't do this, right? And the reason that your eyes can do this is because there are essentially circuits that, this is a model that actually got implemented physically, where there's a photodetector, but then there's an adaptive element that essentially shifts the operating curve of where your maximum sensitivity is to the ambient light, right? So that gave us cameras now that had, like 100 dBs. 100 dBs is about 10 to the 5 decades of sensitivity, right? So you can really see it. Moonlight to bright sunlight is 10 to the 9, right? So 10 to the 5 is a lot, right? Your cameras now can do this, right? So then I came around in the late 90s, early 2000s and said, look, what if I take this and I try to make it look more like what the octopus retina does, which is the octopus retina takes light and converts it to spikes, right? And the amount of light that's falling on each pixel is coded in the interspike interval. So a spike tells you the beginning of the, when I detected this light, and at some point later, it gives you another spike that says, this is, whoops, this is the length of the data. This is what the data means, right? So that had its issues. I mean, it worked. It was a beautiful camera, but it tended to let the brightest spots in the images drive the output, right? So then Toby Delbert came back and said, hey, what if, and Christoph Posch, what if I basically look for a change in light, right? So I'm not going to continuously give you an output if the light is bright and it's constant, but only when it changes. So now all of a sudden you have this, this constant decay that's happening after each image is presented, if you will, and the only outputs you get, only spikes you get are those that correspond to change events, right? So now you had a really beautiful camera that could, here you are basically taking this circle going around and you're getting frames where, the circle shifts, but you can have continuous frames, continuous data going out where that interspike interval captures the intensity. So this is now an example of where you've moved away from a continuous frame-based imaging system to a spike-based imaging system, which is sparse in time, right? That's really the key thing. But you can still do the kinds of things that you want to do. We want to do object recognition, we want to do tracking, and so on. In fact, the NeoVision project did exactly that. We're able to track cars, by flying drones and looking for birds zipping through the field of view in real time, and so on. And I believe this also was probably among one of the first implementation of, Yann LeCun's CNN networks on hardware, on an FPGA. And his student Laurent Farabert worked with us on this with another former student of mine. So this is now, you get into the point where your images are no longer this block of data that comes all the time, but it only comes out when it needs to. But here's the problem, right? If I am letting every pixel tell me when it's ready to output its data, I get this data coming at me, I get a spike. How do I know which pixel actually spoke to me, right? So now you need an encoding mechanism, right? So this is what the address event representation basically does. It says, I'm going to attach not just the the fact that this pixel spiked, but I'm going to say where that pixel is, right? So now the spike is really just the address of that pixel, right? Just you see the address, aha, that pixel spiked, right? What that also does for me is that it allows me to use a single communication pathway and to basically multiplex all these spikes onto a single line. So I don't need to have, n by n number of pixels talking. And then I just need a decoder on the other end that breaks it out and then sends the pixel to the appropriate place. But the beauty of this is that now I can do math on the address. So I don't need to do math on intensities anymore, right? So typical image processing is you get an 8-bit, 10-bit, whatever value per pixel, and you manipulate that, right? Now I do not do that. I only manipulate addresses because the value of that pixel is embedded within the flow of those addresses, right? So it gives me an additional computational capability. And it's asynchronous, so which means that if I do this right, I don't need to have a power-consuming master clock running at at gigahertz rate. It basically regulates the time that it needs to output data at its needs, and ultimately leads to ultra low power. Well, Prophecy, a company out of Paris, basically said, "Hey, this is a great idea." In fact, it was Christoph Posch who basically formed this company with some other folks, and they have sensors that you can buy. Right now with all these capabilities, right? Greater than 120 dB of dynamic range, extremely low power, extremely fast. So one of the applications of this is that is flying on the, I think on the space station, and he's taking snapshots of these lightning strikes that goes up to the atmosphere instead of coming down to the ground. I mean, it's just, an incredible, thing, seeing all that happening because they have like, microseconds response time, these cameras. And then on top of that, you can see the world as it rotates below the space station, and you can see cities coming in, and it's just a really cool set of pictures that they have generated. On top of that, they've now partnered with Qualcomm, and they basically, on your cell phone camera, you'll have one of those chips, one of those cameras on there, and those now will be used for, basically creating pictures without motion blur, right? When the classic things with the regular cameras, you move too fast, you just get a blur, right? But because of these event-based data going out, you can use that now to undo the motion blur with some of the optimization algorithms that we've heard talked about previously, but you can do this in real time, right? And take out the motion blur and spread it out. So really suggest if you're interested, checking out what these guys do. But they're also interested in some of the things that are of interest to the folks in the room, which is the defense, which is what exactly can you do with these cameras, and how can you drive drones, and how can you make sure that these drones are low power and operating extremely fast, and so on, which is what this next slide, which is something that we've done in our lab with Northrop Grumman and with the DARPA, which is essentially this, right? So imagine you have a camera that's going to fly on a, on a drone, extremely low power. It's going to be taking pictures, let's say, of this cityscape over here, and you just want to be able to figure out where this camera is, and it's rotating, it's translating, we have some other noise mechanisms and so on, right? So if I'm able to take the data that's coming off some form of a event-based system, and there are multiple ones now. Davis is one that comes out of Zurich. ATIS is the one that comes out of Prophecy or Octopus or other ones. And you get this stream of events. You can now apply, as I said, apply mathematics on the address space. You can basically compensate, as long as you have an IMU on your drone, you can compensate for rotations, for slips, for all these essentially motion artifacts, right? And then you can go and drive it to a neural array that does the accumulation and does the matrix multiplications, if you will, and then go on and you can then decode the frame that has been actually implemented or seen, or the track that's been seen. This is one of these spike processors, integrated fire transceiver array that comes out of my lab, where we have large numbers of neurons that essentially integrate spikes and produces spikes again. But these spikes now are the accumulation of the events that are coming in, essentially computing whatever the function or whatever the matrix that you're trying to put on, on top of it. And this is an example of the type of operations that you will see. So if you can see, but you've got these, so this would be the image that would be produced by the camera. At some point, then this would be what the camera would see, but you get events being generated by this image. Then this event goes to the appropriate dynamic remapping, if you will, and computation on the addresses. Then it fills up. Then it goes to the IFAD array, and the IFAD array actually is what accumulates all these events and then reconstructs the images that you can see and taking out. So this is called dewarping, because it takes out the warp that will happen because the platform is moving all over the place and so on. So this is a good example of showing different representation of data with temporal sparsity being reconstructed in such a way that is as if you're getting the real thing. You're getting the original thing without it, right? And then you can apply whatever intelligence is interested to you. Here, the intelligence was, can we reconstruct the pathway that this vehicle covered? All right. So the next thing that I'm talking about briefly is about visual saliency. And visual saliency is a very important feature, which is the notion that you're going to look at a scene and only things that are odd are going to stick out, right? What I mean is that it's basically a conspicuity detector, right? Because if things are odd, then most likely those are the things that's going to be important in any kind of AI system that tries to recognize the scene or recognize what's going on. So here's an example of this happening, right? So what is odd about this scene? It's the red flamingo, right? All the other flamingos are white, right? And it sits in this green background and so on. So can I figure out how to actually compute what's this, where is this odd feature of this scene? And the answer is yes. So here is, kind of what, this proto-object saliency map that we developed that looks at how the brain works in order to understand why this is different than what's around it. And that usually drives where the first thing that you're going to look at, your first saccade, first eye movement, is gonna actually zero in on that point, right? And then you can suppress that and look at other places in the scene as you need, right? But this first saccade can be predicted by our algorithm, right? Can basically tells us exactly what you're going to think is interesting in the scene. So how does that actually work? Well, I'm not going to go through too much here other than to say that, look, there, images coming in, there are all kinds of, spatial and temporal feature decomposition that happens. Then, and this happens at multiple scales. Then ultimately they get combined together. There's a normalization process that happens that picks out what is unusual in the scene, and then ultimately gets combined. The ways by which they get combined takes advantage of a particular feature of V4, so V2, and also in V4, where there are cells that are selective to which side of an object they sit on, whether they sit on the closed side or the open side of an object, and they compete. And when they compete, they create a proto-object representation inside the brain. And then with the appropriate competition, you can then isolate regions that are different from everybody else. So if I have a green thing sticking out, everywhere is red, that's gonna be the different thing, right? And in fact, here's a couple of examples of that. This green bar, every other bar here is red, right? So the green bar sticks out. I think can tell that. If you look at the bottom one here, everybody is horizontal. This guy is vertical, so it sticks out, right? So that's why you can take that out. And this is another cool one where you have this, boat. It's by itself. It's sitting in the middle of things. The motor is particularly salient, so it sticks there. But then watch what happens. Another faster boat comes in, which is even more salient. So it basically grabs the attention of the thing. So if I want to try to recognize boats, identify things that are going by, this mask might be the mask that I want to use to simplify my computation. In fact, that's kind of where we're going. That's where we're going, where you start off with some images, you use your saliency, both frame-based and event-based, where you get time associated with it, combine it, and you use that in a feedback mechanism to control what features are projected forward. Because once you do that, you can do things like this, where initially you had the original, those two cars going by, and both of them are salient. But then once you start using feedback, this is like a man and a car moving around as well in the same way. But when you start using feedback, then you see things like, hey, I only care about the big horizontal thing. So all of a sudden, you don't see the guy anymore in this one. But if I care about the guy alone, then I put that feedback in the right place, and it basically it ignores the fast moving car and focuses only on the object, the person moving, right? So you can play around with where in the saliency map you are, killing and increasing, and in order to pass features forward that are relevant. So again, going back to the saliency notion, right? What is salient? What is relevant? So that I can make computation faster in the future. This kind of tells you the same story I just told you a moment ago, but I think it's such a beautiful example of this that I find it hard to not show it. So this is a picture of a waterfall, and there are some other activities going on around this waterfall. or actually it's not a waterfall, but a fountain, right? So typically, this is where you're going to pay attention to, right? And this is exactly what our first pass of our saliency model tells us, right? But suppose now I use, inhibition of return and I suppress the areas that this guy is telling me, right? What I see then is there was a bee going past, and this is what that is right there. I would not have seen it originally in the original scene because you'd be totally compressed by the other big features or things that grab your attention first. So it's this loop now where you can suppress other things that are happening and keep other things and doing sequentially that makes it relevant. And we had a project with ARL to do that for looking at snipers, looking at different depth of field, whether you can suppress certain depth of field and heighten others, to help them better do their craft. And then we can do things where we are also looking at rotor speed, to determine what kind of drones that are actually happening. We can track those. We can combine, this is again, this notion that you can play around with this address space, right? You can combine it. You can completely combine different streams of information, but yet apply whatever recognition or whatever processing you want on top of that, and it separates out these blending fields, right? So I could, then you can stack as many as long as obviously they don't completely destroy the, the features that are at hand. You can do that as well, and you can track objects all over the place. Okay, so just because of time, I'm gonna go a little bit faster. Come on, go. Yes. So where does that all comes in terms of deep learning? Well, it comes in because now we are able to basically, in a pathway of typical deep learning, we can apply a mask generated by these saliency features, either temporal or spatial, right? And we can use that to basically prune the connectivity and the weights that goes through the processing network, right? So here what you're seeing is, a combination of the saliency based pruning plus random based pruning. So if I threw out a certain percentage of my data points, right? And this is keeping only 19% of the data points. This is keeping 33% of the data points. This is keeping 45% of data points. And what we're showing here is that, again, same kind of thing. These are this is now backwards in terms of here is only 1% of the data points is kept, whereas here all the data points are kept, right? So if you just use random pruning, you get the red line. Excuse me, you get the blue line. And if you do the saliency-based pruning, you get the red line. And of course, if you don't do anything, they both work about the same way, right? But the moment you start now applying saliency alone, saliency and random pruning, what you find is that the random pruning dies, whereas the saliency dies very gently, right? Because there's more information being kept, right? So again, sparsity helps. And you're doing this for about the same amount of compute, right? So in other words, you're not paying any more price in combining the two, right? So which is in terms of the number of epochs it takes to converge. That's the I see you shaking your head. Anyway, we'll talk. Yes. So yeah, so in terms of the average of the blue and the average of the red is basically the same, meaning when it stops, the number of epochs it takes to settle is about the same. So my student made me make sure to point that out. All right, let's skip that. It essentially plays a role as well in how data is routed in these networks, right? So if you think about this as being like your classical, GPU-based processing that happens in a typical machine learning scenario, by not multiplying with zeros and by not storing weights where zeros exist, you can drastically reduce the amount of compute you need to do. And this is a very big thing for these large networks with a whole bunch of with a whole bunch of weights to be computed. So ultimately, this is essentially showing you what happens as to latency, which is equivalent in a sense to the amount of data that you need to process. Okay, and if you have saliency gated, machine learning, this one I think was done on one of the ResNets. I don't know, ResNet 100 or something like that, if I remember correctly. There is, and the thick blue line is throwing out 99% of the connections. Okay, and the light blue line is throwing out 93% of the connection. And you can see that there is a drastic difference in the amount of time it takes to compute. Right. On top of that, what's the dynamic here, which is in the red, is basically to say that the data itself is also sparse, right? So the data is being gated by the saliency curve, right? So now you've got even a lower amount of latency, and it's significant, right? So in other words, saliency is a good thing, right? I mean, excuse me, not saliency, but sparsity is a good thing, right? So where are we going? So I truly believe that there is a way that all this wraps around with in vivo / in silico hybrids to do computation. And this is some of the things that we've been starting to do with some folks who works on organoids. I think that ultimately, organoids are a classic example where your electrode arrays are lower density than any neurons that's going to be in these organoid arrays, right? You know what organoids are, right? It's basically these tiny little brains that can be grown in the lab. And then you can put them in a culture and connect to them and actually stimulate them, record from them, and you can get them to do computation for you, right? The computation that they do is dense because it's got all the chemical milieu, it's got all the different cell types, it's got the connectivity that's a little bit still, up in the air as far as whether they're robust or not, but there is connectivity there. So can you drive them in such a way that will help do computation? Now, a 1 millimeter by 1 millimeter organoid runs on, a fraction of a gram of sugar, right? And that's the power that it takes to run these things. And you power it now with a neuromorphic chip that's going to provide the spike trains. Ta-da! Ideally, you can get much more computation than you would get in these big arrays. So there are, and again, the sparsity shell, I think, still wraps around these types of systems because the signal coming in is inherently sparse. Signal going out is going to be inherently sparse. And these are some of the things that we're doing with some other folks where we're thinking about driving drones with these, right? And having them communicate with each other. Again, the notion being that it's going to be ultra low power. It's going to be hopefully robust to adversaries. Is going to allow it, essentially get to a point where hopefully we can do kind of hive intelligence, communications between different organoids and communicating together and coming up with solutions. And that part is still very much science fiction, obviously, and and we are in the process of doing it. But there's a young woman named Anna Kuthari who works in these domains, and Hopkins has a few people are working on organoids for different reasons, but this is one that we are working with them with Sri Sharma. So anyway, I will stop here. These are all the folks that make it happen and folks who pay for what happens. Thank you.
Thank you. We have time for maybe 1 or 2 questions before we go to the panel. Thank you for that excellent talk.
Carrie, you had a question.
So you don't get anything for nothing.
True.
So your red curve is above your blue curve, and it's no slower. So there must be
okay. Go on.
So there must be something that it actually does worse on. And since I don't understand what you were on about, technically, I think I might, and you don't have to answer now, but I think I might get a better idea if I knew what actually you do lose. You don't lose computation. You must lose something unless you're magic, and this is the National Academy of Science.
Of science, not magic? Damn it. Where's the Minister of Magic, man? So what I'm saying we don't lose is the convergence rate, right? So that's what we're not losing, right? So the convergence rate on every one of them is basically about the same, right? On average, right? I mean, It's squiggly, but on average, they're roughly about the same. So what are we losing? That's a good question. I just don't have it on my hand, but I will ask Akwesi and I will have him write to you and tell you exactly what he's losing.
Okay, that's great because it's often, that's when you finally understand what's going on.
Yeah, no, yeah. So, I mean, I get your point. And I think that there is something that he's paying, the price that he's paying. Yep. Yes, sir.
I'm curious how your system differentiates attention from focus sometimes, because like when I was seeing one of those, I was kind of reminded of like a long time ago, the like basketball with the gorilla costume in the background, and how that sort of maps onto your saliency map stuff. Like,
right. So that's a classic. For those who don't know, there's a classic example where there are like a group of people passing the basketball around, and the announcer says, "Hey, count how many passes happens." Right. So you as an individual, you are focused on the counting the balls, and in that same scene, a big gorilla goes right through the scene, and you don't see it. Because at the end, it basically the announcer says, "Oh, but did you see the gorilla?" And you're like, "What?" And then you go back. Yeah, there's the gorilla right through the scene, right? So that's basically what's called covert versus overt attention, right? So covert attention is what you're physically paying for, what you're looking at, and what you are, like saccading to and counting, right? But the overt attention is the stuff that happens in the back, right? It is still happening, by the way, but it's just that it's subconscious, right? But the moment that the announcer said, "Oh, did you see the gorilla?" All of a sudden, you're like, "Oh yeah, there was a gorilla in the scene." And that's where the overt kind of pops up and then it becomes in your consciousness and then you can see it. So yeah, so it's part of the same thing. But we can, also there's another piece to this, which is the top-down versus bottoms-up attention, right? So when you're telling somebody to pay attention to something, that's called top-down attention, right? You're forcing the function, to look at that thing. Everything that I presented here is bottoms-up, right? It's all data-driven as opposed to intent-driven, so to speak. Yep. Okay.
So I was actually going to ask about the top down, bottom up. Are any of your folks is any of your work looking at incorporating semantic, so top down or mission
yes.
driven to?
Absolutely. So the person who's like the biggest person in attention who I've had the fortune to work with is this person named Ernst Niebuhr. He's at the Mind Brain Institute at Hopkins, and he's been studying attention for decades, right? And he has multiple examples of top-down attention, and he actually fits within that model that I talked about. It's just a question of where does it plug in. So in my it's funny that it's top down, but yet for me, it'll be plugging in at the bottom, right? Because I'm forcing what I want the groups to be, right? As opposed to letting the data flow down to form the groups for themselves. And that's the difference. Yeah, there is really cool stuff about that as well. Yes, sir.
Sorry. Yeah. I was thinking about the way that humans learn, and they learn based on what's memorable, which is not quite the same as salient. They're related. And I'm wondering, is there any work in including your salience algorithm in your training to sort of tune that to optimize your compression as you're optimizing your output?
Yeah, no, I see your point, and for me, no, I haven't looked into that, right? But I imagine folks working on hippocampus, maybe looking at those kinds of signals. There's a person, I think she was at University of Arizona, Catherine Cotidar, where she was looking at reactions to fear, and basically there was these primates where she would present certain features to them, and then they would have certain reaction that would be either fear or not, and they show their teeth and whatnot, and that loop as well, combined with essentially with saliency and fear reaction, contributed to memories and contributed to learning. So, but yeah, her name is, Cotida, Catherine. Yeah, so check her out. She does some pretty interesting work on amygdala and front, I think frontal lobe. Yeah.
We want to thank Ralph again. Thank you very much for a beautiful talk. And if you could stay up there, and we'll bring all the panelists and speakers.
Yeah. Right, and Ralph doesn't have any degrees. So I do all the degrees.
Is she on? Leave it off and then we'll point at you. So, all right. So I want to open this panel discussion with the kind of question you use with these panels. And that's for each of you. I'd like to hear, since the audience is the Department of Defense, when you think about AI and machine learning outside LLMs, what does Department of Defense leadership need to be keeping an eye on now over the next 3 to 5 years? What developments do they need to be tracking? And we'll start with Michael.
Dang. So when I was gonna have a few more seconds. It's all right. You had to pick someone. I think that, to me, I could be biased. I think that as we start pushing models, like making models smaller, maintaining performance, and getting them on closer to real-time platforms, to me, that feels like, especially if you could run them on existing. If you didn't, you could tell someone you can run it on a thing you already have. You just have to put some different, firmware on it or something. I think the push to make things bigger and more complex in terms of large language models is very cool and can solve things. But to me, I think that as you push things smaller, you can do things more embedded. You can do things on existing, doing things on legacy. And by things, I mean learned AI type stuff, I guess is what I'm talking about, is that if you could take some of the autonomy, and even if it's more simpler, some of the autonomy or classification or these new missions that AI can do, you can put them on an embedded system sooner. I think the near-term benefits are just going to be, they're going to outweigh being able to do some large language model thing, which again has its uses, but I think being able to loosen a bottleneck somewhere with a learned model that runs on an FPGA, I think is going to have a big impact, sooner than some large language model. But again, not to disparage, I want to be clear on the record. I just think that shorter term, some kind of an embedded learned thing like that, I think will be more impactful in the near term.
So I agree completely, since that's what I do. So yeah, no, I think that's a valid point, and I think folks are starting to go that route, right? So you got companies like BrainChip, Segance, BlueMind, and so on, where they are commercializing these things. But I do think still, so I have this real kind of love-hate relationship with commercialization, right? In the sense that, I think the moment that something gets commercialized, for us academics, we are essentially out of the game, right? Because we can never compete, just that the resources are not there for us, right? So then we let it go. So then I'm looking for the thing that's going to be relevant, 10 years in the future, not now, right? So, when folks were doing neuromorphics at the very beginning, it was like still a dream. But now it seems like it's coming for real, right? So that's why I ended up with where I ended up, because I do think that the combination of in silico and in vivo working together in a comprehensive way, and then looking at other types of ways, almost like meta learning how to learn, as opposed to just reapplying the same learning rules that that we've seen over and over again, and looking at how biology does it, right? So, the roles of like glia, the roles of, astrocytes are only now slowly being teased out and being seen as they are really relevant to learning, right? So how does that get wrapped into the learning rules that we see? I think those are the places that is still very nascent. People don't really know what to do with it yet, but it's that far ahead. Anyway, that's my perspective.
Well, let's go from the hardware people to the exact opposite. And that would be me. So not every model is LLM-like, and not every defense application is LLM-like, but some of them are. So there's some signal processing things that currently a human isn't doing, and AI might do it better or not as well. That's below my pay grade. But there are many DoD applications where somebody is doing something, and the question is, can a Gen AI do it? Or will we have a Gen AI do it? And it's not, some of those are LLMs, but there are many of those that are not LLMs, and it's still that kind of application. So I'm not the hardware guy, I'm the performance guarantee guy in statistics. And so let me tell you a little story. At the moment, when we bring on an intern, somebody who's we're not going to trust to do a problem that a human does, we don't trust the person. And then eventually, we make decisions that eventually lead to them perhaps sometimes becoming a trusted operator, someone who's also allowed to push the button or write the report or do whatever. And we have no proof that this person is going to succeed. Not as a math person says proof. We have intuition, we have anecdotes, we have experience, we have whatever it is that says that my first year graduate student whose paper I wouldn't publish without going through it carefully to my third year postdoc who I would read the paper, who I trust now. We have no proof of that. So if indeed any of the, Laura put up all the hype in the newspapers, if any of that's going to be true for the intelligence community or the Defense Department or any of those things, where we have someone, an AI, do something that a human is currently doing, I see A and not A as the only two options, being a logician. A is we come up with performance guarantees, which we don't require for humans, but we could, according to me, conceivably do for a Gen AI, even though we couldn't conceivably do it for a human. Or we decide we're going to do like we do with other humans, where eventually Amina called me a few times on Zoom and I thought, what's she on about? And eventually I decided I trusted her. And now I will let her do what she wants and I will listen to her. One of those two things, the third one is we don't do either of those, and we just, because it's cheaper and somebody thinks we should let the AI push the button. I hope it's one of the first two. The human psychologists say it's really, really hard to do this, get this confidence, even with humans. So how are we going to do it? But people are working on that approach to trusting AI. And there's ways to do the trusting AI with mathematics, but hopefully one of those two will be done for DoD applications.
Can I follow up? So the in your talk, the size, right? Somebody had to know what is the kind of almost a ground truth, right?
No, sir.
So, but how do you know how close you're getting to something if you don't have something to get close to?
Okay, you do know the answer, but I'm gonna remind you.
Okay.
Or that was rhetorical, so that I could remind the audience. In statistics, the world's simplest thing is I have IID data from a Gaussian with unknown mean and known variance. I don't know the mean, but with samples, I know that I'm close to the unknown mean. So my sample mean is 0.037, And if n is whatever n is, and I know the variance in this simplest case, I know approximately where the unknown mean is. Right. And so under ridiculous assumptions, I can do it in that situation. And I claim, without proof, as they say these days, but I think I have proof, that we can do that same thing for those psis. So the psi hats are close to an unknown psi, but I know they're close to it.
Okay. I guess I had to read.
Say, you understand that a lot better than I understood your thing.
So I'll just add to that. I think kind of what I noticed your talk getting at is, over the past 30 years, DoD built up a whole framework for and NASA too, verification, validation, and accreditation. It can be a struggle to get people to do that work on their models because it's hard, it's slow, it's expensive to do that. But it needs to be done.
And DoD made people do that because you can do that in signal processing, in many signal processing situations. And since you can, they made people do it. I hope so. I hope they find something that they're willing to make people do for Gen AI.
So first of all, I'll answer your question differently. So, but I do agree with this professor that we need to have AI trust but verify. So trust and verification has to be side by side. Why I trust these results? Like again, like it's not a closed form solution. So therefore, I should have trust but verify. Then second point to me is okay. Why? Well, AI is everywhere. So define why, like a DoD, we are using AI. So to me, two reasons. One is automation, meaning that we have huge, gigantic amount of data that otherwise is not possible, impossible, like, for analysts to analyze. So we make a robust, reliable AI model that will guarantee the results. It has to guarantee the results. The second thing is like some of the cases, like say, like SAR imagery, like I showed, the visually analysts cannot see the difference that, okay, hey, what is, are they same or different? But those manipulation happen. So therefore AI, like, like putting into the AI, it kind of like say, see the things. Simple example, like say you take any image and if you do the edge detection, you will see the features. So some of the area, the subtlety human eyes cannot capture, AI can do that. So now going back to your questions like that, okay, now that we have AI, so then how do you trust and how do you make the model? So the model building goes in effect that it should not be like one size fit all. So that's what I think we have different types of problems. So we should not like combine, like, I can do those, tank detection versus like the speech recognition or signal classification. These are all different, types of problems. So you rather make, a problem like AI-based solution very, problem specific. So like it could be like more modular, like say you have hundreds of targets. So hundreds of targets or objects could be like say ground vehicle or naval or like, space or somewhere else. So we tend to say that, okay, hey, we make a taxonomy or ontology of hundreds of thousands of classes like ImageNet and putting into the AI for DoD. This is really big mistake and people are doing it. So now why it doesn't make sense? It doesn't make sense because, like, say, if I am interested for ground objects of interest, I know that I should not see any vessel. So why I should make this vessel and ground vehicle together? I make the model that kind of see this type of vessel. And if I expect to see these objects into the into the forested area, so I'll make a model for that. So we need to have multiple models, kind of ensembles of models you can have, and the analyst should be able to pick, okay, hey, here is my data, here are my expected targets of interest. I like to see them. So I have 10, 15 classes of targets based model developed, and this could be running like easily with the computation for training and then inference time. Everything becomes much more, very compartmented or very smaller in scale. You can handle easily. Like, so maybe in area of interest, you may be able to see 10 objects of interest, and all of a sudden you saw a new class come in. You can retrain the model. 11 class training model is much easier than hundreds of thousands of classes, retraining. So again, if we need to make the modular kind of models, that's kind of easily, computationally attractive and real time, maybe embedded system could be implementable. So that's what I think we should be moving forward. Over.
As a follow-up to that, I was listening to the talks, and some of the talks spoke to, beyond the modeling type, a framework for the modeling. So the idea that you have the salient maps across time and space. And Carrie, you referred to frameworks for dimensional reduction, that you could view the models in a way of their similarity to dissimilarity. But I saw a value in what you presented as not only on the model comparisons, but on understanding. You showed whether you could provide a map of if you added new data or you added proprietary data, is that really informative? So these two things, these paradigms or frameworks, add beyond is this a particular type of generative AI? It's the framework that I think is so valuable. And I was wondering, are these frameworks, the first time I've been introduced to some of these frameworks, are these frameworks being publicized? Are you sharing this across different model developers or different types of models? Is it something that?
Well, you correctly noticed that the work that I presented, the whole DARPA AIQ program that I have, project that I have, was thanks to Microsoft Research giving me the suggestions and whatnot. But I'd been doing that linear algebra, some of that stuff, on time series of networks, swarms communicating with one another across time, and much of that linear algebra and statistics came out of through maybe one of the leaders was Avanti Athreya at Hopkins, who is the brains behind the operation. But that stuff has been published in the statistics and the IEEE transactions journals for a few years. And the idea was, it turns out there are Gen AI questions that can be answered with at least starting with that stuff. And so there were some things that we had to do differently because some of the questions are a little bit different. But the procedures you're talking about in the dimension reduction and what information do we keep and what do we lose? And as Ralph was saying, this truth that we're talking about that we guarantee we're close to, even though we don't know, it depends on what representation we pick there. So we have ways to come up with the good pick. Some of that is basic and applies, it's a framework, as you said, Amina, that applies sort of generally across what I would call statistics, which when Carrie talks, she means everything you could care about, right?
So for, not to just to address directly what you asked about saliency in learning, not new, right? I mean, in the sense of, you look at transformers, there's that, the multi-head attention model, right? Except it's not attention, right? It's just another means of specification at the end of the day. What is different in terms of what I've presented is, because we're trying to use models that are biologically plausible, that are modeled the same way that hopefully the same kind of processing that happens in the human brain takes place, or, well, not human, but in the brain in general takes place, that is where the novelty is, right? Is this notion that, there are these interactive, interrelationship between, like the interferal region versus, like the what and the where pathways, if you will, combine them in such a way that you can then focus on the real things that are important, and therefore maximize the likelihood that you'll remember or that you'll store, right? So those are the places I think that is kind of different or unique. So this project was funded through an EFRI project, the National Science Foundation, and so we continue to do it. And we are getting close now to showing significant improvements on the classic ways of doing things by adding this particular pieces. So yeah.
Can I follow up and ask a question to Carrie? I guess the inputs were all the same. You're relying on some random distribution within these models and how they generate their responses. But to, some of your like adversarial, notions, like really, I mean, the failure mode of an LLM or some of these models that you were probing might be that For example, if I set a fortnight instead of 2 weeks, I might get a way out of distribution. And even though semantically I meant the exact same thing, I get some incredibly bad thing. And this, in the sense, I'm making an adversarial example, for this large language model, and that you really need like some distribution over the semantic meaning of what you're inputting. I see some look here, so there must be some preprint or something that I'm stumbling upon. But yeah, that you would need to be able to assure both. Or you're either going to tell a defense the only way you can ask this question is this way, or here's the distribution of ways that someone might ask this question.
Right, you're
And then,
exactly right.
yeah.
So, yeah, I was making eyes at Amina because we're talking about this in the DARPA AIQ program. It starts at first. So the first thing that it says, type 1, is if you ask it the exact same thing, you'll still get different answers because it's a random map. And so can you characterize things in there? And then the second one is your fortnight, 2 weeks. If you ask the same question semantically, just a little bit differently. So I will tell you that, and that's a thing that Amina and I have been working on a little bit as well. But I will tell you, so if you ask, was R.A. Fisher a great man? I might have said earlier, you ask it 10,000 times, you get 98% yeses. It turns out if you say, was R.A. Fisher a great man, you don't get the same thing. But almost the same, like 0.97 instead of 0.98. But I mean, they're different tokens. It's a really subtle version of your fortnight, 2 weeks, but it's the same thing, and you never get the same answer. Nothing is going to be exactly the same. So the only question really of interest is when they're semantically similar. And now you've got the user defines that, and it's like you could add an extra space, it doesn't change anything. That's obvious. You could put dots versus not dots on initials. Then you go all the way from R.A. Fisher was a mathematician, R.A. Fisher was a statistician. We mean the same thing, let's say. Fortnight versus 2 weeks, we mean the same thing. But if you say R.A. Fisher was a geneticist, was he great? That's different. The answer is still yes, but it's different. If you say he was a eugenicist, was he great? You get a very different answer. So first we have to define semantically equivalent. Then it turns out, since we don't know the map from query to probability, these are all just Bernoulli questions, yes or no questions. That's even a hard problem. So you're exactly right. And the whole point of, you tied it to adversarial. Well, I don't buy into the word hallucination. I mean, it's just doing whatever probabilistically it's doing. But and it's not bad or good. I mean, next token probabilities don't have that either of those properties. But it is fatal versus not fatal for many DoD applications, right? We're not just talking about some big company losing money. We're talking about actual fatal. So you have to know when it's going to, or be able to provide an upper bound on the probability that it's going to put you in this box, which is a region of response space that is fatal. And under some situations we can do that, but we're not going to be able to come up with every possible semantically equivalent thing. Fortnight, we might have forgot that one, and that might put us in the fatal situation. So that's why I want to phrase the question from the point of view of are they giving the same answers is also a relevant way to look at it, because if you know one of them doesn't put you in the fatal situation and they're approximately the same, then you can bound the probability. But it's not adversarial, but it could be fatal. Fortnight, that was a good one.
Yeah, well, actually, so to add that thing, so that's what I think when is a adversarial. So we need to know when the results are not going there, and can you predict, in a manner that, okay, hey, I know that I give this data for testing, and then and I know that I do not know the background information or like the a priori information or metadata information for testing. And so that I can take the results in a grain of salt that, okay, hey, even though I got good results, but I'm really like, for a federal decision, like say, I have to be really careful that, okay, I knew that it give me good results or bad results because of that. And if it is good results, and I have seen the evidence consistently that, okay, my training data and testing data matched, and then therefore I got good results. It never happened. Mistake never happened, right? So I'll be 100% sure.
Lauren, can I run into 2 minutes worth of math?
You hold the floor.
Okay, so that's right, and that was a great question, but there's a math thing. Let's see if we can do it without a chalkboard. So RA Fisher versus R.A. Fisher, or spaces, those are, we could say there's a distance on the strings that is relatively small. And a Lipschitz continuity property is one where a small distance on the input yields a similarly small distance on the output. So we can prove under a Lipschitz assumption on this map, and it's a little bit more complicated because it's from a space to a probability distributions, but we can make this work. We can prove that if Tom's thing works for one of them, it won't fail very badly for the other under Lipschitz. But fortnight versus 2 weeks may not have that same property. It's the semantically equivalent, means the strings are really close sometimes. And sometimes it means semantically equivalent, but the strings aren't very close. And so that would be a different kind of math question. And so you can control for one. It's possible to control for one without controlling for the other, and that could be fatal.
Maybe the 2 weeks fortnight one is a little bit.
And I got to say Lipschitz on camera.
And Prost earlier on. Anyway, so maybe the 2 weeks fortnight one is a little bit closer on that semantic line as you're talking about. But I mean, there are obviously, what's the word I'm looking for? Idioms, where the words are like, but they mean the same thing. How do you account for that? That would be like out of distribution, basically. That's what would happen.
Well, they wouldn't be out of distribution because if we're talking an LLM, it's trained on the Google net. If we're talking whatever else, it's going to be trained on a bunch of stuff. But what are we after here, right? I mean, human performance is not what we're after, because when I give a saying, an idiom in class, I have to ask the American students if I get a bunch of blank looks, because sometimes it's an American idiom and sometimes it's a rural Iowa. And many times the Americans don't see it either. So what are we on about, right? And so yes, that's there's things that aren't going to be that if you treat this thing, if we're going to trust it to be a collaborator or whatever, to push the button, we're either going to, Lauren and I were talking and you were listening about, we either have to prove it or we have to find some way to trust humans, right? Well, if we're going to rule out this idiom thing, we're going to have to do a bunch of math that I can't do right now. Or we're going to have to restrict the way you do the input. And we're not going to restrict it to only this question, but we're going to have to filter out a bunch of stuff. And that's not how that's not how Amina treats me. She lets me talk however I want. She regrets it sometimes, but she lets me. So, right, that's part of this analysis, right? I mean, if we're going to figure out how to do it, there's going to have to be guardrails. We currently put guardrails on various real applications, but these are going to be different ones than we've thought about before.
So Amina's going to cut me off, but I got to throw this in here. My favorite community, I'm sure there's some in this room that are familiar with it, is for understanding how people learn to use computational tools is weather forecasting. And there is a large and just wonderful body of literature that examines. I'm a weather nerd and I read the discussions, the forecast discussions every day. I read all of them because what they're doing is discussing how they're making sense of the models. And which is something I used to do a lot of work in V&V, and I just find it fascinating. And I think we have a lot to learn collectively as a community about how to enable people to interact and make sense of any computational tool by looking at how weather forecasters do that.
Okay, that's great. But what you said earlier, I think, is essential. So that can be done. And the weather people did it. Somebody's going to have to make, because the industry is, there's too much money in it to do the next thing. And, you know, so somebody's going to, DOD or somebody's going to have to require that certain things happen in order to make these situations for any, I mean, the title of your workshop, it's critical DOD technologies or whatever. I mean, we did it, you people, not you've done it before. The only way that this is going to work without some problems is if we do it again.
So this whole time I've been thinking the game is now come up with two strings that are very close in edit distance, but have wildly different semantic meaning. I guarantee it's going to have the word flag in it. If I can think back to like studying for the GRE, flag has like 9 different meanings. I guarantee flag is in that string. So how could you, what's the two strings you give and it interprets this very common word one way with this string, and I changed thee to the, or I changed thou to it's
yeah, but the linguists have a lot of that.
It's now switched the second word to, or that variable meaning word to its other meaning, and now interpreting flag as like, well, you look, you're getting tired. Yeah, you look tired. Yeah, and it's responding as a drink some caffeine as opposed to you know, yeah, most flags are rectangular.
And when you know, when first year graduate student graduates to postdoc and we trust them, it's because somehow based on all the context or whatever else, they're going to get it right. And maybe ChatGPT 6 will as well, or the image analysis or whatever non-linguistic LLM. But as long as you're going to have a random variable as an output and map from input to output that you don't know, you're going to have all these issues. So these are not, you know, unknown issues in mathematics, but it's an issue.
What is the variability? And I mean, again, my chimpanzee brain understands like 20 numbers at once. And so these models have, you know, billions and billions of parameters in it. Where does all this randomness come from? Are there seeds like by layer? Is it seed by sub-tasking? Like why can we not fix the seed on a lot of these things?
Oh, you can fix the seed.
Sure, but what is the, I mean,
you can fix the seed and you can reduce the temperature, and we're not talking about training time because I don't talk about it. But the randomness is inherent in the. Sorry, I don't know if I was supposed to answer.
No, it's okay. We're getting back to our
story of what these things do. That is, if you're doing you don't do tokenization, but if you're doing next token prediction, where no matter how much you're going backwards, and even if you're going back and forth, you've got a probability distribution on what that token you're predicting it. So you can choose the highest probability, and now you don't have any randomness, but you also don't get the kind of behavior you want. So you choose probabilistically, and so you're, regardless of whether there's any randomness, you want it to be random. You're forcing the randomization in the by choosing next tokens according to a learnt probability distribution, and it's got nothing to do with the way that it was trained or anything else, because a next token probability distribution is a probability distribution on next tokens, and so it's inherent in what they're trying to do.
Sure, yeah, I mean, yeah, in this diffusion process of
same thing.
Yeah, but I mean, I just wonder to get after this problem of like, I'm going to also require that this probability distribution essentially be as delta function-esque as possible, and so I don't want this, no matter how you ask.
But then nobody's going to fall in love with that.
Sure.
So I just want to thank everyone. We're a little bit over time now, and it's really interesting discussions that we can continue. Just want to. Yes, the audience has not been able to ask a question. So let's go ahead.
Hey, great. I just have a question. I've been thinking about all of these great presentations, and I've been reading. I always go back to Baruch Fishoff and Risk, and a lot of his work. on risk. He's at Carnegie Mellon. And my question is, how do these different AI models and all the different things you guys presented on, what's your conception of risk? Is that a system question, a performance question, a values question? Carrie, you were saying something about fatal or losing money, and you have a great talk on sparsity. And I was just wondering, a lot of times humans like agency. And so if you give AI models and they pump out risks, humans like to decide what risks are worth it. And they like to have democratic deliberation to kind of define those risks. So I just want to know, what does a reasonable AI model look like? If a reasonable person would like to be sort of epistemically humble and try to gather people to kind of define risk for a particular industry or sector, how do you operationalize risk, and what's the conception of risk, and how do you embed that in your inner workings? Thanks.
Give you the short answer. So again, it's a loaded question. So I think the adoption of AI for your applications should be something that based on what is your applications, and make the model based on your applications need. So I mean, I hate to say that, yeah, there is no generic answer, like in how you can reduce the risk and what will be the best model. So there is no generic answer. Yeah, over.
So I guess for me, because I'm a hardware guy, risk is something that doesn't work, right? So, and the places where things fail for me is more like latency. It takes too long to get an answer, right? By the time, and the control loop is too slow. So by the time you close the loop, the system has passed you, right? It's gone and so on. So it's those kinds of things that worry us, right? Or being out there and and you run out of batteries too soon, right? So those are the real elements in terms of you're flying a drone and it falls, and it doesn't give you the data that you want. So those are the kind of things that at least from my perspective as a hardware designer, I think about. From the computational neuroscience side, it is interesting. I mean, in the sense that my model could be wrong, but at least physicists, he says it's okay to be wrong, right? You just don't want to be not wrong, not even wrong. So you can fine tune wrongness, right? You can get better at getting improving the models, but that's a matter of understanding what the physiology is telling us, and what people are measuring, and then folding that into our model. So we have to continuously work with the folks who are generating the knowledge to make our models better. So if you lose that loop, I think you also are at risk of not keeping up with understanding what the systems are doing. Anyway, my perspective.
I'm going to sidestep this somewhat elegantly, maybe not. To me, Tom, to your point, there's no generic maybe sense, and I don't even know if I ever, not that I don't consider, but it's situation dependent, but also that's not my call. Ultimately, especially in an application like defense, like the end user, the person who's making that decision, that's their job. Like, I'm not going to tell them how to do their job. They're experts in their mission. They're experts in their requirements, and whatever they have to do. I'm here to provide the tools, and certainly that needs to come with some kind of performance metrics. And in the same way that the spoon has its requirements that we build and give to people. They have to know when it's going to fail, know when it's going to work. The same thing here, that we need to have good methods for assessing when things will work, when they won't, the failure modes, what they're good at. And then, like, here you go, here are the tools. Now the end user, again, the operator, whoever it is, can decide, make an informed decision of the risk of for what they're doing right there, because this radio won't work, but it's okay because you're back in CONUS and you're in beautiful Washington, D.C. Okay, well, the risk is relatively low then, because I wasn't really sending much data back and forth anyway. But there could be other scenarios where this radio stopping working is a huge risk. And so don't do whatever this AI thing is telling you to do or something like that, right? So maybe not elegantly sidestep the question, but
that was very good, actually. And I know we're past time, but as a statistician, I'm not passing up a risk question. That would be risky for my career. But actually, the summarizing this, all three of their responses were splendid, I thought. And so I'm not a hardware guy. And have you noticed that Ralph starts every sentence with "I'm a hardware guy"? But I may have never said actuator before, but the question, I mean, at some level and in some form, that's the deal, right? The Gen AI is running, and the risk happens when it actuates, right? When it pushes a button or it writes a report or whatever it does, that could be what we want, or it could be bad. And let's call it, that's where risk comes from, right? Is something that's bad. And so for me, and then the discussion, whether or not a particular actuation is bad for a given input depends on the situation, on the scenario, where you are. And so that's completely up to that. So there are two extremes now. There's, somebody, I think it was you, yeah, you said you're going to let the boss decide that. And if they want to build a model, I mean, that's what reinforcement learning with human feedback is somebody decides, I don't want it to do this in this situation, and you just keep hitting it every time it does that until it doesn't do it very often, right? So if you're training the model, then that's what that is, and you pick what things you want to reduce the risk on. When you decide when to do that, you're defining your risk, even if you don't do it formally. And then at the other end of the world, for me, it's just the response is in this region of response space, right? And eventually, if it's in something, then that will trigger an actuation. And I'm just interested in what can we say about, again, combining all three of your responses, what can we say about the probability that the response is in polytopes in response space? I mean, that's all I can say about risk. That's all. If I could tell you everything, that would be all you'd want to know about risk. Now the question is, which things are the most important if they're going to be used in critical applications in the next 12 months? What can we do between now and then, or whatever the situation there is?
And we didn't even get into uncertainty quantification. Okay, we're going to stop now. Thank you, everyone. This was really fun.
I'm not a hardware guy.
Yes, thank you, Gabby and Richard and